University, Tirunelveli, Tamil Nadu. He did his PhD from Gujarat Agricultural University in Agricultural Statistics, and his research areas including, not limited to, including design of experiments, stochastic process time series analysis, and extreme value theory, and so on. He's very active researcher, very young professor. He produced more than 10 PhDs and around 14 MPhil guided 14 and more than 14 MPhil students, and published more than 50 research papers in national and international journals. And also he delivered invited talks in around our India and abroad. And also he's very active researcher and has research fundings. And with these words, I welcome Professor Loganathan sir in the absence of Professor Rajarathinam. Thank you, Professor Satish Kumar, for giving these opportunities, and thank you all. Now I invite Professor Loganathan to chair the important session. Thank you.
Thank you, Dr. Bindu, for your kind words and helping me to introduce the speaker, Professor Anna Panavska, and I thank Professor Satish Kumar for giving me this another opportunity to chair this session. And since enough introduction has been given about the speaker, let me not waste our time. And the actual chair is on the way. He is coming on the line. And let me invite on behalf of the organizing committee, our speaker, Professor Anna Panavska, to deliver her talk in the special session in honor of Professor Alayamma George.
Thank you. Thank you very much for inviting me. Now I need to figure out how do I give a talk. So I press present now. Professor Satish, how do I give a talk? Okay, maybe. How do I?
How to share?
You have slides to share?
You can share your slides.
How?
Okay. Yeah. You go to, madam, in the bottom there is a hand raise button. Hand raise. Near to that there is an upward arrow. Okay?
That upward now.
Yeah. A small box containing upward arrow like that. Near right to the
just to the right side of the raised hand.
Click on there.
Yeah.
Then your entire screen comes there. Isn't it? 3 choices.
And before choosing that, madam, you have to open your presentation file.
I have it open.
Yeah.
Okay.
Yeah. Click on the entire screen. Okay.
Okay.
Now a small window comes there, and click on the middle of that portion so that the share button will be active.
Can you see the presentation now?
No, you click on that share.
Oh.
Click on that share.
Share, it says.
Okay.
Yeah, but
so
I did. And
just click on a small in the
I see the icon, but I cannot share.
Right corner of the right below corner, bottom corner.
I'm trying to click on it, but
that small window in the right bottom corner, there is a share. Can you see that share button?
I see, but I cannot click on it.
Yeah, just click on that share. Whether it is active now, it has a color change.
No, it just
click on the middle of the window. To click on the middle of the window, so that portion, then that share will be active. So that just click on share, you can go.
I understand, but it doesn't want to share at all.
Yeah. Don't worry. Let's just try once again.
Okay, let me.
Or if it is difficult, any difficulty, you can send to me the slides. Like
That is fine.
from here. Yeah.
That is also fine. You can
Mail to me.
send your presentation file to the Dr. Satish Kumar.
Okay.
They will
Now, can you
showcase
see?
your slides.
Okay. Can you see the slide?
No, madam, it has not opened. You have
Just
because
once
you have
again,
not posted.
madam,
Yes.
professor, yeah, just you try once again. Yeah, now it is coming.
Yes,
Now it is
yes, it
coming.
is
Okay.
fine. It is
Okay.
fine.
Now it is fine, professor.
Now you're cooking.
All right. Sorry about it. I think I have about 10 minutes to finish. So I'll just go somewhat maybe quickly. The talk here. So first, let me say a few words about Professor Aliana George. I also looked her up. I couldn't find the date or the year when she was born, but she lived and worked in Kerala in India. She did her PhD under Professor C.R. Rao. And her research was really statistics, but her focus was on demography and vital statistics, okay? Now, I'd like to thank the organizers of the conference and in particular, Professor Satish Kumar for his support and help. I got data that I used for this talk from Professor Castillo and Papasopoulos, and the research was actually supported by a European grant. So I'll talk a little bit about generalized Pareto distribution, and I'm going to call it GPD. You're going to hear a few things that echo what Dr. J or Professor Jamalamadaka said. And so I'm going to talk about Greenwood statistic, which actually he mentioned as well, and some issues with estimating this model using maximum likelihood, and then some solutions for estimation and for testing that we took. So what's a generalized Pareto? I just introduced generalized Pareto distribution via a stochastic representation, and that representation has to do with exponential distribution. So essentially, a generalized Pareto is e to a power that is an exponential distribution. This is a general representation, and so in this representation we have two parameters, alpha and beta. Now, parameter alpha is way more important than beta. Beta is just scale, but alpha actually tells us what kind of distribution this generalized Pareto is. Now, we call it generalized Pareto because these distributions come as limits in peak over threshold theory, which I'm going to talk about in a second. Now, the notation here, we're going to say that X has a generalized Pareto distribution with two parameters. Now, depending on the value of alpha, either I get a distribution with a power or heavy tail, or I get exponential or a essentially beta distribution. So for positive alpha, this generalized Pareto is a low max or Pareto type 2, and it has power low tails. For alpha equal to 0, we get exponential, and for alpha distributions. Okay, so there are really three cases of these generalized Paretos. Now, how do they come up? They come up in the peak over threshold theory because they are the limits for the normalized excesses or exceedances of observations over high thresholds. So that's why this is the connection with extremes, actually. Now, so they approximate what is left over of some, let's say we have a random variable y, and I subtract some threshold d, and given that my y exceeds that threshold, so given that the observation is large enough, essentially, for increasing threshold, the generalized Pareto is a good model for that distribution of the excess. Okay. Now they also have power law tails, and for alpha greater than 0. I'm sorry, there is something weird with my deck, but anyway, so there are many applications for the power law tails, and they go from ecology to finance to hydrology, etc. Now there are also applications in insurance mathematics, in climate science, and essentially everywhere where observations over some high threshold is of importance. So again, this extreme value connection. Some examples of power tail data. I did a little survey, and they are everywhere. So we have examples in geosciences, in seismology, size of landslides, mountain collapses, wildfires, hurricane losses, and so forth. They actually exhibit power tails in economics and finance, in social science, in the everyday internet, the data sets actually that come up, many of them will have these power tails. Okay. Now, why would we be interested in those events, in these extreme events? And the reason is very simple. It's just that these extreme events, they are very impactful. They have a huge impact on our life, safety, economy, and so forth. So one more thing that in general I want to say about GPDs is that they are related to generalized extreme value distributions. And in fact, there is a one-to-one correspondence between generalized Pareto and generalized extreme value distributions. So for generalized extreme value distributions approximate or provide limits for maxima of IIT sequences. Okay. Now, the main question. So really the main question for GPDs, for the generalized Pareto distributions, is what is that index alpha, the tail index? And the reason that it's important is that, as I said, depending on the value of alpha, we actually can have completely different distribution of the process that we are studying, right? So we chose to, for testing on alpha, we chose to look at the Greenwood statistic, and there are many reasons why. I'll talk about the reasons why Greenwood statistic in a minute. Now, my Greenwood statistic is denoted by Tn. N is just the sample size, okay? And it's a sum of squares divided by the square of the sum of observations for a random sample. Now, the Greenwood statistic is related to many other very well-known statistics, such as coefficient of variation, self-normalized sum, or the student t statistic, okay? Now, why is it that if I want to test for alpha, I'm not choosing a standard likelihood ratio test? Well, the reason is that just like Dr. J was saying, in many cases, if I need maximum likelihood estimators, and I really don't have them well defined for generalized Pareto distributions. Now, if in order to do the likelihood ratio test, I would have to have MLEs of the parameters, and actually, there are many cases in which there are no MLEs, or if they exist, they may not be well defined. So the likelihood function can, if we don't impose any restrictions on alpha parameter, then the likelihood function can simply go up to infinity, and then the MLEs are not well defined. Now, even if they are well defined, sometimes we don't even know that they are unique. Okay, so the question of uniqueness here is still open. Okay, so of course people try to compute anything, and when trying to get MLEs for GPD, this for generalized Pareto, there are many problems with that, and they are documented problems in literature. Okay, not to mention that there are some inaccuracies in the estimating literature. Now, so essentially, when you look at the number of problems with MLE, with the estimation, a solution comes up saying, well, if I want a test, why don't I make a test that is based on that doesn't require estimation of alpha? Okay, so it's not based on an estimator of alpha. Okay, and therefore the idea of the Greenwood statistic. Now, that there are more reasons how Greenwood statistic comes to play in this case. Another reason is that in order to have a test that is well defined, so that I know that the rejection regions are correct, I basically need to have the test statistic that is stochastically monotone with respect to the parameter, either increasing or decreasing. And it just happens that for generalized Pareto distribution, the Greenwood statistic is monotone. Okay, it's actually increasing. Okay. So I'm going to skip the previous work and just say the conclusion. There was a lot of interest in estimation for generalized Pareto, and it is connected with extreme events and all kinds of engineering problems and science problems. And there was a lot of work done. The problem, though, is that we have not found any test that actually works on small samples and without any restrictions on the values of alpha. Okay, so the tests that were introduced either were asymptotic type tests, or we had to they had a restricted region of applicability for the parameter. Now, in this work, one asks, okay, so what would be a competition for our test? And there is another statistic, a test statistic, we call it R, that was used for testing about alpha when the data was coming from GPD. And an interesting thing is that this statistic R actually has very similar properties to the Greenwood statistic, okay? And one of the main properties is that, first of all, it doesn't require estimation of the parameter, okay? So that's a good thing. And second, this statistic is also stochastically ordered with respect to alpha. So it's a legitimate competition for the Greenwood statistic-based test. I'm trying to go very fast. Now, I just mentioned what do we mean by stochastic order here, and really we are only using ordinary stochastic order where we say that, say, random variable x is stochastically smaller than y when the CDF of x is greater than or equal than CDF of y. You can think of it, and I think of it as a random variable is larger than another in a stochastic sense when the probability of large events is larger for that variable. Okay. Now, this is this symmetry of the Greenwood statistic and actually R statistic within the GPD family is an important point when we look at domains of attraction. So both GPDs and the extreme value distributions have their own domains of attraction. And actually, if there is this one-to-one correspondence between extreme value distributions and GPDs, and if they have the same alpha parameter, then they have the same domains of attraction. So the tests for alpha actually also answer the question to what domain of attraction a given distribution belongs. So typically when we test, well, for domain of attraction, but also for just in general here, we may consider using excesses. So we don't use the entire sample, but we just use the excesses over some threshold. And the reason is that it's these excesses over high thresholds that should be either should be approximated by the extreme value distributions or GPDs. And the question is, so how does the Greenwood statistic or the R statistic behave? And an interesting thing is, and these are some recent results, some of them already published, some of them not, that if I look at the Greenwood statistic and compute it on excesses over a threshold that is one of the order statistics, then essentially this is the same. So the distribution of that Greenwood statistic is going to be the same as a distribution of Greenwood statistic if I actually looked at the GPD data. Okay, so this result actually makes all of that inference for domains of attraction sort of legitimate. Okay. All right. There is also some limiting behavior, and all I'm going to say about properties of this statistic is that they are basically the same as properties of the Greenwood statistic. Both of them are actually bounded, so they are between 1 over n and 1. And so I'll just mention quickly this testing for alpha within the GPD family. And it's a beautiful theory based on fundamental ideas of statistics. So if we have a sample, IIT sample from GPD, and remembering that TN, that the Greenwood statistic, and the same for R statistic, they are scale invariant, then I can assume that the scale parameter is simply 1. And the goal would be to find that.
To disturb you, Dr. Anna Panoska, this is how much time you require further? Because as per schedule, we have 5 more minutes. Only 5 minutes.
Know, so I'm just going to say 5 minutes.
Okay. Proceed.
Yeah, I'm doing this very fast. Okay? So just if you want a test, what I'm going to say is that using Greenwood statistic or a test based on the R statistic, we can get a test on any level that we want and actually unbiased. Okay, I'm going to skip this. All I'm going to say about practical implementation of these tests is that it's very easy to implement them, and the implementation is via p-values, okay, which can be computed real easy using Monte Carlo. One can do two-sided, one-sided tests. One can also do confidence intervals for the parameter. Now we did some power analysis to compare if the test based on the statistic Greenwood or R are comparable as far as power, and basically they have the same power. We wrote a paper earlier, this Kozłowski et al. 2009, discussing testing just exponentiality versus Pareto with positive alpha, so essentially alpha equals 0 versus alpha greater than 0. And this the test based on Greenwood statistics. So here, this was a likelihood ratio test because in this case, we can actually get the MLEs. And the test that is based on Greenwood statistic or R statistic that are really trivial to implement, there is no estimation necessary, have exactly the same power. Okay, and I had two data examples. I'm just going to talk about one of them quickly. We wanted to see how our tests stand in comparison to published literature about certain classic data sets. And one of the classic data sets in extreme values is the crossings of river needs. So that means it's just recording of exceedances over 65 meters square per meter cube per second flow. Okay, so it's basically recording of excess flow of a river in UK. Okay, these exceedances were analyzed by many people, and the main question was whether the exceedances are Pareto or exponential. And so we also used several thresholds for the exceedances or excesses, testing that hypothesis, and we agree with the common perception that the exceedances should be exponential. And with that, I'm going to finish, and I think I'm not too much over time. So thank you.
Thank you, Professor Anna Panowska, for helping us to maintain the time. It's a very good lecture on the testing approach of generalized Pareto index, which is based on the Greenwood statistic and RN statistic. And I wonder that it has a lot of applications from geoscience and varied areas, geoscience and internet and social science. I wonder, it has applications in social science also. Excellent talk. Due to the as per the schedule, we have to wind up this session by 10:35. However, we can allow some questions or doubts or comments from the participants. Some of them will be eager to ask questions regarding this.
But you are also welcome to email me with any questions you have in order to get the next speaker, to give the next speaker some reasonable time. It's all right.
Anyway, let us say.
Anyway,
let me see that there are some people, they have raised their hands. Baya Venkatesh.
Sure.
Baya Venkatesh.
Yes, sir. Yes, sir. Good morning, ma'am.
Mr. Please ask.
Ma'am, can I ask one doubt? The Greenwood statistics can be applied in quality control applications?
I'm not aware. I know that Greenwood statistic is used in engineering applications, but I'm not aware of quality control.
Okay. Okay, ma'am. Thank you.
You're welcome.
Any further questions? Yes, Professor J.S. Rao is opening his mic.
No, I just opened the mic, but that's all.
Okay, fine.
No, thanks.
Viswanathan?
Yeah, if time permits.
No, you are permitted. Only one question.
Thank you, Professor. Thank you, Professor. Madam, if you go through the definition of TNK, the statistic TNK you have defined, can I get that that flashed on the screen?
He wants to display.
Yeah, I know what you want.
The statistic TNK.
In the same way, you can share the screen.
Yes. You don't see it yet, right? Okay. Can you see now?
No, not yet.
You just need to wait because.
Okay, madam. I will, no issue. I will just, it's an observation or a comparison in the sense that in that statistics, if you put k is equal to 1, it's going to be something like simple difference that Professor Jamalamadaka was talking about. If I, yeah, exactly. So if I put k is equal to 1, it is something like the simple ordered difference that Professor Jamalamadaka was talking about. So it's my doubt in the sense that this T and K will become a special case of H, because this is also ordered difference. And Professor was giving a generalized function H of the observations. Okay, so in that case, can we take this T and K as a special case of your H that Professor Jamalamadaka was talking about? That is my observation. Is it possible?
You would have to ask Dr. J.
Okay,
because I don't know right now. I would have to look at the function H, at the conditions on the function H that he had.
Okay. Thank you, madam.
I think that, may I say that this is a fair observation, because it's a sum of squares here. Instead, you could do other functions, log and log, x log x, and there are various functions are possible, but you get different crazy statistics maybe.
Yeah, I mean, I actually wrote to myself to ask Dr. J for some references. So we'll see. Maybe this is an example. Maybe Greenwood statistic is also somewhat of an example of one of those non-parametric H functions.
Well, thank you, Professor Viswanathan, for your nice observation and interesting point. Thank you, Professor Anna Panavska, for delivering a nice job and having for your interaction with the participants. I thank also Professor Bindu for co-chairing this session with me, and I thank Professor Satish Kumar for giving me this opportunity to chair this session. And now I hand out the session to the Satish Kumar, the organizers, for conducting the further proceedings or further sessions. Thank you.
Thank you, sir. Thank you, madam. Very interesting talk. Thank you, madam.
Thank you all.
Professor Satish Kumar, your mic is muted.
Sorry. Thank you, Professor Anna Panavska, for your nice presentation, and surely it will be helpful to our youngsters. And Professor Loganathan to chair this session, and Professor Bindu, Dr. Bindu to support as a co-chair. Now, let us move to the next session. We have a great professor is waiting for the next session, Thomas Kusubowski. So, to chair this session, our Professor S.T. Malik is here, and Dr. Dilip.
Yes, sir, I am here.
Dr. Dilip is also here to support our chair. Dr. Dilip is a very energetic young researcher, active, and is in fact a faculty of our mathematics department presently, and a student of our Professor A. Mathai. And in this session is in fact for honoring our great professor in the area of statistics, Professor A. Mathai. So we dedicate this session to honor Professor A. Mathai, and I invite Dr. Dilip to introduce the introductory remarks and hand over to our SC Professor S.C. Malik to carry over the session. And we are all waiting to hear Professor Kusubowski. Thank you all. Thank you so much. Yeah, please.
Thank you very much, Satish sir, and the organizers, especially Riaz sir, for giving me an opportunity to co-chair this session. This session is in honor of the great mathematician or statistician, Dr. A. Mathai. Unfortunately, I was the student of him. And before going to the session, let us have a brief idea about a brief introduction about Professor Mathai. Professor Mathai was born in 1935 at Palai, Kerala, And after completing his schooling, he has completed his MSc from University of Kerala with first class, first rank and gold medal in 1959. And later he went to Canada to University of Toronto, where he completed his PhD in mathematics, and under the guidance of Wilmington. And he has been the founder of the Statistical Society of Canada, and he is a fellow of various academic societies, including the National Academy of Sciences and the Institute of Mathematical Statistics. And he has written a number of papers, more than 350 papers in international journals, and has published more than 30 books. And his main areas of research are applied statistics, special functions, and reaction rate theory in astrophysics. So I am very much fortunate to say a few words about my guide. And to chair this session, we have Professor S.C. Malik. S.C. Malik is the professor of in the Department of Statistics at MD University, Rohtak. His field of specialization are reliability theory, sampling, and applied statistics. He has been teaching so many subjects, including real analysis, measure theory, linear and nonlinear programming, complex analysis, probability theory, statistical methods, and stochastic processes. He has published a number of books in a field of real and complex analysis, and has published more than 175 papers to his credit. Up to now, he has supervised 35 PhDs and 24 MPhil students. And he has been, Professor Malik has been in various academic institutions and has delivered invited talks in many places, including USA, UK, Portugal, Singapore, Germany, and has been the founder of the president of the Indian Association for Reliability and Statistics, and also the chief editor of the journal IJSRE. He is an elected member of this section, Mathematical Sciences section of the Indian Science Congress also. He has been appointed as a UGC member of the advisory committee for SAP. So on behalf of all gathered here, I invite Professor S.C. Malik to chair this session. Professor Malik.
Yes, Dr. Dilip Kumar, thank you very much for giving a nice introduction in brief. Thank you very much for this. First, I am very grateful to Dr. Satish Kumar, Professor and Head Department of Statistics, who invited me to chair this session. And really, he is a very dynamic personality who is always ready to spare time to conduct such type of interactive programs in the form of conferences or webinar nowadays, webinar and international webinars. So I'm very grateful to all of you. Thank you very much for giving me the chance. Now, in this session is specifically focused on to remember the contribution of Professor A.M. Mathai. Special session in the honor of Professor Mathai. So in this session, we have very eminent professor, great professor, Tomasz J. Kozubowski, and he is going to speak in the area of multivariate models for trivariate events involving sums and maxima. So I have nothing to say more words about Thomas, because he's a well-known professor of statistics and has a lot of contribution towards research and teaching areas. So I request Professor Thomas to kindly share your views in this area. So I welcome you all. Thank you.
Thank you, Professor Malik, for your introduction. Thank you, Professor Satish Kumar and the organizing committee for this event, for this most kind invitation to present at these proceedings. Let me see if I can share my presentation here. So just click on present, right? Let's see if I will be successful. I have this presentation open there. hopefully
it is coming. Yeah.
Something is doing.
You have to open the presentation.
The presentation is open.
Go presentation.
Now you have to go to the presentation. Yeah, it's fine. It's
fine.
Oh, I have to go to my presentation. I see. Do you see it now?
Yes, okay.
Okay. It's always some technical difficulties at this events. I'm not actually used to this particular tool. We often lecture using the system called Zoom. This one is a little bit different. So just to make sure about the timing, do I understand correctly? There is about, what, half an hour for the presentation? How much time is there for this presentation?
Yes, you have 30 minutes. No problem, sir.
About 30 minutes. Okay, very good. So research is about multivariate models for these trivariate events that I will describe in just a second. This particular piece of work is based on our work with Professor Marek Arendarczyk from Poland and Anna Panorska. And then it also contains bits and pieces of other papers that we've collaborated with various individuals over the years. So thanks again for this kind invitation. There is also some acknowledgement here for some funding that this research has received over the years. So here's a brief outline of this presentations. Generally, we are focused on some extreme events that actually occur over time. So in with the in the area of climate, for example, we are now all used to this heat waves. Actually, there is a heat wave now going on in Reno for several days. The temperature is around 100 degrees, which may not be much in Kerala standard, but here in Reno it's really, really hot, and it makes it very uncomfortable. So events such as heat waves, drought, floods, and so forth can be handled by means of this methodology, where we're basically looking at events that occur one after another for a certain period of time. Okay, so I guess this picture, I'm just browsing through this, and I'm looking at my screen at this end, but I'm not sure if the audience sees the same thing. I hope so. So let me describe these events mathematically. So what we're looking for is there is some kind of threshold. That threshold could be, for example, the value of 0. And if the threshold is 0 and we observe observations taking on real values consecutively in discrete points in time, then generally there will be group of events like values that are basically consecutive values that are above the threshold. So here we're looking at this thing here, and then this is followed by the values of x that actually fall below the threshold, and so forth. So this splits this observations into groups of events, and essentially we can look at the positive events, starting at the first one here, where all the values of x were positive, followed by another event where the values of x were actually negative. And then at some point there will be a transition to the positive values and so forth. So these events are often characterized in terms of these 3 characteristics. So the very first characteristic is n, which is the duration of the event, and actually tells us how many values were there sticking above or below the threshold. Now, the second characteristic in the climate and hydrological literature is often referred to as the magnitude, while the third one is often called the peak value. So the magnitude is basically the sum of those values of x that are grouped together, while the peak value is the largest one of those. All right, and there are various strategies to handle the joint distribution of these three events. There is a huge literature on this topic, and people use different approximations for those distributions. Our goal here is to actually look at one particular case where one can get the exact distribution of this trivariate distribution that consists of the n, x, and the y. Okay, so that's our goal, is this trivariate distribution. We have the very natural representation of these variables in terms of these characteristics. So certainly we have the sum of those x's from 1 to n. We put this together with the same n, so that already makes them dependent. And there is, in addition to that, the third factor is the maximum value of those x. All right, so we're looking at the three random variables put together, n, x, and the y. All right, so in terms of the applications, and again, since we don't have perhaps enough time to cover all applications, I will focus maybe on financial applications where this threshold has a very, very simple interpretation. But here, that can be, this methodology can be applied to any such process. For example, one can look at the temperatures or precipitation exceeding certain values that could be, not necessarily values of 0, but some kind of high threshold. So I'm gonna move on with this, since I'd like to show a little bit of mathematics here. I will maybe move to those examples in finance. As far as heat waves, naturally we're talking about a threshold that oftentimes has to do with particular temperature, like over 30, 33 degrees in this case. And we may have several consecutive days of heat, right? I mean, this definition of heat waves, again, is very basic here, that we, looking at values, consecutive values that exceed the threshold, essentially, those values form this heat waves. But there are some other definition in the literature as well. So as we consider such an event, the basic question, that comes up is, how often these events come up, magnitude of those heat waves, how long they can last, what's the distribution of n, what's the distribution of the size, what's the, highest value within the heat waves, and so forth. All right, so there's a great interest in handling the distribution of those things. Now, I'm gonna move on with this other applications here in finance. This is something I will maybe focus on a little bit more. So in this application, we may be looking at a particular, maybe like in this case, we're looking at exchange rates, but it could be other things like values of the stock or other financial commodities. So we have a value, we have daily, for example, daily values we can look at. And then what we do is we look at the change, how much the value is changing from, say, day to day. So then the value of the stock, for example, or exchange rate can actually be moving up or down. And there will be days where the value is increasing in size, followed by days when the value is actually going down. So in financial mathematics, those things are often modeled by the so-called logarithmic returns, where you look at the ratio of two consecutive values, and then one takes the log of those, and then they make them either positive or negative. So if this logarithmic return is positive, that simply means that the ratio was more than 1 from day to day, so the value was actually going up, right? So we can study the number of days and the total return over the period of the growth, or we can do the same thing over the period of decline when all these logarithmic returns are actually less than 0, right? So in these financial applications, it's very natural to have a threshold of 0 and essentially study the periods of growth and the period of decline in the value. So this is an example we would focus on. So in this application, n is the length of the growth period, the summation of those x's, since these are logarithmic returns, that actually has a very natural interpretation of the log return over the period of the growth. And the y value is actually the maximum of those log returns over this period. So the peak of a threshold theory plays some role in this application as well, since we're looking at the values exceeding a threshold that may be large and look at the exceedances, then according to this extreme value theory, those distributions of these exceedances over high threshold essentially can be approximated by these 3 random variables that Professor Panorska was talking about, the generalized Pareto distributions, or in essence, these are either exponential Pareto or beta random variables. So it's natural in this application to actually take those x's to be, as an approximation to be one of those distributions. And the very basic model that one can put together that actually is quite manageable in terms of these distributions have to do with the exponential case. So this is where we will start. All right, so just to recap what I'm talking about, we start with the process driven by the values of x. We are then converting this process into those trivariate events consisting of the duration, the magnitude, and the peak value. Now, in reality, of course, those x's may actually be, and often are, dependent random variables, but it turns out that the approximations that one get from independent events actually approximate the data quite well. And also one can make extension of this to x's that are actually dependent. All right, so the basic model will assume independence among those x's and the same distribution, and then further extensions would allow for dependence among the x's, which is a more realistic assumption. All right, so essentially we're looking at this trivariate vector, and then it should also be pointed out that one important feature of this vector is that one of the components is actually discrete. So by its very nature, this n is a discrete random variable, and often in application, this n doesn't take a very large value. It could be 3 or 2 or maybe 10, not hundreds. So approximating this n by continuous, which is often done in applied work, is it doesn't really reflect the nature of this distribution. Okay, so we'd like to have a model that for this trivariate distribution, and we basically proceed first by considering a fixed n, And then by conditioning, we can get to this trivariate distribution. So the basic building block of models of this form is when one assumes that n is actually fixed. And the basic thing that one needs to get in order to produce such a model is the joint distribution of the sum and the max. All right. So this is the main difficulty here, is how to handle the max and the sum together in one model with the fixed n. So once this is taken under control and we have such a model for the sum and the max, then the extension to the trivariate distribution is quite simple by the standard conditioning arguments. So it should be mentioned that when one studies these distributions, then often it's helpful to use tools from extreme value theory, where one studies quantities such as the maxima of random variables, where the basic tool there is the distribution function. And then when studying the sums of random variables, the basic tool is either Laplace transforms or characteristic functions. And when we study them together, we often use like a mixed functions, where on one coordinate we use ideas for the characteristic function, and the other coordinate we may be using distribution functions. So some sort of hybrid functions that operate differently on x and y are often used in this area. All right, so I should mention these two models that will be described in this presentation. So first of all, we will focus on the case where the variable n is a geometric random variable that seems to work very well in these applications. We would also consider the cases where the x's in these models are exponential random variables. And in this case, we refer to this as the Tetlek model. That stands for the trivariate distribution with exponential, truncated logistic, and geometric margins. Okay, so it turns out that when you actually take a random sum of exponentials, that is another exponential with different scaling. So that's the marginal distribution of x is exponential, and is the geometric distribution, since that's the n that we use here. And then the maximum value can be worked out as well. It turns out to be a truncated logistic distribution. So then another extension that we will mention in addition to that is one where those x's are actually Pareto distributions. So the marginal distributions are Pareto, but they also have a joint distribution, the multivariate Pareto. So both of these constructions, again, they go back to this basic model with the fixed n, which is what we want to start with. I should also mention that there is quite a body of literature on the asymptotics of this. In fact, one can study the asymptotic distribution under proper normalization. What's the approximating distribution for the sum and the maximum of those same x or related x? And, under proper normalizations, the summation by itself may converge to a normal distribution for light tail random variables x, while the maximum of x would also converge under different normalization to this extreme value distribution that can be one of three types. And then one can also, using similar techniques with this hybrid characteristic distribution function, get the joint distribution in the scheme where one component is normal and the other is from extreme value. And for light tail distribution, those components actually turn out to be independent. While in real data, even with large values of n, when we look at the values of x and y, then we actually see them to be dependent. So this asymptotic distribution, is not always useful to approximate the distribution of the sum and the maximum, simply because it always stipulates that the values are independent in the limit, which is not necessarily the case in practice. So here are some basic information about the results for this exponential case, where several such constructions have appeared in the literature. So I already mentioned the Tetlec model based on geometric n and exponential x. There is also, this basic component with the fixed n, that is called BGGE distribution, that stands for bivariate with gamma and generalized exponential marginals. There is a back distribution that is just n together with the sum. There is another marginal distribution of n and y called BTLG distribution, and so forth. Okay, but let me start with the basic ingredient, which is the distribution of sum and the max for the fixed value of ed. So here are the details regarding this construction. So when looking at the values of the sum and the max, it's clear that the value of x, which is the sum, must be between y and n times y, or in other words, the maximum is always less or equal than the sum x and greater or equal than x divided by n. So that particular distribution for continuous x actually lives in this sector. The value of x and y needs to be below the diagonal y equals x, and above the line y equals x divided by n. Now, this region where the distribution is defined actually can be divided into these what we call sectors that go between the lines 1 over kx and 1 over k plus 1x. And in each and every one of those sectors, when k ranges from 1 to n minus 1, the form of the PDF is a little bit different. All right, so that's the basic formula for the joint PDF under exponentiality, which is one particular trackable model that one can get for this case. The estimation of parameters is fairly straightforward for this. Using maximum likelihood, one immediately gets the value of beta hat to be just n over the average of x. And then the standard properties of the estimators hold up as well. Now, when we replace this IID exponential with Pareto, which will have this multivariate Pareto distribution, that can also lead to a trackable model as well. And here, for the Pareto case, I should mention that, there are two parameters now, beta and alpha, and the distribution is put together in such a way where this alpha now, when this alpha becomes 0, then, which is one of the special case of the parameters, then this reduces to IID exponential. So this Pareto case is a natural extension of the exponential case, and exponential is a very special case of the heavy-tailed Pareto distribution. So for this multivariate Pareto, let me skip some slides here. We get, again, the joint distribution under similar conditions. We refer to this distribution as GSMP distribution, that stands for geometric sum and maximum of Pareto variables. And again, the main component consists of the distribution with the fixed n, where we have the sum and the maximum of those Pareto variables. All right. So again, one can get the exact joint distribution with the formula similar to the exponential case. What one can identify the marginal distribution of this construction. as well as the conditional distributions. So here are some details regarding those marginal characteristics of the distribution where the value of n is actually fixed. The PDF again is given inside those sectors with a little bit different form, depending on which sector the value of x and y is in. And when alpha converges to 0, we recover the previous distribution with exponential components. There is also a stochastic representation that aids in theoretical work with this distribution. That stochastic representation is actually quite meaningful and useful in deriving some properties of this distribution. So let me just say that one can actually look at a bunch of vectors that we call AI, where this I ranges from 1 to n. These are vectors with coordinates 1 and 1 divided by I, as presented on this graph here. And then what happens, we essentially take a multivariate Pareto distribution, y1, yn, with n components, and form the linear combination of those y's with these vectors A. So it's like a vector sum, along each direction A, we actually distributed this component yi, and then we take the vector sum of those vectors to get the point x and y. All right, so that's the stochastic representation of this construction. In the case of exponential distribution, then these y's would be IID exponential. So in summary about these properties of this model with heavy tail Pareto xi's, let me just make some general remarks. So the conditional distributions can be derived, and they have well-known expressions. The joint moments, the mean, the covariance, the correlations, and so forth, they're not always exist. That depends on the parameter alpha that need to fall in a certain range for these characteristics to be finite, but they can be calculated exactly for this distribution. We can also study the distributions of the ratios, so-called peak over sum or peak to average ratio. Again, is an important concept in certain areas that, here we can derive distribution for those things. The parameter estimation for the Pareto case is a little bit more tricky than exponential. Actually, you don't get exact form of the MLEs, but we can prove their existence in this case. Let me talk a little bit about this estimation. So when we use information from the random sample of size m from the distribution, so here we're talking about the distribution where the n is actually fixed, then based on the likelihood function, we can proceed with estimation. In order to maximize the function with respect to the parameter, actually we need to use numerical search, and then it turns out that the values of this alpha, the estimator, would always be either 0 or greater than 0. That's the range of the parameter here. For alpha equals 0, we get the case of exponentiality. And this estimation actually involves this Greenwood statistics that we saw in the previous presentation. So, whether the value of alpha hat is 0 or greater than 0 is closely related to that. So that's, one way that this Greenwood statistic actually comes up quite naturally in the problem of parameter estimation, and which is among the reasons why one can use it, or could use it effectively for testing hypothesis about the parameter alpha in these models. All right, so that is it's a close connection here with the Greenwood statistic and testing exponentiality versus Pareto distribution. So I will skip this further facts about the Greenwood statistic. We've seen it in the other presentation. Now in the more general model with actually a random value of n, the maximum likelihood estimation proceeds along similar lines. And another statistic comes up in the problem of estimation. Actually, that statistic called SM is also related to Greenwood statistics through the components right here, where it has to do with the x's and the n's through the Greenwood statistic, and there is some additional terms involved as well. And essentially, when this statistic is less than 0, we would conclude that the parameter alpha hat is actually 0, pointing towards the exponential case, and in that statistic is positive, then the estimate of alpha would always be greater than 0, indicating a heavy tail in the data. So now going to examples, let me show at least one. I know we may be short on time, so do we still have time, or how are we doing in this regard?
Yeah, 5 minutes, Professor.
We have at least 5 minutes.
Yeah, 5 minutes.
Thank you. So I managed to show an example.
Yeah. Sorry for the same.
So, all right. So these examples here, I mean, there's several of them. We may see maybe one or two. So we're talking about exchange rates. Now, these exchange rates are daily observations. And again, they are converted to these logarithmic returns, which could be either greater than 0 if the value is increasing from day to day, or in the values less than 0 when the values are actually decreasing in value. So all this data were converted to these episodes, right? So we essentially look at day by day, check whether the price is going up, and counting the value of n, how many days it's moving up. And then for all those cases, all those days, we look at the cumulative return, x, the sum of x's within the episode, along with the peak value, which is the largest one of those xi's. All right. So then the basic model based on exponentiality actually says that this x has exponential distribution and has geometric distribution, and the y value is this other truncated logistic distribution. All right. Now, of course, we don't feed marginal distribution. We feed the trivariate distribution to this data using maximum likelihood. And it's really surprising that this model that only has 2 parameters, there is only parameter of exponential and the parameter of geometric, the y value doesn't have any extra parameters. So the 2-parameter model actually captures the behavior of this data quite well. So we're looking at a bunch of graphs here. This graph over here represents the, I think it's looking at just those xi's, the building blocks of this model that were positive. And we're checking those xi's against exponentiality. So we're looking at the QQ plot, which is the standard graphical display to measure the goodness of fit. We also look at the histogram with the overlaid exponential curve. And of course, one can also do formal testing for exponentiality based on this data. And they all checked out, indicating a pretty good fit of exponentiality. Now, the graph on the right, on the other hand, shows the cumulative positive log returns. That is the value of x in the trivariate distribution. So these also pass, very well the requirement of exponentiality. In addition to that, of course, we also, check other marginal distribution. So we fit, check how geometric fares with the data. We use the check the fit of the marginal distribution of the y values versus the theoretical marginal distribution with estimated value. It should be pointed out, actually, that may not be very clear from the description on the slides, but it should be pointed out that when we do estimation for these models, then the y values actually don't play any role whatsoever in the estimation. So the estimators are indeed based solely on x's and n's, and y's don't play any part in estimation. So it's particularly interesting to see that even though the y values were not used at all in the process of estimation, the distribution of the y values actually fits remarkably well to the observed y values. Now, in addition to the marginals, we also look at the conditional distributions. So as I mentioned earlier, the conditional distributions of x given n or y given n or vice versa can be worked out theoretically, and then they can be compared with the data in this regard. And those conditional distributions actually fit quite well as well. So overall, the conclusion is that this simple trivariate distribution based on exponentiality actually fits these event data quite well. And we reach similar conclusions for other types of data, some financial data, climate data, all kinds of data were used to check these kinds of models. We use it on heat waves, we use it on precipitation, we use it on temperature data, flood data, and other types of data. And, in many cases, we obtained a very good fit of this, this particular methodology. So here, just briefly, we're looking at precipitation data. That's example number 4, where we use a more general model with Pareto components. And then again, we are looking at conditional distribution of x given n and y given n, theoretical versus sample data. And again, they are not perfect. As you can see, there's some, maybe slight issues with the fit, but overall, they don't fit badly, this data. Okay, so there are numerous examples illustrating this methodology. And lastly, let me mention that this, once you have the joint distribution of the sum and maxima in the context of finance, you actually can evaluate a certain important measures that otherwise are difficult to evaluate. And these, like standard measures are so-called tail conditional expectations, or TCEs, where we can use this, like expectation of x given that is greater than s, or y given that it's greater than s when you have bivariate distribution. But these measures don't require bivariate distributions. And with this methodology, we can actually look at these mixed measures of risk, where we can look at the expectation of x, provided that the other one is greater than a threshold, or the other way around, expectation of y given that x exceeds a threshold. So that would provide additional risk information in the context of like in financial applications. So far, without exact distributions of those things, only asymptotic results are available in the literature when the threshold T or S, goes to infinity.
Yes, Professor, we have some time limit. Please.
Yes. Oh, we have time limits, so I'm skipping through this. I don't have time to present everything, but let me just finish by saying what we've done here. We've presented results for this trivariate distributions. We try to argue that these are useful objects, for applications, and there are many further extensions that are possible with this. I didn't mention all of these things, but there's further things one can do with this methodology. All right. So thank you very much for your attention. Here we have the finishing slide showing the extremes in Nevada that ranges, 120 degrees Fahrenheit in the desert near Reno to a beautiful waters in Lake Tahoe, which is, hot. And, we get snow in winter as well. So, reference related. So thank you very much again for this opportunity to speak in this session, and let me finish with that.
Yes, Professor. Yes, wonderful presentation in this area. Or really, you demonstrated good applications, in particular in finance area. Do you have some idea about the application of this work in COVID-19 pandemic situation?
Oh, for the COVID, that's a very interesting question. I actually didn't think of that. I wonder how one might use this methodology, perhaps look at days where the COVID cases are increasing or decreasing maybe, and looking, like the rate of basically the daily cases of COVID are going up.
Yeah.
There will be, but where the daily cases of COVID are going.
Yeah. And nowadays we are facing different waves also. First wave and second wave. Hope for the next.
Interesting idea to apply this to COVID. Maybe that's something one can look at.
Yeah. So, any other questions from the part of the audience, or yes, any question? Yes, Vishwanathan, you want to speak? Yeah.
Sir, can you hear me?
Yeah, yes.
Professor, with the given structure, can you predict when the next peak is going to occur in case of financial data?
No.
Is it possible?
That's that may not be possible. I mean, so far this methodology has been developed just to model the distribution of those events. The goal was not one for predicting the next peak. Maybe it's possible to handle this, but at this point have any very interesting question.
I think you have mentioned it for the regression setting. So in that case, is it possible to predict?
Can you please repeat this question? I didn't hear that.
I think you have cited some papers. So whether this has been extended to the regression problems.
Yes, there is a problem. This regression problem, though, is not going from one event to another event. This regression problem is about linking the parameters of the distribution. So in this sense, once you have a model in the regression setting, parameters linked to covariates, then you actually make some sort of prediction based on covariates, where you can actually calculate probabilities more precise than from the IID model. So you are right, it's possible to make some kind of predictions from the regression.
Just to add one more thing, instead of introducing a regression model with time variable as a separate parameter, is it possible that we increase the component by one more parameter by introducing t, time component, instead of 3, x, y, and that is sum and maximum with n. So if you are able to introduce a time component t as a 4-variate model,
4 variables, yeah.
Then possibly I think that will be addressed.
That's right. So some of these models can naturally be extended to stochastic processes where T is another component. And that particularly refers to the case where you don't have the maximum. It's difficult to incorporate both the maximum and the sum into such a stochastic process, but when you don't include the maximum, just the sum and the size of the event, the n, then these have been extended to stochastic process parameter t. So, for example, you can have an analog of Brownian motion or process, the Levy process with additional parameter t.
Okay, so I think, Professor, you nicely give the ideas for final application, and some other areas we will try, and the audience will try to search out some other applications in this area by considering the 4th variable also. There is a time variable.
Yeah, thank you.
So thank you very much for nice talk. Is there any? So over to Dr. Dilip Kumar.
So thank you very much, Professor Kusbowski, for your nice talk. And thank you, Professor Malik, for chairing this session.
Thank you.
And those who have any further questions, they can discuss later with Professor Kusbowski. And I think the session is over, and now I request Professor Satish sir to take over the session to the next.
Thank you, Professor Kusbowski, for your wonderful talk. Surely it will illuminate several researches, both in theoretical and application areas. And also, we would like to extend our gratitude to our Professor Malik for chairing this session in a nice way.
Thank you, Professor.
And Dr. Dilip too. Also, we are thankful to Dilip for supporting Professor Malik as co-chair.
Yeah, nice.
Thank you, sir. Thank you.
Thank you all. Now, let us move to the next session. I think it is a special invited session organized by Professor R.L. Shinde. And so R.L. Shinde and his team will be ready to. Yeah. This session is will be chaired by our beloved professor from Kusat, S.M. Sunoj. Professor Sunoj is, in fact, very busy presently, mainly due to his activities, administrative responsibility, especially as a syndicate member there in the Kusat. And also, he is a very active researcher. And I'm not extending too much about him for the time being, because everything available in the online. And Professor Sunoj, kindly proceed the session in a nice way, as you like.
Okay, thank you, Satish sir. As mentioned, this is a special invited session organized by Professor R.L. Shinde. So this session is on statistical process control and process capability analysis. I think apart from Professor Shinde, 2 more speakers are here. So I hope all the speakers are present now. Yeah, okay. So this session, yes, like the other session, we have 1.5 hours time. 10 was scheduled from 11:30 to 1 p.m. So now it is 11:40 p.m. So it can be extended up to 1:10 p.m. So I request, so I think one more co-chair is here in this session, Dr. Vichana. So I, without introducing much about the topic, I hand over this speaker to mic to Professor Shinde to because he being the organizer of the session, I think he can introduce much about the session. So please, Professor Shinde. So please restrict your talk half an hour time. So I think we can have 25 minutes time, and 5 minutes can be allowed for the discussion on each talk. So please.
Thank you, Professor, for introduction. So, first of all, I would like to thanks to our organizer, Chairman Professor Satish Kumar, for giving us an opportunity to present our work in this particular session. In fact, this seems to be only session on the process capability and control charts. So, I have got two more speakers with me in this session. They will speak afterwards. So I will start my presentation. Can you see my screen?
It's coming.
Yeah, it is.
Now it is okay.
Okay. So thank you, Professor. So this is my talk is on the multivariate process capability indices. This is the joint work with one of my PhD student who completed PhD, KG Khadse from one of the college at Jalgaon Autonomous College. So my content of this session lecture is process capability, then objectives of process capability indices, and basic process capability indices for univariate processes. Because in order to go for the multivariate processes, we first need the basic capability indices in order to motivate about the multivariate process capability indices. Then we talk about the third generation process capability index in univariate setup and its extension for the multivariate setup. Then process capability indices for non-normal processes for univariate setup given in the literature, and then we'll discuss about the multivariate process capability index for non-normal processes with example. So process capability is refers to performance of the process when it is operating in statistical control. Control charts and histogram are graphical tools can be used for judging the process capability sometime. Objectives of process capability indices. Basically to compare the process performance with the specification. This is one of the major objectives. Process dispersion with the amount of dispersion allowed. This is what we compare. Compare different processes, unitless measure sometime. So provide information about the processes in regard with the proportion non-conforming or proportion conforming product. Closeness to target also, we talk about the Taguchi's approach of quality loss. To provide direction for the quality improvement, this is also objective for the process capability indices. To choose the endpoint of the process mean in order to minimize the proportion of non-conforming product, that is also objective. So what are the basic capability indices in the invariant processes? So the process capability represent the performance of the stable process. Stable process means it has a quality characteristic distribution is stable. Original motivation underlying the introduction of PCI is to monitor the proportion of non-conforming, in fact. Kane 1986 and Kern 1992 papers one can refer. Kane 1986 gave the useful discussion on the comparisons of these basic PCIs. Basic PCIs are defined under the assumption of processes under statistical control. The tolerance is specified by lower specification and upper specification limit with target as the midpoint of the specification limit, and the quality characteristic X follows normal distribution. Normal processes in which first PCR, first process capability index is CP, which is also known as PCR, process capability ratio. So PCR is greater than 1 when the length of specification is greater than length of natural tolerance limits in invariant setup we are talking about. When process is really capable, the situation where the specification limit length and natural tolerance limits are matching, then the process is just capable, and when the length of specification is lesser than the length of natural tolerance limits. Natural tolerance limits are mu minus 3 sigma and mu plus 3 sigma. The length is 6 sigma. So in that case, process is not capable. This is based on the potential capability CP. It is a very basic measure. And then due to the inherent inability of CP to consider process mean and target, several indices have been proposed in the literature later on by considering the mean and target. For example, most useful indices in industry, CPK and CPM, they are being used. CPK is minimum of USL minus mu upon 6 sigma, and this one. It measures the actual capability of the process by considering mean and sigma both together. And third index, CPM, which is based on the loss function approach. So where USL minus LSL upon 6, instead of 6 sigma, we have here 6 tau, where tau square, where variability is measured from the target. If mu process mean is at the target, then CP and CPK and CPK, all three will become same. Then probability based indices in univariate setup. In order to introduce these indices, we need some probabilities. P1 is the probability that the quality characteristic lies in the specification limits, provided mean is kept at target and variance is natural variability sigma square in that process. So P lower is like this, P upper is defined like this, mu2 upper specification, mu and sigma square natural variability, and mu is considered. P is 2 times minimum of P lower and P upper. P, and P2 is actual proportion of conforming by keeping mu and sigma as it is. This is X lies in specification limits, this probability proportion. So this is actual proportion of conforming, and P1 can be called as a potential proportion of conforming. The process has potential up to this if you shift your mean to target, and this is actual proportion of conforming. And P3, which talks about the same probability by keeping mu at target and sigma square at sigma square t, measuring variability from the target. So once you define these probabilities or proportions, you can now define the CP, CPL, CPU, CPK, and CPM. Alternative definitions for these can be given in terms of probabilities by using these probabilities. Those are CP, P1 is minus 1 by 3 phi inverse of 1 minus P1 by 2. This way, CPL based on P lower we can define in this fashion. CP UCPKP, where P is 2 times P lower and P upper, minimum of P lower and P upper 2 times. And CPK P2, please note this P2 is the actual proportion of conforming in the process, while keeping mu at mean and variance sigma square. And this is based on the considering the target. So all these indices, the originally defined indices, CP, CPL, CPU, CPK, and CPM. So this result is we have given in the third science in the 2009 Communication in Statistics paper. These all indices are equivalent. So one note is there, CPK and CPK P2 are not equivalent. For example, if you consider two processes, A and B, with mean 50 and sigma 5, and another process 48 and 4.5, CPK comes out to be 0.8, CPK P. Please note that P is nothing but 2 times P lower, minimum of P lower and P upper. 2 times minimum of P lower and P upper. And P2 is actual proportion of conforming in the process. So all three are matching here, but in process B, which has larger proportion of conforming product, it should be reflected in the index. So this index CPK P2, which reflects, whereas these two indices CPK and CPKP, they are always same. So CPK and CPK P2 are not same. That is what it is demonstrated here. This is a better index which takes care of proper proportion of conforming. So P1 measures the potential capability, P2 measures the actual capability, and P3 relative to P1 direct measure how your process is operating off target. That can be measured through the difference between P2 and P1 that will reflect. In practice, we appeal to practitioners to use P1, P2, P3 itself as a capability indices. But many people are still in industry, their familiar users are still friendly with the CP, CPK and CPM, and they don't want to move to directly probabilities. So for that purpose, we suggest that CP, P1, CPK, P2, CPM, P3 can also be used as indices which are based on these probabilities. Multivariate process capability indices. Generally, multivariate process capability indices are really univariate indices. They are univariate in nature. They are not multivariate. So only few, one or two in literature, they have vector valued indices. Those are Shahrari 1995 and Bowen 1997. Their indices are vector value. Specification region consider in the multivariate process capability indices. Generally, most of the literature or industries, they talk about the hyperrectangular region, because ellipsoid region and other complicated region, it's require much knowledge of engineering design. If design engineer is more familiar with this type of situation with some mathematical constraints on the quality characteristic, then only while giving the specification region, ellipsoid or other complicated region may be given. Otherwise, most of the situation, hyperrectangular region is specified. Notation CP, instead of CPU, now onwards MCP we have for potential capability in multivariate setup. MCPK, actual capability, it measures, any MCPM which measures the capability index based on loss function. First one takes care of variability only. Second will take care of mean vector as well as variance covariance matrix. And third one is based on the variance covariance matrix measured from the T. Some multivariate process capability indices some authors have proposed alternative methods of multivariate process capability indices. In general, MPCI constructed using ratio of tolerance region and process region, probability of non-conforming product or conforming product, principal component analysis, and other approaches. In literature, the modified tolerance region concept is used for introducing multivariate process capability index, first time introduced by TAM in 1993, Bound 2001. These two papers where the tolerance region was modified and then the index was defined. February 1995, here the process region was modified according to the tolerance region. MPCI is based on the probability approach. Then first time mentioned that probability itself can be considered. He has just introduced in this paper as a index. We also have some articles in this area for probability based indices. MPCI based on the window of opportunity, one paper is there. MPCI based on the relative importance of quality characteristic. We had one paper in this area by giving the unequal importance to quality characteristic. MPCI is based on the principal component analysis. These are articles in this area. In the Wang's paper, these three papers, they have used the Wang's paper also. The specification region obtained for the principal component was not correct, that we have pointed out, and later the theory changed accordingly. The MPCI for non-normal situation, these are the papers with different objectives people have considered, and they have given their limitations also. We have one recently published paper in IAPQR. I forgot to mention here. I have mentioned in this set. This is this one, which is based on principal component as well as the non-normal situation. Another paper we have. Comparison of MPCIs is done by different authors. These are some articles. What are the multivariate process capability indices based on the probability approach? We have just extended the probability approach from univariate to multivariate in this similar direction, where process is statistical control and multivariate normal data if we have, and the specification is such that the target is at the center of the specification. And P1, which talks about probability that the X lies in specification, where mean is at target and sigma as it is. And P2 is actual conformance it measures. This is potential conforming probability. This is actual conforming probability. And P3, which takes care of, which measures the variability from the target, mu at target, and sigma is at sigma t, where sigma t is like this. So using this P1, P2, P3, these indices are defined, and these indices that measures the potential capability and actual capability. So the last one, CP, MCP P3, that and MCP P1 able to distinguish the off-centered process. How process is off-centered, that can be observed by a relative comparison of these two. The third generation index in univariate setup itself, it is CPK, CPMK, given by Parn in 1992, which incorporates the merits of CP, CPK, and CPM, all three, and it is defined in this manner by extending CPK, which takes care of CPM as well as CPK also in the definition if you see carefully. Then we define P lower as probability that X lies in lower specification to mu, and P upper is X lies in mu to upper specification. And if you define CPMK P based on P in this manner, this is going to be alternative definition for CPMK, this one. In fact, the equivalence can be established by in these two indices, probability based index and this originally given index. Later on, we wanted to develop the multivariate set of index on this. For that purpose, SPK and SPMK as introduced in the literature by Boyles. CP and CPK, if you have the corresponding proportion of conforming, exact proportion of conforming, you can obtain. Only by CPK you cannot obtain, but if you know CP and CPK both, this relation you can use from Ford and Johnson 1993. And SPK is given, Boyles 1994 developed the yield index SPK, which interpreted as the smooth version of CPK. He introduced this smooth version of CPK in this fashion. And this can be alternatively, later on we have given the another index based on P, where P is the actual proportion of conforming. If you use like this, these two are same. These two are same. And another way of expressing this index CPK P is 1 by 3 instead of minus 1 by 3. 1 by 3 phi inverse 1 plus P by, due to symmetry of normal distribution. And Khadse and Shinde in 2009 claimed that this Boyles index and our index, they are almost, even though their forms looks different, they are same. Their equivalence was established there. And Boyles 1994 has given the smooth version of SPM, smooth version of CPMK in this fashion. This now we are by keeping extension of this index in multivariate setup. So far we are talking about univariate setup. In order to extend it, it cannot be extendable directly to multivariate setup. But our approach, both are same. If you express this way, P star is equal to proportion of conforming when using sigma square by replacing sigma square by sigma square T, and then take this SPMK P star. Their equivalence can be established, and this their extension to multivariate indices is given here. Again under the multivariate normality setup and all those things under assumptions. MCPKP, this is actual capability index, and the another one is MSPMK P star index, this one. So these two indices we have given as multivariate indices, and their comparison can be done. These two indices are same when mu is equal to T, and this MSPMK P star is less than this one whenever the process shifts from the target. In order to estimate the two multivariate indices, you can use your multivariate estimation procedure, where P star hat is this is estimated probability of X belongs to the specification region. If you have summarized data instead of complete data, sigma hat T will be obtained by sigma hat plus D, where D is like this. One real life situation example, we have taken data on the quality characteristic. X1 is the length in millimeter, and x2 is the inner diameter in millimeter, and x3 is the depth in millimeter. This is automobile product throttle valve, which is used in the carburetor of the vehicle regularly. This is these are three important characteristics of this product, and their specification region and the target values are specified. This data is taken from the automobile industry. 24 observations we had, and we had mean vector and sigma vector is like this. Accordingly, sigma hat t, you can get sigma hat plus d by adding d over there. This is sigma hat t, and it comes out to be the proportion of conforming under this sigma we replace by sigma hat t is like this. This is the index, third generation index multivariate setup, under multivariate setup. This value is this one. If you look at the ISPKP, it will be definitely higher than this one. And if there is a significant difference, you can see that there is a need of maintaining the target. So there is a need to set up the process vector target at the target in order to improve the process. Performance of this index, what we have given just now example, is studied under the different probability setup of the distributional properties. Here we have considered the mean vector, multivariate normal with mean vector and this sigma under different row values 0, 0.3, 0.5 and 0.7. And these are four scenarios we have considered. Under all these four scenarios, we have conducted the simulation study for different sample sizes 100, 200, 500 and 2000. Generally, we can expect sample size 100. Yeah, under these scenarios, we can observe that the true values of these indices for given parameter values, we have obtained the true values, and these are simulation studies results. These are this estimator of this is bias estimator here. It's not unbiased estimator. In all scenarios, we observed in the similar way. And some concluding remarks on these indices are this particular index of third generation multivariate setup index. Simulation study reflect that natural index of this is not unbiased. It is not unbiased, and it is negatively biased. And all confidence interval percentage, 95% confidence interval, they capture the true values of this index. Now, process capability indices for non-normal data. These are univariate setup capability indices available in the literature. Tang and 1999 suggested the transformations for non-normal to normal. There are many situations where the non-normality can be observed in real life. There are industrial environment, non-normal data sets are really observed, and they have one-sided specification also most of the time. Another capability index, CPQ and CPKQ, they are also being used in the industry. This is another capability index based on the PL and PU probabilities. According to Tang and 1999, transformation method is better most of the situation, and Box-Cox transformation they have suggested, noted that the Box-Cox transformation is consistently superior for performance throughout. We have suggested here probability-based MPCI for multivariate non-normal situation. First case is independent exercise, and second case is dependent, which is based on the principal component analysis. The first one, when you have independent.
Please adjust your time.
Yeah, 2 minutes, sir. 2
Yeah.
minutes. So So P1 is probability P11, P12, PM1. These probabilities are nothing but the probabilities of exercise lies in specification. So as they are independent, the product we are looking for P1 for the P1 like this and P2 this, for P21 to P22 in this manner. So you can define MCP based on P1, which measures potential capability. See, while P1, all components are lies between lower and upper specification, with process mean is centered at the target value. And in second case, where process mean is naturally you have taken. So MCP P1 and MCP P2, these are two potential capability and actual capability measures where exercise are independent. We have again got the brake system manufacturing data, trivalent bonding process data, where X1, X2, X3 are the bonding strength at room temperature 200 degrees Celsius and 300 degrees Celsius. Naturally, as this is destructive test, we assume that X1, X2, X3 are independent. And these observations, mu hat and sigma hat, rho hat are like this. An estimate of this process capability index comes out to be product of this first of all, and then by using MCPK P2, directly we have obtained MCPK P2 1 point, which is greater than 1. This is the really capable process. Second case, we have to use the PCI, principal component analysis. Here we have to use non-normal data we have, and mean is mu and median is m. By taking the transformation from X to Z, while talking about potential capability index for non-normal, transform data from X to Z. Z is xi plus di, where di's are ti minus mi, median. These are ti's are target values, and subtract median. And after getting this principal components on the transform data, you have to identify some k principal components with 90% process variability. Those are to be identified, and their specification region, this has to be noted properly. And their computation based on the simulation technique we have given here. We have to take around 5,000 samples from sample of 5,000 from this identified distributions of the principal components. We have to identify a distribution identification tool we have to use, and then P1 hat we get. Similarly, you can define MCP based on P1 by replacing P1 by P1 hat. So actual capability, you don't have to transform data from X to Z data. You can directly deal with your data and get the principal component and their specification region. Accordingly, you get. We have suggested here simulation technique and getting the estimate of MCPK P2. One example data from the literature only. This is historical air scrub data on 10 variable data, and their specification and target values are given. For this, we have given the complete analysis for principal component analysis, their eigenvalues, and their distributions comes out to be beta, Laplace, and beta for first 5 out principal components. And based on their region, specification region, this is the capability index value 0.79 as actual capability index, and for potential capability index point, there is no much difference. So one has to concentrate on the reduction of variability also, and particularly we have identified the second variable's variability has to be reduced in this case. So I will summarize here. These are some references. Thank you for your attention. If you have any question or query, you can ask.
Please, the platform is now open for some quick questions. There are, please. Shanadhan, please.
Yeah. Professor, this is regarding the principal component structure. Okay, see, normally when you deal with principal component structure, we have independence. That is, the three components will be normally extracted using the concept of independence. In that case, instead of doing a multivariate analysis, can we not do away with three independent univariate cases? Are they equivalent?
No, that is done later on. No, first of all, your original data is dependent, and later you got the independent principal components. And by using those distribution identified on those principal components, you can talk about. We have suggested the simulation study in order to give the probabilities, estimate the probabilities, and then probability-based indices. But you cannot use that technique on the original data.
No, I am asking about only the transformed data, because the original data is done away with, and we are we are in the transformed space. In the transformed space, okay, instead of carrying it out multivariate, you can carry it with three univariates. So that is my doubt.
No, problem is that the complicated region, the specification region is not that much easy. As Wang made a mistake in 1998, and that he straightforward transformed the specification region, and that was wrong. That we have pointed out in our 2009 paper also.
Okay, thank you, Professor.
Okay, thank you, Professor Shinta, for the very informative talk. So let me invite the next speaker. Next speaker is Shashi Bhushan B. Mahadev. He will be talking on SPRT control charts. So over to Shashi Bhushan.
Yeah. Okay, thank you, sir. Professor Sunoj, can you see my presentation?
Yes.
Okay. Good afternoon, everybody. At the outset, I would like to thank organizers of this international webinar, and especially organizer of this session, Professor R.L. Shinde, for providing me opportunity to present my work. Right now,
Sir, you make it full screen.
Full screen, sir, it is not possible for me right now.
Okay.
Is it readable?
Readable, but it captures only a portion of the screen.
Yeah, that can be done. So, I'm fortunate enough right now in Google Meet, we have 52 participants. Apart from that, there will be many more on YouTube. Nowadays, it is very rare to get such huge audience. So thanks to the audience also. Coming to my talk, I will be presenting the SPRT control charts. SPRT control charts are relatively new as compared to the other control charts such as Shehart control chart, Kusum chart, EWMA chart, etc. So whatever research work I will present in this talk, it is a joint work done by me with one of my research scholar, Mr. D.G. Godse, and one more collaborator is there, A.C. Rakitsis from University of AGM. Plan of my presentation is somewhat like this. In the first half of my talk, I will introduce the concept, explain mechanisms of SPRT control charts, talk about the statistical performance measures provide some remarks. And in second half, I will talk about asperity control charts for Maxwell distribution, and I will end my talk with conclusions. So, as you know, shared control charts are effective online process control technique used to detect out of control state of process. They are highly efficient in detecting large process shifts. However, relatively they are less efficient in detecting small process shift. So when we are interested in detecting small process shift, alternative to shared control charts are Kusum and EWMA control charts. They are more efficient than shared chart for detecting small process shift. However, they are less efficient than shared control charts for detecting the large shifts. So when one is interested in detecting shift of any size ranging from small shifts to large shifts, asperity control charts are effective alternatives to Shehart and Kusum charts. That is, they are more efficient than Shehart as well as Kusum and EWMA charts for detecting shift of any size. So, asperity charts are particularly appropriate to use in the following situations. The observations can be taken sequentially one at a time with the possibility of decision about the process after each observation. When testing is destructive or expensive, or when shift of any size is expected to be detected as efficiently as possible. For example, consider manufacturing process of automobile airbags. Here, important quality characteristic is the air pressure or the deployment pressure rate of automobile airbag, and that is tested in an air tank with sensors. At a time, only one bag can be tested. Testing is expensive as well as destructive, and departure of the deployment rate from its target value of any size is expected to be detected as efficiently as possible. One more example I would like to quote: manufacturing process of plastic eyeglass lenses. Here, important quality characteristic is durability of eyeglass lenses. In this case also, testing is expensive as well as it is destructive, and any departure in the durability of air glass lenses from its target value is expected to detect as efficiently as possible. So, relatively very few work has been done in this area. Stombos and Reynolds are the pioneers of asperity control charts. They have proposed asperity charts for mean of normally distributed processes. Further, they also propose asperity chart for proportion. Howe and others extended work of Reynolds and Stombos, and they optimized design parameters of asperity charts for normally distributed process. Recently, Wsta and myself proposed asperity charts for dispersion of normally distributed processes. So almost all work in the current literature deal with one-sided asperity charts. Further, most of the work has been done for normally distributed processes only. And general conclusion of the research on asperity control chart is like this: an asperity chart is significantly more efficient than Shehart and Kusum charts for detecting shift of any size. So basically, as I told you, asperity charts are one-sided charts, and that's why they have been compared only with Kusum chart and Shehart chart. They have not been compared with EWMA charts. So extension of one-sided asperity charts to two-sided asperity chart is a non-trivial task. This has also been mentioned by Stombos and Reynolds. So we have took this query, and recently we have developed a two-sided asperity charts for mean of normally distributed process, and also two-sided asperity charts for dispersion of normally distributed process. So obviously charts are based on Walsh asperity. Everyone knows what is Walsh asperity. Briefly, I will revise here. Let fx mu be the PDF of random variable x. Consider testing the null hypothesis mu is equal to mu naught against the alternative one mu is equal to mu 1, where mu1 is mu naught plus delta 1, or we can consider mu1 as delta 1 into mu naught. That is, we can consider either additive shift or multiplicative shift. So for testing this hypothesis, observations x1, x2, xn on x are taken sequentially one at a time. After taking ith sequential observation, one has to compute this test statistic, which can be computed recursively. For example, in case of normal distribution, suppose we have to test mu is equal to mu naught, and mu is mean of this distribution, and in this case that statistics takes this form: Sj is equal to Sj minus 1 plus Xj minus gamma, where gamma is mu naught plus delta 1 by 2 into sigma. So after taking every sequential observation, we have to compute this particular statistics. If this statistics is smaller than b, where b is some constant, we have to stop the sampling and accept H0. If it is greater than a, where a is some constant, we have to stop the sampling and reject H0. If it is in between b and a, the test is inconclusive, and we have to take next observation xi plus 1, and we have to repeat the procedure. The stopping bounds b and a are determined such that the test has desired strength. The world provided approximate expressions for b and a like this: b is equal to log of beta divided by 1 minus alpha, where alpha and beta are type 1 and type 2 errors, and a is equal to log of 1 minus beta divided by alpha. Performance measure of SPRT are operating characteristic, which is probability of accepting H0 when mu is equal to mu plus delta, and average sample number, that is expected number of observations required to terminate the SPRT when mu is equal to mu plus delta. World also have provided approximate expressions for OC and ASN. The exact values of OC and ASN can be computed using Markov chain approach or integral equation approach. So with this brief about SPRT, we shall now move to mechanism of SPRT chart. As I told you, basically SPRT charts are one-sided charts. So let X be the quality characteristic having PDF fx mu. Suppose the parameter mu is to be monitored at mu naught. Assume that occurrence of assignable cause generates a sustained shift in mu. So at each sampling instance, observation on X are taken sequentially one at a time, and the SPRT of null hypothesis H0 mu is equal to mu naught against H1 mu is equal to mu naught plus delta 1 is applied by appropriately choosing delta 1. Now how to choose this delta 1, I will explain later on. The quantity delta 1 is the design parameter of the chart and is referred to as design shift. If the SPRT accepts H0, the process is declared to be in control, otherwise it is treated to be out of control. So this is pictorial representation of SPRT. I have shown here two sampling instances. At the first sampling instances, this is first sampling, first sequential observation. It has fallen in between the bounds A and B, so immediately we have to take next sequential observation. It has also fallen in between A and B like this. The fourth sequential observation has fallen below B, indicating that process is in control. So at this sampling instance, we will stop sampling, and at next sampling instance, which will be after say 1 hour, we will repeat the same procedure. The appropriate statistical performance measures for SPRT control chart are: the first one is ANSS, that is average number of samples to signal, which is referred to as ARL traditionally, which is expected number of samples following occurrence of an assignable cause until signal. Expression for ANSS is like this: 1/1 minus OC delta. Clearly in SPRT charts, sample size is not fixed, it is variable. So one more performance measure required is ANOS, which is average number of observations to signal, and which is the expected number of observations following an assignable cause until signal. Expression for this is ANOS is equal to ANSS into ASN. Some remarks about asperity charts. So asperity is the best hypothesis testing procedure in certain sense. However, even a small departure from assumed model can have serious damaging effects on properties of asperity. Therefore, the asperity charts are not robust. That is, if the actual process distribution is even slightly different from assumed one, then those charts can give misleading results. Hence, the asperity charts based on assumption of normality of process cannot be used for monitoring non-normal processes. However, in practice, there exist several situations wherein a non-normal model describes a process more appropriately. For example, one such model is Maxwell distribution. So distribution has important applications in physical and chemical sciences. It is an appropriate model for physical quantities of molecules such as velocity and momentum. Also, distribution has applications in reliability and life testing. Distribution has single parameter and it is scale parameter. We have proposed asperity charts for monitoring this parameter. So this is PDF of Maxwell distribution. It has only single parameter, which is scale parameter, which is denoted here by sigma. And this graph shows probability density function. It is skewed distribution. So for asperity of H naught, sigma is equal to sigma naught against sigma is equal to delta 1 sigma naught. We have considered here multiplicative shift as sigma is scale parameter. So asperity for detecting increase delta 1 greater than 1 means increase in sigma naught. Test statistic for this asperity is as given in equation 4. If it falls below its lower bound, we have to accept H naught. If it falls above upper bound, we have to reject H naught. If it falls in between, we have to take next sequential observation and continue the procedure. Similarly, this is test statistic for detecting decrease in the value of the scale parameter. So based on these two asperities, we have proposed upper and lower asperity charts for detecting upward and downward shifts respectively. So the upper one-sided asperity chart. Let X be Maxwell distributed quality characteristic whose scale parameter sigma is to be monitored for upward shifts. Let sigma naught be the target value of sigma. Suppose an assignable cause shifts sigma from sigma naught to delta sigma naught, where delta is greater than 1. Control procedure is like this. At each sampling instance, observation on X are taken sequentially one at a time. The asperity of H naught sigma is equal to sigma naught against sigma is equal to delta 1 sigma naught applied by appropriately choosing design shift delta 1. If asperity accepts H naught, the process is treated to be in control, otherwise it is treated to be out of control. Similarly, we can propose the mechanism of lower one-sided chart. It is based on asperity of H naught against H1 prime sigma is equal to delta 1 sigma, where delta 1 is in between 0 and 1. So now I will come to the discussion regarding optimal choice of design shift delta 1. Statistical performance of an asperity chart for detecting a shift of any size depends on choice of its design shift delta 1. Now suppose delta prime is the size of shift that is desired to detect as efficiently as possible. Our numerical computations of statistical performance measures showed that the choice of design shift delta 1 to optimize performance of chart for detecting the shift delta prime is equal to delta 1 is equal to 1 plus delta prime divided by 2. For example, in case of upward one-sided chart, if we are interested in detecting shift of size 1.4, then the optimal choice of delta 1 is 1 plus 1.4 divided by 2, that is 1.2. Similarly, in case of lower one-sided chart, if suppose we are interested in detecting shift of size 0.7, then optimal choice for delta 1 is 1 plus 0.7 divided by 2, that is 0.85. So based on these observations, we have proposed design approach for one-sided disparity chart like this. With this design approach, we can propose chart having specified in control performance and optimal out of control performance, which is optimized for detecting shift of size delta prime. So for this, we have to choose design shift delta 1 is equal to 1 plus delta prime divided by 2. We have to compute this gamma, which can be referred to as reference value of this chart, and which is one of the quantity in control statistic. Next, we have to specify ANSS1 and ASN1, that is in control values of ANSS and ASN. Find alpha using this expression 1 minus alpha is equal to 1 divided by ANSS1. Alpha is type 1 error, and we have to find type 2 error using expression 6 and 7. Expression 6 is for upward one-sided chart, while expression 7 is for downward lower one-sided chart. So in case of upper one-sided disparity chart, compute bounds GU and HU. These are the bounds for control statistic using expressions 8 and 9. So these are actually approximate bounds which are obtained using the formulae given by Waltz, and these are to be corrected to achieve actual strength alpha and beta, and the bounds can be adjusted by trial and error to achieve the required strength of the test. Similarly, these are the bounds for lower one-sided chart. So using Markov-Chain approach, we have computed performance measures of this chart, and we have evaluated performance of the proposed chart with Shihart and Kusum charts. In first figure, these are the plots corresponding to the ANSS of Shihart, Kusum and SPRT charts of upper one-sided chart. So this curve corresponds to Shihart chart, second one corresponds to Kusum chart, and last one corresponds to SPRT chart. So from this figure, it is clear that performance of SPRT chart is significantly superior than Shihart and Kusum charts for detecting shift of any size. And second graph is for another performance measure, ANOS. So here we can see that performance of SPRT chart matches to the performance of Kusum chart, which is significantly lower than ANOS of Shihart chart. So overall performance of SPRT chart is significantly superior to the performances of Kusum and Shihart chart. Same case has been observed in case of lower one-sided chart. See that Maxwell distribution is skewed distribution. That's why it is necessary to assess performance for both the charts, lower as well as upper charts. So in case of lower charts also, we observe the same scenario. An extension of one-sided asperity chart is a two-sided asperity chart. How it is constructed, let me explain. The upper and lower asperity charts can be merged to form two-sided asperity chart. This chart uses two control statistics. That is the control statistic of both upper and lower asperity charts. And mechanism of this chart is like this. After taking ith sequential observation, if any one control statistic falls above its upper bound, then stop the sampling and conclude that process is out of control. If both control statistics fall below their respective lower bounds, then stop the sampling and conclude that process is in control. Otherwise, take next sequential observation and repeat the procedure. When any one control statistic falls below its below its lower bound and the other falls between its bound, then the computation corresponding to the statistic that falls below the lower bound are ceased. Through numerical computations and simulations, we observe that performance measures of two-sided charts are related to the performance measures of one-sided charts, and these are the approximate relationships between performance measures of one-sided and two-sided charts. ANSS delta is ANSS of two-sided charts, and these ANSS delta plus ANSS delta minus are the ANSS of upper and lower one-sided charts. And through simulations and computations, we found that these approximate relations are quite accurate. Similarly, this is relation for ASN delta. And these are the results of performance evaluation. Same scenario we observed in case of two-sided charts also, whatever we observed in case of one-sided charts. The blue
please conclude.
Yeah. Yes, sir, just within 1 or 2 minutes I will conclude. So the blue curve corresponds to the performance measures of two-sided asperity charts, and this one is the ANOS of Shepherd chart. The pink one is ANSS of Kusum chart, and the blue one is ANOS of asperity chart. So most of the work in existing literature on asperity control charts deal with normally distributed processes. The general conclusion is that asperity control charts are significantly more efficient than Shepherd and Kusum charts uniformly for detecting shift of any size. However, the asperity charts are not robust to violation of assumption about distribution of underlying process. We have proposed and investigated one-sided and two-sided asperity charts for monitoring Maxwell distributed processes. In case of Maxwell distributed processes also, the asperity charts are significantly better than Shepherd and Kusum charts for detecting shift of any size. These are the references, and thank you.
Okay, thank you, Dr. Mahadik. It was an interesting talk. Now it's time for questions or queries. Okay, so there are no questions. Let me ask one query with regard to this your presentation. In fact, you mentioned about the non-normal processes,
yes,
and you have used Maxwell distribution.
Yes, sir.
So you haven't mentioned anything about the other type of non-normal distribution that has been used in literature.
As a trial, we had started with Maxwell distribution. This is first thing.
Because, no, this is the first time non-normal distribution is used? No.
No.
There are, that's my query, which are the popular type non-normal processes that has been used in.
Pardon, sir?
Which are the popular non-normal distributions that has been used in this SPRT control charts?
No, this one is the first. Maxwell distribution is the first. All earlier research has been done only for normal distribution.
Okay.
And further, we also extended our work and we have developed a non-parametric control charts based on SPRT, which is based on sequential sign test. That has also been done.
Okay. Is there any rationale behind the selection of this Maxwell distribution?
Rationale behind is that it is we have chosen it because first thing is that it can take different shapes, number one, and it has good applications in physical and chemical sciences. That is the motive.
Okay.
And
I thought of this beta gamma type of distribution there.
Yeah.
We have plenty of candidates available.
And another important thing is that shared and Kusum charts have already been done for this distribution. Recently, we encountered these in literature. That is the reason.
Okay, thank you. Okay, thank you very much. Yeah, please.
It's a very nice presentation, Doctor.
Thank you, sir.
I have one doubt. You have mentioned the Maxwell distribution, and I didn't see where the estimation and the other procedures.
Because of time constraints, sir, I have skipped technical details.
Okay. So you have estimated the parameters and the parameter. You applied the parametric sheet.
No. We had assumed that parameters are known.
I see. You haven't estimated. You haven't estimated.
Parameters are known here.
Okay. So you assumed different values and then proceeded.
Yeah.
So then we cannot get the influence of the parameters.
This work can be extended. This chart can be tested if parameters are estimated. That can be future work.
Yeah.
Thank you.
Yeah, that is good.
So that's very important. Right.
Yeah.
Okay. Thank you, Mahadik. So our next speaker is Vikas Baharao Gupte. He will be talking on multivariate process monitoring with auto-correlated data. So I request Vikas to present his talk in about 25 minutes time. Please, over to Vikas.
Okay, sir. Thank you, sir. First, good afternoon to all. And I would like to take this opportunity to express my sincere thanks to organizers for providing me the opportunity of presenting the research work. Also, I would like to thank session chair Professor Sunoj sir as well as Professor R.L. Sinde sir, the organizer of this session. Is it visible, sir? Sunoj sir?
Yeah, it's coming. Yeah, it is now visible. Right.
Okay, thank you, sir.
Please proceed.
The topic of my presentation is multivariate process monitoring with autocorrelated data. Now, first part is introduction. As we know, statistical process control, this is a technique which is widely used in industry for monitoring the process and quality improvement. In industrial process monitoring, there are many situations in which overall quality of the product is determined by several related quality characteristics. The control procedures that are used to monitor more than one quality characteristics are referred to as multivariate statistical process control procedures. So this MSPC is the most rapidly developing sector of statistical process control and lead to interest in simultaneous monitoring of several related quality characteristics. Many multivariate control charts have been developed in literature to handle the multivariate processes. Among these charts, Hotelling T-square is the popular multivariate control chart for monitoring mean factor of multivariate normally distributed process. As a Sehar type chart, the major disadvantage of this chart is that it only uses the information contained in most recently inspected sample and thus relatively insensitive to detect small and moderate shifts in the process mean factor. Now, during the last few decades, various strategies have been proposed in literature to improve the performance of Hotelling T-square chart. Some of these are the use of adaptive sample sizes, or use of run rules, or use of double sampling technique, or synthetic control charts. Among these, upper C used adaptive sample size. Then they also used the double sampling technique to improve the performance of the chart. Myself and Professor Sirke have developed a multivariate synthetic control chart in order to improve the performance. Lee in 2013 studied the properties of Hotelling T-square chart and suggested the run rules for improving the performance of Hotelling T-square chart. Now, as in Sehar type chart, the basic assumption of control chart, univariate as well as multivariate control chart, is that process observations are IID distributed, identically independently distributed, and second assumption is that the process distribution is normal. So these are the two major assumptions. In multivariate setup also, the Hotelling T-square chart is based on the assumption that the successive observation factors are independent. And second assumption is that the process observations are multivariate normally distributed. Now, in many situations, it may happen that the process observation or process observation factors may not be independent. The assumption of independence is not even approximately satisfied in some manufacturing process, since the characteristics are measured in time order of production. So when autocorrelation is present in the data, and it can have significant effect on the performance of control chart procedures. That means even the process observations or observation factors are autocorrelated, then we cannot directly use the theory that is used for IID observations or IID factors. So to monitoring multivariate process with autocorrelated variance is growing area of research. To deal with autocorrelated data in multivariate process mean vector monitoring, some charting techniques have been proposed in literature. So Kalgonda and Kulkarni have proposed a Z chart for monitoring mean vector of multivariate autocorrelated process. Then Pan and Jarrett, Pasarkis and Perpendicular. In the modern process of observations of correlated characteristics gathered in rational subgroups of size n that are autocorrelated and cross-correlated. So if we consider a single observation vector x1, x2, xn, the sequence of these observations may be autocorrelated, or one observation of one vector may be correlated with another vector. So autocorrelation measures the dependence between the observations of same quality characteristics, while cross-correlation measures the dependence between variables. According to Huang and et al. 2014, autocorrelation increases the false alarm rate while cross correlation reduces the power of the control chart. So Leone in 2014 studied the performance of simultaneous univariate X-bar charts to monitor a bivariate process with correlated variables and autocorrelated observations. So they compare the performance of these charts with the performance of T-square charts for a sample size of 4, combining 3 levels of autocorrelation. They also studied the combined effect of autocorrelation and cross-correlation on the performance of bivariate T-square chart. Then Vanallo and Kulchi have studied the performance of Hotelling T-square chart for different shift size and various levels of autocorrelation and cross-correlation. Recent studies have shown that the skip sampling strategy can reduce the effect of autocorrelation on the performance of control chart. So in skip sampling strategy, the samples are formed by collecting one atom from production line and then skipping 1 or 2 or more atoms before selecting the next one atom. In our traditional sampling procedures, we continuously select the observations first from the production line, first atom, second atom, third atom, and so on. But in skip sampling, once an atom is selected, then we skip 1 or 2 next atoms and then select the next atom in the observation factor. So this skip sampling is nothing but the way of reducing the autocorrelation among the observations. So Costa and Castigula in 2011 studied first X-bar chart, univariate chart with autocorrelation level AR1 model, and they investigated 1 skip and 2 skip strategies which prescribe the measurement of quality characteristics from 1 out of 2 consecutive or 1 out of 3 consecutive atoms respectively. And it was shown that the desired effect of autocorrelation can be reduced by building up the samples with non-neighboring atoms according to the time they were produced. So these skip sampling atoms we can use to reduce the autocorrelation when multivariate T-square control chart is used. Now Leone in 2014 extended the skip sampling strategy concept to monitor multivariate autocorrelated process, and they used the first order autoregressive, that is VAR model, and they consider skip sampling strategy to reduce the negative effect of autocorrelation on the performance of bivariate T-square control chart. So in this study, our objective is to investigate the effect of autocorrelation and cross-correlation on the performance of synthetic T-square control chart. So synthetic T-square control chart is the combination of traditional T-square control chart and CRL control chart, whose performance was shown to be better than the traditional T-square control chart. So first we see the VR model and cross covariance variance matrix. So here we consider XT as the observation vector of dimensions p by 1. Then VR1 model is given by vector XT minus mu I XT minus mu plus epsilon t, where this vector is a p-variate normal with mean vector mu and cross covariance matrix sigma. Mu is mean vector. Epsilon t is the vector of independent
Something is interrupting.
I noticed it. I think, sir.
Please proceed.
Please.
Yes. Here we consider two-dimensional vector.
No, your slide.
Okay, sir, you have
to present it again.
So display it in the full screen.
Now you have to pin this presentation. Yeah.
No, it's all right, sir.
Okay.
Is it okay, sir?
Yes, sir, it's okay.
Now it has gone. Please share the.
I think we can share it.
Now we consider a two-dimensional vector autoregression model where phi is diagonal elements A, B, then error covariance matrix is given by this, and variance covariance matrix of vector x bar, it is given in this form. And after this substitutions, we get variance covariance matrix of main vectors whose elements are given in this form, and we use all these transformations to Hotelling t-square chart. Now, as we have studied, there are two strategies. First one is standard sampling strategy, means select atoms from the production lines one by one, and if we use this strategy, then mean vector is mu0, phi vector matrix, diagonal AB of diagonal, and this is variance covariance matrix of error terms. And we compute the Hotelling t-square statistic based on this mean vector and variance covariance matrix inverse, and we use this t-square as the control chart statistic and plot this statistic on the control chart with upper control limit chi-square to alpha. And if the point falls outside this control limit, then we say that the process is in control, otherwise the process is out of control. In two-dimensional vector, the shift in process mean vector, it is generally denoted by vector delta, which is delta 1, delta 2. Delta 1 is the shift in first variable, delta 2 is the shift in second variable, and we can compute the power of the control chart as P is equal to 1 minus F of UCL, where this F is the cumulative distribution function of non-central chi-square distribution with 2 degrees of freedom. And 1 upon P or 1 upon power of the chart, we call it as the average run length of the control chart. Now, average run length, it is the performance measure of the control chart. When the process is in control, that means when there is no shift in process parameters, then in control ARL is denoted by ARL 0, and which must be maximum possible. And when there is a shift in process parameters, then we get the out of control ARL, and out of control ARL should be as small as possible. That means average number of points to be plotted on the control chart to detect out of control. So that out of control ARL should be small. That means we can early detect the out of control situation on the control chart. Now this is a skip sampling strategy, as earlier I have told. That means instead of taking continuous observations from the production line, we skip the neighboring atoms. That means if first atom is taken, then for one skip sampling, we skip second atom and take the measurement of third atom. For two skip sampling, if one atom is selected, then we skip 2 atoms and directly select the fourth atom. In this way, we can use 0 skip sampling, means standard sampling strategy. 1 skip sampling, we skip 1 observation. In 2 skip sampling, we skip 2 measurements, and in this way, so S can be taken as S equal to 0, standard strategy, 1 skip sampling, 2 skip sampling, and so on. So in this case, the vector of observation will be xi1 ith vector, then second xi s plus 2, xi 2s plus 3 and so on. So when s equal to 0, the strategy corresponding to traditional strategy, that means consecutive observations are taken. Now by taking the transformations that are proposed by Leone in 2015, we get the variance covariance matrix sigma x bar in this form, and these elements are given in this way, where here S is the value of S. If S is 0, then we get the traditional Hotelling T-square chart. S is equal to 1, we get the matrix for 1 skip sampling, S equal to 2 for 2 skip sampling, and so on. So we simply use this variance covariance matrix and compute the Hotelling T-square statistic. Now, the main objective of this study is the synthetic control chart with vector autoregressive model. The synthetic control chart that we have already proposed is based on independent of the observation vectors. But what happens if the autocorrelation and cross correlation among the observations and variables is observed? Then we consider the synthetic control chart. So synthetic control chart is nothing but the combination of two charts. First chart is Hotelling T-square chart. Second chart is CRL chart, confirming run length chart. And as usual, when the observation goes to out of control limit of T-square chart, we do not consider whether the process is out of control, but we observe the CRL value, and if the CRL value goes outside the UCL, then and then only we say that the process is out of control. In traditional or simple Hotelling T-square chart or any chart, when any point falls outside the control limit, then we call the process out of control. But in synthetic control chart or combined control chart, the point plots outside the control limit, UCL, then we count the confirming run length. That means how many points that are required for the first out of control. That number we call it as the CRL. That CRL is plotted on CRL chart, and when that CRL value also lies outside the upper control limit, then and then only we call the process out of control. And this Hotelling synthetic T-square chart, we have already shown that chart performs better than the standard Hotelling T-square chart. So is procedure is like this. Determine the design parameters L and CL. L is the design parameter of CRL chart, and CL is the upper control limit of Hotelling T-square chart. For each sampling point, we observe the random observations using skip sampling strategy. In our traditional synthetic control chart, we observe the continuous sample observations, but here we take a sample by skip sampling strategy and then calculate T-square. If it is greater than CL, then we count the CRL value. Again, if it goes to upper control limit, then we say that the process is in control. Otherwise, the process is out of control. And ARL values of shift vector delta is given by this equation, that is 1 upon P into 1 upon 1 minus P raised to L. So this is ARL values. And in order to compare the performance of control charts, in control ARL should be fixed. Generally 200 or 370 or 500, these are in control values we can fix the, which depends on alpha, that is type 1 error. So these are the optimal design parameters. That means synthetic control chart requires the L and CL. L is the upper control limit of CRL chart, and CL is the upper control limit of T-square chart. So this is a mechanism how to obtain the parameters, design parameters of the control chart. And for illustration, we have considered here the synthetic T-square chart under vector autoregressive model with skip sampling strategy. Here we consider observation vector of n equal to 4 and skip sampling strategy is one skip sampling strategy. Delta is the shift in process variables, process means. For example, for first variable mean, it is shifted by 1, for second also shifted by 1. These are the autocorrelation levels in first variable and second variable, and this is the variance covariance matrix of error terms, and also we have assumed that the in control ARL is assumed to be 370. So we apply this design procedure and obtain the set of these design parameters CL and ARL. So here this out of control ARL first goes on decreasing, and then at L equal to 7 it increases. So last decreasing value, these are the design parameters. For example, L is equal to 6 and CL is equal to 7.6508. So we consider these as the design parameters. And in this way, we can obtain the design parameters for different levels of autocorrelation. So when rho equal to 0, that means there is no correlation. Then rho equal to 0.3, that is the correlation between two variables is 0.3. Correlation between two variables is 0.7. Then A and B, these are the levels of correlation, and these are the design parameters. For S equal to 0, that means standard sampling strategy. So these are the design parameters for rho equal to 0, rho equal to 0.3 and rho equal to 0.7. So by using these design parameters, we can obtain the performance of the control chart. Now here, these are the numerical values that we have considered for studying the performance. Mean vector is assumed to be 0, 0. In control mean vector. In control ARL value is assumed to be 370. Variance covariance of error terms is 1, 1, rho, rho, and we have taken rho equal to 0, 0.3 and 0.7, while this A and B diagonal correlation values are taken as 0, 0, 0.2, 0.7, 0.2, 0.2, that means equal correlation, and we have obtained the performance of the control charts. So here, okay, now this is the value of S. These are the shifts in A and B. Rho equal to 0. In control ARL value, we have considered it as 370, and when for S equal to 0, in control ARL 70, out of control,
please conclude.
Yes. Here, out of control ARL values for different shifts in process AB are decreasing, and for skip sampling, S is equal to 1. This out of control for standard sampling. This is out of control for one skip. This is out of control for two skip. So if we observe these values, so out of control ARL value for one skip sampling is early detected than zero skip sampling. Similarly, for S equal to 2 skip sampling, ARL out of control ARL value is smaller than zero skip, that means standard sampling value. That means when we skip or when we use one skip sampling or two skip sampling methods, the effect of autocorrelation can be removed, and in this way the control chart shows better performance. Now in this table we have considered equal shifts in process parameters. In mu1 we have considered shift delta 1, in mu2 we have considered shift delta 2. in next table, we have considered equals and there is only one shift, either delta 1 we have given shift and second there is no shift, and here also we observe the same performance. For example, out of control of this level, 0 sampling requires 40 observations, here 42 observations, here 42 observations for rho equal to 0. But when correlation is presented, then this control chart performs better for higher correlation. So here 21, 15 and 14. So these are the findings from our study, and in this study we suggest that the skip sampling, when we want to remove the effect of autocorrelation from the observations, we can use one skip sampling or two skip sampling methods. So this is the conclusion. It is observed that implementing skip sampling strategies with rational subgroups reduces the negative effect of autocorrelation on the statistical performance of synthetic control charts. So these are some references. Thank you.
Okay, thank you, Professor Kupe. It was a nice presentation with regard to the multivariate process monitoring with the autocorrelated data. And the methodology you have introduced, the skip methodology, I think that is quite interesting. And you have restricted mainly to the bivariate. Whether you have extended this in the multivariate, trivariate or multivariate case?
Okay, sir. We have observed it for ES equal to 3. Up to 3 skip sampling, the performance improves. But after increasing the value of ES, that means 4 skip or 5 skip, it will require large number of observations. Okay. And performance also does not improve. It comes back to the original performance.
Okay, thank you. Professor Kupe, any more questions?
Yes, sir, I have one question.
Yeah, please.
Professor Kupe, I have a very basic question.
Yes, sir.
What about the concept of rational subgroup when we do skip plot sampling?
So generally we take the observation from production process continuously.
Yeah.
That means after some sampling period, that means 1 hour or 2 hour or so on. But here in skip sampling strategy, there is no limit. That means by taking 1 hour or 2 hours, we only observe that once the observation is taken, then next observation will be taken after skipping one item or 2 item or so on.
Doesn't it lose its concept of rational subgroup?
I think for S equal to 2 or 3, 1, 2, it may not lose because there is no much more effect. But skipping large number of observations, so it may affect the concept of rational subgroups.
Yeah.
You have Dr. Mahathir, you have any queries?
No, sir. Over.
Okay. Shows hands raised.
Thank you, sir.
Thank you very much, Professor Kupe, for the informative talk. So, with this, we conclude the session on statistical process control and process capability indices. It was organized by Professor Shinte. So, thank you very much, Professor Shinte, and all the other speakers for presenting your works, and especially Professor Shinte for organizing this session. So, over to Professor Satish Kumar for concluding this morning session, I think.
Congratulations, Professor Shinde, for organizing a very nice session. with two, in fact, very good professors, Professor Mahadik and Professor Gudey. We expect these types of support in future also.
Yeah.
Yeah. Very nice session. On behalf of the Department of Statistics, University of Kerala, and ISPS and KSA, I would like to extend our thanks, gratitude to each one of you professors for your nice presentations, and especially particularly Shinde for nicely organizing this session, and in particular Professor Sunoj for chairing this session in a very attractive and very nice way. Even though he is busy with several governing activities of the university, as well as his research activity. Yeah. Thank you all. Thank you so much
Thank you
for your support.
Okay.
Thank you.
Yes.
And let us rejoin. In fact, now we are lunch break time.
Okay.
We can join at 2 p.m. Right at 2 p.m. itself. So we have. Thank you for all the participants for your patient listening.
Thank you, sir.
Thank you so much. Thank you. Thank you all. Thank you, sir. Sunod, sir.
Thank you. Thank you.
Hello, Nikhil. Nikhil.
Hello?
Yeah. Hello.
Yes, sir.
Yeah. No, I was just trying to check whether it's audible or not. I
Okay,
have
sir.
a talk at 2 o'clock.
Okay, sir.
Okay.
Hello, Professor Satish.
Hello. Hello, Professor Kanji. How are you? How are you, Professor? Yeah. Okay.
Good afternoon.
Yeah, good afternoon. Okay. If everyone are ready, let us start the session.
Yeah.
Now it is right time. Okay. In this is a special session consisting of two speakers, Dr. Rudra Pradhan and Professor Asha Gopalakrishnan. And to chair this session, we have to assist and to support the chair. We have the co-chair as Dr. Shubha is there. Dr. Shubha is a very energetic and active researcher. Completed her PhD under my guidance, and she did she got several awards, and especially Professor I. Mathai Best PhD Thesis Award, and also several publications she has. I'm not explaining too much about her. This is not for the time being. I invite Dr. Shubha to introduce Professor Kajan Jain and thereby help Professor Kajan Jain to add further proceedings of this session.
Thank you, sir. Thank you for the nice introduction. So good afternoon, one and all of you. Today, the session is chaired by Professor Kanchan Jain. She's a professor in the Department of Statistics, Punjab University, Chandigarh, a very eminent researcher with more than 32 publications to her credit from various areas of statistics. We are extremely happy to have you among us, ma'am, and I invite you to share the session, this special session in our webinar series. Welcome, ma'am.
Thank you, Dr. Shubha and Professor Satish, giving me this opportunity. So can we start with the session now?
Yeah, Professor.
We have two speakers in this session. First one is Dr. Rudra Pradhan. He's from Vinod Gupta School of Management, IIT Kharagpur. His research areas include applied econometrics, predictive analysis, statistical decision making, and he has a number of publications to his credit. He will be speaking on pooled mean group estimation, a matter of perspective. So over to Dr. Pradhan. Please take over.
Thank you. Is it audible?
Yes.
Yeah. I'll just share my PPT first. Is it visible?
Yeah, you can go to your slides. It is visible, but now you can.
Okay. Yeah. Is it visible
now?
Now
It is fine. Now it is fine. I can make it full screen if needed.
Yeah, I can do this. Is it now? Okay.
Yeah, now it is very fine. Yeah.
Okay.
Okay.
Very good afternoon to all of you, and thanks to Professor Satish to invite me for this talk, and thanks, Madam, for chairing this particular session. So when I saw the name is K Jain, so I thought it's a Professor Karuna Jain from IIT Mumbai. Anyway, thanks, Madam, for chairing this particular session. So my talk is on pool mean group estimation, a matter of perspective. Particularly, if you talk about statistical modeling or econometric modeling, so we have three different structures. One particular structure is called cross-sectional modeling, Second one is called as time series modeling, and then third one is called as a panel data modeling. So, okay, let me first, give you the kind of, overview. So if you talk about these three models, this is how the kind of, structure. If you like to understand a particular model with respect to cross-sectional modeling, time series modeling, and panel data modeling, then obviously data is a kind of, factor. That means it is a kind of, differentiating factor where, for cross-sectional modeling, I is the kind of, variations where T constant. And in the time series modeling, where T will vary, I remain constant. And in the case of, panel data modeling, or sometimes called as, pool data modeling, I and T likes to vary. So accordingly, we have three different structures, and the models basically for two variables, say y and x. This is how the kind of proxy. So here y equal to alpha plus beta x, where I is the kind of subscripts for cross-sectional modeling, and in the second case, same y and x, y equal to alpha plus beta x. In place of I, we will replace t, and then we call it a time series structure, where I remain constant for a particular cross-sectional unit, T will vary. Similarly, for cross-sectional modeling, so for a particular time period, I will vary. And in the third ones, so same Y and X, but here instead of I and T, so we have it together, both I and T. So that means technically YIT equal to alpha plus beta XIT. So the today's my talk is with respect to these third structures particularly. So where we are using a models with respect to data where we have a time series component and cross-sectional components. So now coming to panel data structures. So we have a different kind of, again, classifications. So one particular classification is called as, linear panel data modeling. And again, another is also there, nonlinear panel data modeling. And again, within linear panel data modeling, we have one-way effect, and we have a two-way effect. One-way effect means I remain constant, T will vary. So that means we like to study the time domain, and the other ones keeping time constant, we can go for checking the cross-sectional domain. So two-way effect means within these particular structures we can check time domain with respect to cross-sectional domain. So the third structure which we will have is called as pool regression. So where we like to just pool the data, time series data and cross-sectional data, but we are not going to study the particular cross-sectional effect and then the time effect. The moment we go for cross-sectional effect and time effect within the pool data, then it becomes called as panel data. So my talk is on these aspects. And okay, by the way, in the panel data econometrics, so we have a number of techniques. So far as empirical processing is concerned or estimation process is concerned. So so the techniques are basically starts with you simply called as pool data modeling, where we just club the data, time series data and cross-sectional data, and then we apply simply ordinary least square mechanism. So that's how called as simple pool data modeling, or otherwise called as PDM. So the second one is called as fixed effect model, where we again check the cross-sectional domain and time domain, so that the impact usually come into the intercept. And the third one is called as a random effect models. Again, we check the cross-sectional domain and time domain, where the impact we will study through the random term. And the fourth one, which is a little bit advanced, that's called as general methods of moments, where we like to incorporate the endogeneity issue, where we can also take care of the lag modeling, because sometimes the lag effect, lag of the dependent variable is also a factor depending upon the kind of problem which you like to investigate, which you like to explore. So that's very powerful technique, and there are several structure within the general methods of moments. So my talk is not with respect to that fixed effect model, random effect model, and GMM. So my talk is with respect to pool mean group estimation. So this is another kind of approach through which you can also investigate some problems where the data is all with respect to both cross-sectional unit and time unit. So let me give you a simple structure. What is exactly the panel data structure, and how will we go for different kind of classifications. So as I have already mentioned in my first slide, we have three different models, and this is the model with respect to the third one. So where we are integrating dependent variable with independent variables, and the IT is subscription, which represents that the structure is with respect to time series data and cross-sectional data. Then these are all, as usual, the kind of specifications or assumptions which you will put before you apply some estimation technique. And if you target this model and then you classify into two different structures, then from here we can have the first models where T constant I vary, and again we can have another structure where T constant I constant T vary. So that means cross-sectional setup and time series setup. So that's why if you go by this particular structures, then we have a simple structure here where I represents constant here, so T varying. So then we have a series of models actually, because if you have a n number of cross-sectional units and T number of say time units, then for every cross-sectional unit and when time will be a factors, then we'll have a number of regression equations corresponding to each cross-sectional unit, and for that this is how these specifications. And again, if you go to the other side of the pictures, where every time period we can have a regression models where we have a number of cross-sectional setups. That means technically I is a kind of variability where T is a constant. So that means for every time period we have a kind of cross-sectional cross-sectional modeling. Okay, so that's how the two different structures within the kind of pool data structure. And my talk is actually with respect to this pool data approach, and again, what is happening? So when we are, pulling the data, time component and cross-sectional component, and that too, if you start with this particular, model specifications here, yit equal to alpha plus beta xit, then we have some assumptions. Every time model start with the assumptions and then ends with the assumption. The first assumptions which you talk about, pool data modeling, where the alpha and the kind of that is intercept and the residuals, which are constant across individuals, and that to our time. Sometimes these particular assumptions are not always true, or reality it may not possible, because so the cross slope component and intercept component can vary with respect to the variation of cross-sectional setup and time series setup. So that's why the second approach, where we will consider the models that makes intercept or residuals change over time and across individuals. And that's slightly, you can say, more practical, more relevant, more useful, and for real life situations. And this kind of structuring is very important. And that too, when you talk about applications, the second approach is more practical and more applicable. So that's why we are, you will find more number of research, with respect to this second approach. Of course, there are a couple of several researches are available with pool data where both intercept and slopes are constant. But again, it depends type to type, problems to problems and situation to situations and so on. Our issue is not the debate between the two different structures. We are just interested to highlight what is the second approach and what are the ways we can integrate this approach with reference to a real life situation or real life problems. So talking about the pool mean group estimation, so what is the beauty of this particular technique and how it is so relevant? In fact, it's not so new, but it is a very powerful technique. The one of the point which you can highlight that it is applicable for small samples and also large samples. And again, with respect to testanarity issues, whether the variables are I0 type or I1 type, or both I0 I1 types, so this model can be also very handy. So that's why it has more I cannot say more practical, but it is very useful, because if your sample observation is less, still you can use. If your sample observation is very high, still you can use. So by the way, what is exactly this PMG? So pool mean group estimation is associated with pooling and averaging of coefficients over the cross-sectional units. So the other side's mean group estimation, which is associated with the estimation of each unit separately and averaging them over the cross-sectional units. So this kind of more or less same, but we have a different kind of structures. As I have already mentioned, so we have two different means there are a number of utility in this particular technique, but these are the two most important advantages. So first one is what I have already mentioned. It is applicable to both large sample and small samples. And again, it can be applied in a situation where the variables have a different orders of integrations. Whether it will be I0 type or I1 type or I0 I1 both. Means for examples, when you go for multivariate problems, we have a more number of variables. Some variables means there is a possibility that all variables are I0 type. There is also possibility that all the variables are I1 type, and there is also possibility that few variables are I0 and few variables are I1 type. Of course, some variables may be I2 type, higher order of integrations. So when you go for means when you find at least one variable of higher order of integration, say I2, so in that times this particular model is having some kind of limitations. So that's why this model practically can be applied, or particularly can be handy. So when the variables are under actually I0 type or I1 type, or it may be kind of mixed, right? So in that case, so we like to highlight these ones, and then again we have some kind of application to a particular problem, so which I will highlight in the just after a few slides. So what are the steps or kind of structure we have to apply, or you have to use this technique for some kind of applications. So since it is a case where means this particular technique has a certain limitation, you can say it has advantage, but it has a limitation in the sense all the variables must be up to I1 type, right? So that's why what is most important here, you have to check the testanarity of the variables. That means if you are not sure that all the variables are I0 or I1 type only within that particular interval, then you can use. If not, then you may not use. So that's why the first requirement or first step of this process is to check the testanarity of the variable. Again, since we are using cross-sectional data and time series data, because this technique is applicable or handy when you have time series data and cross-sectional data. So when you have a time series data and cross-sectional data, then there is a chance of homogeneity and heterogeneity. So means more or if it is homogeneity, then it's a good actually. If it is heterogeneity, then it is a kind of problem, and and there are lots of complexity. So that's why the second step where you have to check the cross-sectional dependency. There are several techniques which you can check the testanarity of the variables, and again there are certain techniques through which you can check the cross-sectional dependency. Okay, and the third one is the co-integration. So after checking the testanarity and cross-sectional dependency, so we have to check the co-integration among the variables. That means, of course, this technique is very handy in the kind of multivariate framework. So we like to check whether they are having some kind of relationship over the long runs. And the first step where we can use the PMG. So that means technically before you come to PMG, full mean group estimations, where the objective is to another advantage, you can say it's objective or advantage, where you can have both short-run impact and long-run impact. Because when you talk about the long runs, then by default, co-integration is a kind of factor. So that's why in the third step, we like to highlight what is the co-integration among the variables. In fact, if there is no co-integration, then this particular technique may not so important again for checking or investing any kind of problem. So that means technically to apply PMG, so you have to apply, you have to take care of the first three factors or first three steps, and then subsequently you can come to the PMG where we can check the short run and long run dynamics. Okay, so so far as the application is concerned, so we like to study the role of institutional quality, that's governance indicators, and insurance market, and that too on economic growth. So that means the objective is to know whether institutional quality and insurance market are the factors for economic growth. Since it is a kind of panel data study, so obviously you need more cross-sectional unit and more time in it. And for that, we have chosen a particular group because to bring the homogeneity within the particular structure. So one of the, of course, within this particular group, there is a heterogeneity with different kind of factors. But we assume that with random, instead of randomly picking up countries within this particular basket, we can pick up a particular group, and that particular group is called as a middle income countries. Of course, within the middle income countries, there are different kind of variations, but there is a kind of homogeneity. And the time period which we have taken is 2005 to 2019. This is as per the latest availability of data. And by the way, institutional quality is a kind of factor which cannot be directly quantified. There are certain through kind of qualitative factors which you can explore or you can quantify, and for that we have used the WDI database to get this data because it is not directly quantified, and these data are available from 2005 to 2019. So what is problematic in this particular problem, research problem, that so far as insurance data is concerned, it's mostly available for developed countries, right? And so far as institutional quality data is concerned, it's mostly available for middle income countries and poor countries. So you'll find plenty of data are available for poor countries because for advanced country, the institutional quality they have already reached the top level. So that's why their feedbacks are not available there. Only available for poor countries and rich countries. But if you link with this insurance market, then you don't find any country in that particular list. So that's why it is one of the biggest challenge for this particular project to increase the cross-sectional units, and that is the reasons actually we have chosen the full mean group estimation. So with respect to insurance kind of constraints and then institutional factor constraints, so only these countries are in the list. Otherwise, we have another kind of side projects where same middle income countries, we have 79 cross-sectional units. In fact, if you put classification upper middle income countries and lower middle income countries, again this will be a bigger list. But with reference to these two variables, and we have these are the countries through which we can take care of the particular process. And these countries are listed here, so starting from Angola, Bangladesh, India, Indonesia, Nigeria, Pakistan, Sri Lanka, and Vietnam. Of course, some are Asian countries, some are African countries, but still more or less they are in the similar kind of clusters. So these are the that's why I have highlighted these are the only countries under the middle income group that have both insurance data and institutional quality data. And the variables which you have captured for this particular investigation, where we have applied this full mean group estimations. So like this, we have used institutional quality indicators where we have used 9 different variables. And again, for insurance market, we have density, insurance density, and insurance penetrations. Insurance density again classified into 2 different parts where we have a life and non-life. And again, insurance penetrations, we have a life and non-life. And again, we have a total insurance, the coverage of insurance density and insurance penetrations. And so far as the institutional quality indicators are concerned, since there are 9 different variables, and of course the data size is very less, of course we are using panel data still, the cross-sectional units are not so high. So at least, it should be 25 above for, using, let's say, GMM technique or something, BSM, etc. But since with respect to, our factor constraints or data constraints, so we have actually used very less number of countries. So, and for that, 9 different variables for institutional quality, we have created a composite index through principal component analysis. So I'm not going details about this principal component analysis, how to construct this particular index. That means technically, instead of using 9 different variables, we are using a particular factor which is called as composite index of institutional quality. And then the last variable, which is representative as economic growth, is nothing but percentage change of gross domestic product. And the model which you have actually used is like this. So this is the first model specific, gives the idea is that economic growth is a function of institutional quality and insurance market, and where we are trying to observe what is the role of institutional quality and insurance markets towards economic growth. And the process through which we can investigate is nothing but called as panel data modeling, where I have already highlighted what are the cross-sectional units, where country is a factors, and what are the time factors. That's from 2005 to 2019. So we have used AirDL 1.1 models. The thing is that AirDL is always fitted under the structure of where variables are I0 type and I1 type, but it is not actually for the I2 type. So we have a different models when the variables having I2 types. If at least one variable is I2 type, then we may not use here AirDL type of it. So coming to the RDL model, so the second equation is actually the kind of structure where we have the short run kind of parameters, and we have the long run kind of parameter. So the ECT, error correction term, that is the kind of adjustment factors linking the short run impact and the long run impact. And the derivation of ECT is actually mentioned here with the third equation. So here we first estimate this equation 1, and then through the estimation of equation 1 we get the error correction factors, and then we link with AirDL modeling. So that means the entire process of investigation is with respect to this model 2, and this model 1 and model 3 is the kind of supporting components towards the model 2. And these are the kind of notations here. So I have already highlighted, and details are here explained here. So I'm just skipping this one. And that's how the results part. And of course, let me explain how these results are coming. See, instead of using 9 different institutional indicators, we transfer into a single composite index. And again, for insurance market, we have a different kind of indicators, starting with life insurance density, then non-life insurance density, life insurance penetration, non-life insurance penetration, then total insurance density, and total insurance penetration. Technically, we have 6 different cases, right? So that's why here the case varies with respect to the insurance indicators, where the institutional quality is a single factor. So that is nothing but a composite index. So that means for every case we have one estimation. So as a result, we have 6 different model outcomes. So in the first case, where the insurance factor is life insurance density, second one is for non-life insurance density, then similarly case 3, life insurance penetration, non-life insurance penetration, total insurance density, and total insurance penetration. Right? So that's how the kind of structure we have applied. And this estimation follows with 3 different structure here. So the first structure is the long run coefficient, then the second structure is the ECT, error correction link, the adjustment factors, and the short run coefficients, right? So, and then there are some model kind of diagnostics. There are several other model diagnostics which can be validate these models, but we prefer to report here log likelihood ratio, and all the cases log likelihood ratio is actually having fair kind of indications to justify the model validations. And these are the sample observation, 108. In fact, for panel data or pool data, 108 is not so much so good, or not sufficient. But still, with respect to our variables limitations, or the kind of problem like to investigate, so we cannot extend this much of data. So at present, so we have 108 data points, and with the 100 data points, so we have a different kind of results. Coming to the results, we will find very interesting kind of inference. Sometimes the institutional quality has a positive impact towards growth. Sometimes it has a negative impact. Similarly, insurance, it has sometimes positive impact, and it has sometimes negative one. But overall, if you look, then many occasions insurance market is having some kind of positive link to the economic growth, whereas institutional quality is having some kind of debatable kind of issues, both in the case of insurance density and insurance penetration. Of course, in the short runs, they behave very positively, but in the long runs, because institutional quality basically it's a kind of governance kind of factors, where there are always ups and downs. So that as a result, so long run is always having such so much volatile, but in the short run somehow it is a kind of giving some kind of a positive push. Means it's a kind of push factor towards economic growth. But in fact, if you look into this overall scenario, both are very relevant factors, you can say. And that means technically a particular country having a good institutional setup or a good insurance market, definitely there is a growth and there is a development. And in the case of low income countries or poor countries, it is sometimes factors. Even there is an institutional setup, but that institutional setup is not so what we can say so well established, or not having some kind of stability or sustainability. So that's why this is a very kind of debatable, or some kind of problematic. So that's why one of the suggestions from this research is that so these countries should properly implement, or they give high impact towards institutional establishment or institutional setup, because it's a kind of system, right? So institutional kind of factors, it brings develop, or brings the kind of system through which everything can generated. Similarly, insurance market, it is a part of the financial market, but many occasions, in insurance market is neglected, and particularly, for middle income countries and poor countries. Like if you look into the Indian context, you have let's say top class industry and poor industry, or medium sector industry. So you will find top class, everything is insurance coverage, where it is not there. So it's like same thing in the country levels, because for linking the insurance market, obviously there is a need of some kind of management, need of extra finance, need of infrastructure, something like that. So overall, actually, so both are having the factors. Our approach in this particular project is just to check what is the behavior, or what is the kind of role of institutional quality and insurance market towards the economic growth in the context of learning. Yeah, I am about to finish. So this is how the kind of overall findings. So the kind of message is that for every policymakers of these countries group is that they have to take care of the institutional quality factors and insurance markets so far as economic growth is concerned. So with this, I am stopping here. So I am ready to take any questions if you have. Over to chair. Thank you.
Hello. Thank you, Dr. Pradhan, for your quite interesting talk. New estimation method, whole group estimation.
Yes,
and you gave an example also. Any questions from the audience? I can't see anything in the chat box as well. So I think there are no questions. Any questions, please? So thank you, Dr. Pradhan.
Thank you, madam. Thank you very much. Thank you, everybody, for listening this particular talk. If any questions later, you can drop a mail or you can put in the chat box. I am here also for the next lectures. I am happy to answer in between if there is any kind of doubt. So thank you very much, madam, and thank you, Professor Kumar, for giving me an opportunity to have a talk in this particular seminars. Thank you once again to everybody.
So our next speaker is Professor Asha Gopal Krishnan. She is professor in Department of Statistics, Cochin University of Science and Technology, and her research interests include distribution theory and reliability. And she's been actually membership of ISI Netherlands, American Mathematical Society, IISA, ISPS, Indian Statistical Association, Kerala Statistical Association. She has a large number of publications to her credit and also shouldered many administrative responsibilities. She has also taken up many projects and consultancy works. So over to Professor Asha. She will be talking on modeling left-censored data from a dynamic reliability system. So, Professor Asha.
Thank you, Professor Jain. And I would like to thank the organizers of Wsta for inviting me for this talk, especially Professor Satish Kumar. So let me begin the talk. Let me share my slides. Thank you.
No, it is fine. Yeah, very good. Very good.
Okay, right? So I'll be speaking on dynamic models for left-censored data. This is a joint work with my student Durga Vasudevan. So I have structured my talk in this manner. So I'll first motivate this model, and later on we talk about the properties and consider a few estimation of parameters of this model. So left-censored data, by left-censored data, what I mean is the event of interest has already occurred for the subject before a time, say CL, and the exact time will be known only if it occurs beyond CL. And you represent the data as you represent a censored data as T delta, where T is a maximum of the exact time or the left censored value CL. And delta is your censoring indicator, which is 1 if you're having your exact observation, and it is 0 if you are having a censored observation. So these are like, conventionals where conventional notations of a censored data, left censored data. So left censored data is very common in survival and financial studies, and it is like, very, very common in environmental and biomonitoring studies, wherein you look into especially occupational hazards, the exposure of workers to an poisoned environment. There, what happens is you might not always be able to measure the exposure of some element because it would be below the limit of detection. And it's very common that you can only detect the value of certain variables if it is beyond or above a certain level. This could be because of the sensitivity of the measuring equipment or something else. So mainly in these situations, you find data which have at least like 50% censoring and so. So these data are very common, and and a typical left censored data would look like this. So you have This is a typical example that is there in Tennant and Muschocki, 1983. This is about the fractional variation of X-ray intensity for 53 active galaxies. Now, this is like, a well-analyzed data. And here, if you see that all the information you have is that the observation is less than 1.6. So this is a typical case of a left sensor data. And then you have like exact observations also. So there are many methods and a lot of literature is available on how to handle left sensor data. Beta substitution and the reverse Kaplan-Meier method are a few of the most popular methods to handle these type of situations. And Huynh in 2014, he had actually compared various methods and he advocates the use of Bayesian techniques over all these techniques for left sensor data. Way back in 1976, as early as in 1976, Ware and Demetz, they had analyzed left sensor data and used the concept of reversed hazard rate to analyze these type of data. And Kalbfish and Lawless once again reiterated it, and they found the survival function as Ware and Demetz did to estimate the distribution function. Similarly, Sengupta used the concept of the proportional, Cox proportional, Sengupta 1998 used it to analyze reversed hazard rates wherever, Cox proportional hazards model is inappropriate. So this concept of reversed hazard rate was introduced way back in 1963, but later on, in recent days, this is a topic of research interest. And here you define the reverse hazard rate as a dwell of the hazard rate. It actually works as a hazard rate would work for a right sensor data. Reversed hazard rate works for a left sensor data. So if you have a support AB, a random variable with distribution Fy in support AB, then the reversed hazard rate of Y is defined as Ry, probability of Y to lie between Y minus delta Y and Y, given that Y is less than or equal to Y by delta Y. So if this is an absolutely continuous distribution, you can, like the hazard rate, write it as a ratio of the density to the distribution function. And this actually gives you the probability that Ry into delta Y would give you the probability that that event has happened in a small, infinitesimally small interval of time, delta Y, just before Y, given the information it has already happened during the time point Y. So Kielsen and Sumita, they have worked on this reversed hazard rate and showed that this actually specifies the underlying phenomenon by this relationship, and they specify the distribution function uniquely. So Gupta et al. Proposed a dwell model called the proportional reversed hazards model. And the proportional reversed hazards model is expressed as an equation 1. As you can see over here, you have a baseline random variable x, which has a reversed hazard rate R0 x, and Rx is there is a multiplicative effect on this reversed hazard rate, and Rx is theta into R0 x, and this model is known as the proportional reversed hazards model. And the proportional reversed hazard model reflects on the distribution function in this manner. It will be exponentiated, and this is basically called the Lehman family of distributions. Here, F0 x is the baseline distribution function. So these concepts of reversed hazard rates have been shown to be helpful in the analysis of left-censored and right-truncated data. And the parameter theta, for the proportional reversed hazard rates model, parameter theta, actually this plays a very crucial role because you can see it is a multiplicative. The baseline hazard is multiplicated, it has a multiplicative effect on your R0 X, and this actually affects the distribution of the proportional reversed hazards model. It actually manages the skewness of the distribution, and it shows the effect. The theta gives the effect of the proportion on the hazard rate, whatever it was there on the hazard rate. Now this effect, or this effect of this parameter theta was in detail studied by De Crescenzo. He studied that how it affects the aging and relative aging in comparison to the baseline distribution. Now, suppose you have a bivariate data. For example, a bivariate left-censored data would look something like this. Now, this is a data of the amount of copper and zinc in the groundwaters of California in 2 zones. So if you look at this, here also there is an limit of detection problem. So you will have either the copper is censored or the zinc is censored, and this is the amount of these metals in the groundwater. So if you look at this, when we have to model data like this, it is very necessary to see whether there is some sort of dependence between these variables. Because when it takes into contamination of groundwater, groundwater would be contaminated either by a level of presence of copper, zinc, or both. So there is some sort of a dependence between these. So whenever you extend it to a bivariate model, you need to actually incorporate that dependence also to the model. And many a time when bivariate data come, it is the marginal distributions that are studied and reported. So whenever you propose a bivariate model, this dependence also needs to be reflected. So this proportional reversed hazards model was extended to the bivariate case, and it was studied by Kundu and Gupta in 2010. And they had extended where their marginals follow a univariate proportional hazards model. And in this model, it was something like, it captured the dependence shown in these type of data, wherein either of them would affect the groundwater or both of them would affect the groundwater. So this model actually captured the dependence on these types of left-censored data. And we were able to fit that data to their model in Kundu's and Gupta's, and we obtained a model for that data. But somehow if you consider some other type of data, data which we will be discussing in detail, and we name it as golden. This talks about the dependence between chronic renal. This talks about. I think we'll discuss this data as it comes. It talks about the dependence between liver and kidneys. So in these type of data, when a bivariate censored data, in these type of data, when you have one component, when the effect of one component, or when the event is affecting one of the component, the other component is affected, then that dependence needs to be captured by the bivariate model. And there is distribution function of the other variable would be affected. So the time at which the first component is affected, the distribution function of the other variable changes and it is affected, and there's some sort of a dynamic type of modeling that is happening. So what we have done is we tried to generalize Kundu and Gupta 2010 to incorporate this type of a modeling. For that, what we do is we define or we modify the bivariate reversed hazard rate given by Gerler in 1996, and we modify it in this manner. That is, when one of the component exceeds a limit, then the probability that when one of the component exceeds a limit, the probability that the other component is now affected by theta 1 dash R naught Y1. And when Y1 is greater than Y2, then it is affected theta 2 dash times. Suppose both of them are not like beyond the limits, beyond the LOD limits, then both of them work independently or they are independent, and then they have this type of a model, lambda 10y, theta 1 R naught y, and theta 20 R naught y. So, but when one of them exceeds, then there is a dynamism coming into it, and the model structure and the model parameter changes. The form of the model, we have assumed it to be the same. So this lambda 1, 2 and lambda 2, 1 are proportional reversed hazard rates, which are defined in this manner. It is defined as probability of yi to lie between in the small interval. Given that one of the components, you're already given the information that the ith component is less than yi, while the remaining component has experienced the event at this time point, y3 minus I delta I. So this actually indicates, this component indicates when both of them have, like, we know the information, we just know the information, both of them experience the event less than y. So in this way, we try to extend Kundu's model, and the underlying density function now changes, and it has a form 7. So this is the form of the model, and we call it the dynamic proportional reversed hazards model. So as you can see from here, if there is like no change, when there is no dynamism and the status is the same, then y1 and y2 remains independent as before. So this theorem is very, this corollary is very intuitive. Theta I dash equal to theta I, then that implies that both y1 and y2 are independent. Now the maximum of y1 and y2 also belongs to a proportional reversed hazards model, and probability of yi to be greater than y3 minus I is given as theta I by theta I plus theta 3 minus I, for I taking the value 1, 2. So you can see, like, unlike Kundu's model, the marginals are not proportional hazards models. They are actually mixture models. They are mixture models, and they are given in this manner. So, now the association between other local dependence between both of these models are measured by the measure beta y1, y2 introduced by Shankaran and Glija in 2006 for reversed hazard rate models. And that is given in this manner. And here also we can see that beta y1 is 1. This is also a very intuitive result because this actually indicates independence. And the total positivity of the model is also considered. The TP2 is considered, and it is restrictive. You have a TP2 property only when your parameter satisfies this condition. the model identifiability. We were able to prove the model identifiability of the model. So all parameters can be estimated. And then we have a characterization of this model. Suppose you have a distribution function G such that your Fy1, Y2 can be written in this manner for two baseline distributions F0 and F0. Then this functional equation 8 is satisfied only if your distribution function is of the form 9. So this is a very general relationship, and both the model of Kundu and Gupta and Kundu and the proposed model satisfies this functional equation. And we can actually use this functional equation or this characterization for simulation of random variables from any class of distribution. In fact, over here, F0 Y1 and F0 Y2 are any baseline distribution. So if you put if G and your F0 are proportional hazards models, then this model reduces to the model by Kundu and Gupta. Now, if you put your G1 F0 Y2 by F0 Y1 as our mixture model which we got earlier, this becomes a characterization of our model. And in fact, this consists of a lot of classes of proportional reversed hazards model, bivariate model, giving different values for F0, Y1 and G. You can use this to simulate your simulate observations from that distribution. So as I mentioned before, both these models, Kundu and Gupta, as well as our DPRH model, belong to that class of models satisfying that functional equation. Okay, so suppose now I define two random variables, y and x. Now I consider a few characterizations of this model. Suppose I have two random variables, y and x, such that I define y as maximum of y1, y2, and x as maximum of x1, x2. And the relationship between y and x is such that Sorry. So I defined the vector failure rate for random variable x corresponding to lambda x1, x2 as r x1, x2 and r I0 x, similar to lambda x1, x2 for the random variable x. And I defined the function at as minus log fxt for the random variable x, and ayt as expectation of a and y given y1 less than t, y2 less than t, and a1 to t1 as minus 1 by n d by d2 fx t1, t2, t1 less than or equal to t2. Then under these conditions, I can show that my x and y are related in such a manner that lambda and r are proportional hazards. So y and x are proportional, their hazards are proportional. So here I can show that this recurrence relation holds if and only if lambda naught t is equal to theta naught r naught t. Similarly, for any real number t1, t2, I can redefine the recurrence relation of those expectations in this manner, if and only if lambda 1 to t1 given t2 is theta 1 r 1 to t1 given t2 for theta 1 greater than 0. This applies for both lambda 1, 2 and lambda 2, 1. So if x1 and x2 are independent and identically distributed, then my R12 will reduce to RT1 and R21T will reduce to RT2. And in this case, the recurrence relation, this will be the recurrence relation between X1 and Y1, and we can show that under this situation, our dynamic proportional reversed hazard rate will satisfy this recurrence relationship. So when you don't have any censored observations, the parameters, the baseline, we have assumed that the baseline contains no parameters. So if the baseline contains no parameters, then we have closed forms for theta 1, theta 2, theta 1 dash and theta 2 dash, if their observations are not censored. But when you have a left censoring, so it could be any of these situations, either both the observations are censored or one of them are censored, and none of them are censored. So in that case, the likelihood contributions are as in 11. And this we solve using optimization techniques. We have used the software R. Now for Bayesian analysis, we did a simulation, and samples from the posterior distribution were generated using the MH algorithm. So we could do a Bayesian analysis also. So for the inverse Weibull distribution, whose baseline is specified by this, we were able to obtain these results as a for maximum likelihood estimate. And these were the results for the Bayesian estimates. We showed the prior sensitivity by actually working out for different parameters as well as different priors. We could see that they were robust. And we considered the Australian twin data studied by Duffy. So in this data has been, it's a very well analyzed data. We take a sub data from this. This data has 6 zygote categories, and we take this monozygotic identical male-male category. So here our theta 1 and theta 2 is taken to be the same, theta, because it's a twin. It's very intuitive. They are twins. And there are 157 pair of twins, among of which 60 and 66 are censored respectively in twin 1 and twin 2. So both of this twin have undergone this appendectomy, and the censoring is, you consider the observation to be censored if they have undergone appendectomy before a given age. So now we were looking how the information that a twin has already undergone appendectomy. We know that the information a twin has already undergone appendectomy. What would be the probability that the other would have gone appendectomy at a certain age Y1 before this twin? So now these parameters are theta 1 dash and theta 2 dash could be same. So we take this condition, theta 1 dash and theta 2 dash. It is similar for both. And for different baseline distributions, that is the inverse exponential, we have fitted these inverse Weibull, inverse exponential, and generalized exponential. With that, we saw that the inverse Weibull was a better fit. For the inverse Weibull, we had a baseline parameter 2. So then we tested for this, whether the value of one affects the other. That is, we had to test the hypothesis whether if there was an independence between two variables. So we could actually confirm that there was some sort of a dependence between the pair of twins. And then we conducted the Bayesian analysis on this model, the inverse Weibull model. We considered the flexible gamma prior, and this is what we observed. And we could take the estimate of theta and theta dash in this manner. So, here in this, we actually considered a bivariate class of models, which is used to model a two-component load-sharing system. I didn't use the word load-sharing system in this earlier presentation because load-sharing system is a particular case of dynamic systems. So I would rather for my example here, instead of load-sharing, I would use dynamic system. Sorry for this load-sharing. When there are left-censored observations is proposed, the proposed model uses concepts of proportional reversed hazard rate for modeling such system. The distribution of the maximum of lifetime of two components are and different properties of the models are discussed. Characterizations of this model are presented, and we have done the simulation studies and illustrated the proposed model with an example. So these are the references. Thank you.
Thank you, Professor Asha. You have kept up with the time also. And it was a very interesting talk. Actually, we have seen most of the results or whatever is there in literature is mostly pertaining to right-censored data. And you have given very interesting examples and analysis for left-censored data.
Yes.
That is really appreciable. Great. So one can now think of working on left-censored data because there are examples available for this, real-life examples.
Yes, yes, a lot of examples, in fact.
Yes. We took it to the bivariate setup also and used reversed hazard rate. So that was really good. Thank you. Any questions from the audience? Nothing in the chat box.
Okay, can I ask one question?
Yes, sir.
Okay, so you are talking about, it is very applicable to bivariate setup only. Am I right?
Yes, sir.
What will be, the situation in the context of multivariate setup?
Well, the model proposed by Kundu and Gupta, that can be directly extended to the multivariate setup. But the model that we have proposed, that needs to be taken in every dimension. That is not very straightforward. At least you need, not. It can be done. It can be done.
So is there some work on multivariate or no?
Yeah, multivariate, there is work on reversed hazard models, multivariate reversed hazard models, yes.
There will be definitely works. There are works. Otherwise, it will be questionable. In the real life situation, you cannot just think a model and you cannot do a kind of innovation with respect to bivariate setup. Okay, in the real life scenario, do you think that any problem is very restricted to bivariate setup? Obviously not.
Yeah.
Kind of extent.
Yeah.
In the bivariate setup, because it means it's very reliable and very user friendly. You can say the moment you go to the multivariate setup, then there are lots of complexity will start increasing.
That's true. That's true. In our model, even the model cannot be written in a multivariate. Even in the trivariate setup, we need to work out the various combinations, y1 less than, y2 less than, y3, y3 less than. But in the model presented by Kundu,
in fact, in the multivariate setup, the one typical problem is the multicollinearity issue. So already data has some kind of problems. Again, if you find any kind of multicollinearity problems, then the complexity will be very high. That's why that may be a factors for this situations. I hope you know multicollinearity, right?
Yeah.
In your case, if you maybe the models you're using, they will be affected due to multicollinearity.
Yeah, it can be factors, but actually, you have to be
Multicollinearity is basically talking about dependence between the variables, right? Y1, Y2.
No. It's not Y1, Y2. It's actually it is the game of independent variables only.
Covariates.
Yeah, covariates. It is basically covariates. No relations with Y.
Yeah, we have not included any covariate in this model.
No, in the bivariate setup, there is no question of multicollinearity at all.
Yeah.
We start within the trivariate and multivariate. In fact, in the multivariate, it is actually very meaningful, and the impact is very, very complex type of thing. If you have more and more independent variable, then the chance of multicollinearity and the volume of multicollinearity is very high. So that time it is very difficult to handle this situation.
But if they are not taking up any covariates, then question of multicollinearity does not arise, even for the trivariate.
No, you have to take care of the covariates because see, covariates is the requirements, right? So, but multicollinearity is a negative side of the pictures. It's a negative side of the pictures because covariate is allowed, but multicollinearity is not allowed. But in the same time, multicollinearity you cannot find a model where there is no multicollinearity. That's why there is a limit actually. Up to certain limit, it can be tolerable, and after certain limit, it cannot be tolerable. So that's why it's a very challenge. It's a challenge, and to optimize this particular structure is very difficult sometimes.
Okay, Professor Asha, you can look into this.
Yeah, I think I
know. It's a kind of a suggestion. See, I know there are lots of challenges to face. Thank you.
She can look into it.
Yeah, sure. No, she can divert to to her student, and she can explore something more.
Whenever they want to extend this work, they can surely think of looking into this also. Okay, Thank you, Professor Asha, and thank you everybody who joined this session. And thanks to Professor Satish again. Okay,
Thank you.
Thank you.
Thank you, sir. Thank you.
Dr. Sashish, your microphone is switched off.
Okay, thank you, Professor. Okay, thank you. Thank you once again. Yeah, on behalf of the Department of Statistics, University of Kerala, we wish to extend our gratitude to Professor Asha Gopalakrishnan and Professor Rudra Pradhan for their talks, and Professor Kanchan Jain for chairing that session. Now we have to move to the our next session, or a keynote session. The speaker is our Professor Carlos Kachashvili. Professor, this session is Professor B. Basu, and Raki Ramachandran will support you, teacher, Siddharashmi teacher, for chairing this session. She will do the needful for as a support to you as co-chair. Raki is our student and our contract lecturer. Is a faculty of our department presently. She is a very active researcher, and she is doing all the activities assigned to her in a very sincere way. She has publications, good publications, and also have certain awards, especially the C.R. Rao Gold Medal for Best Paper Awards, etc. Now, I invite Raki Ramachandran to introduce Professor Siddharashmi and thereby help her to other proceedings of this session. Okay.
Thank you very much, sir.
Yeah.
Thank you very much, sir. Good afternoon, one and all. Good afternoon, one and all. The present session is chaired by Professor V. Seethalakshmi. Professor Seethalakshmi was the Associate Professor and the former Head of the Department in the Department of Statistics, Nirmala College, Muvattuvuzha. She is a very eminent and hardworking researcher, and she has more than 25 publications, especially including statistical papers, statistical methods, statistics and probability letters, etc. Her special areas of interest are distribution theory, time series, statistical inference, etc. Also, she has produced 2 PhD scholars. And more than that, we have heard a lot about her, the quality of teaching and her dedication to the subject. So we are extremely happy to have you among us, ma'am, and we humbly invite you to the new session for our webinar. Ma'am.
Thank you, Rahi, and thank you, Sadesh sir. Good afternoon to all. Welcome to the technical session 16. It is a special session in honor of Professor D. Basu. Today we have the speaker, Dr. Carlos Kachiasvili, with us for delivering a talk on parameter estimation of some irregular probability distributions. Let me introduce the speaker of the session. Dr. Carlos was basically an electronic engineer, obtained his PG in applied mathematics from Moscow Energy Institute. Then he acquired candidate of science in technical cybernetics and information theory from Moscow Energy Institute and Doctor of Science from Chemical Technology Institute, Russia. Now he is a full professor of Georgian Technological University, Georgia. He has published more than 200 research articles in reputed journals. He has also served as a consultant for various academic institutions. We are extremely delighted to have such an eminent speaker over here with us, and I am sure that this session to follow will enlighten you all. With extreme gratitude, let me now call upon Dr. Carlos Kachiasvili to deliver the talk. Also, I welcome all the delegates to this session. Sir, please.
Thank you very much. Thank you. My good wishes and greetings to all of you, because we are living now at difficult situation, but I hope very soon it will finish and we will meet physically to each other on such interesting conferences that is present conference. Now, Dr. Sashish, explain me how I can to share my presentation.
Yeah, Professor.
I cannot find activities. Here is activities. I must click on activities.
Hello, Professor. Yeah, first, yeah.
What action I must to make for sharing my presentation?
Yeah, Professor. Yeah, at the bottom there is a present now button. Present now. Yeah. First of all, you open the slides in the desktop. First open the slides and then you go to this.
My file is open.
Okay. First, now you please come back to this platform, Google Meet platform.
Okay.
Yeah, and now there in the bottom, the right to the hand raise symbol, there is a upward arrow. Just click on there. That's a present now.
Details.
Yeah, that the small.
Okay.
No, Professor. No, Professor. Bottom central position. Bottom. Yeah.
Which
bottom.
Which bottom?
Central. Bottom central place. Yeah.
This one?
There is a hand raise button, you know, hand raise symbol is there. Can you see? Near to that, the right side of that, there's a small upward arrow in a small box.
Yes.
Yeah. Click on there. So a small pop-up menu comes, isn't it?
Oh,
A small,
activities.
yeah. Then your entire screen, you can see there that small pop-up menu in the small, your entire screen, window, a tab, like you can see. Click on there, that small arrow. Now, then you can choose your entire screen. Can you see that?
I cannot find. Here are different bottoms, but
Yeah, Professor, the
but
bottom.
CC, turn off captions. CC. I click this button.
Yeah.
But no new
Okay.
buttons appear.
Oh, there are different versions of the Google Meet. Probably there are the other different versions, maybe.
Meeting details.
Yeah. Please wait 1 minute. Wait. Yeah. 1 second. Okay. Then there in that version, the right side, extreme right, you just 3 dots are there. Can you see?
Dot. Yes,
Extreme right.
dots.
Can you see that?
Full screen, change background. Change background.
Left of that present now button.
Left of that 3 dots, left of that 3 dots, there is a present now button is there. Can you see in the bottom anywhere that 3 dots?
Turn captions.
So turn on
Here
captions.
is 3 dots. I
Yeah.
click and here are.
You don't click on 3 dots.
What?
You just turn on caption.
Right to that.
Caption. Okay.
Right
Caption.
to that there is a present now button. Yeah.
Reply.
3 near to 3 dots. There is.
Yes, 3 dots after.
Yeah, there is a
Present now button.
Present now is there. Just touch on present now. Yeah.
Sir, next to that turn on caption button, there is a present now button. Can you see that, sir?
What?
Sir, there is a turn on caption button. Can you see that?
Yes, caption bottom. I click.
Yeah,
and
please
after
don't.
they appear it.
Yes. Next to that there is a
language, English.
yeah. We can turn on the caption. It's not the right button. Next to that there is a present now button. Can you read that one?
What? Can you read it? Yes, I can.
Yeah.
Yes, I can. And after what? It's after what?
Can you see some symbols in the right side? Down.
In the right side, down, yes. Yes.
Yeah. What
Meeting details after show everyone, after chat with everyone, and the activities.
Okay.
There are only 4 buttons.
Okay, sir. Do you see the mic?
Mic symbol.
Okay.
Mic symbol. Mic symbol.
Yeah.
No, here is not such symbol.
So is there any small box in which a upward arrow, is it such a symbol is there anywhere in the bottom? bottom. A small box in which an upward arrow. Arrow directing upward direction.
Upward arrow, upward arrow, upward arrow. Where is upward arrow?
Okay. Just put on the cursor, your cursor.
Yes.
Yeah.
You enter screen, a window. Present.
Yeah.
A window.
Yeah.
You enter screen.
Yeah, that
I must
click.
click
That,
it. Okay.
that click you do. Yeah. Then a box comes up.
Okay.
Okay. Now click on the middle of that box. So share button, share will be active. Share that portion will be active.
Okay.
Now
Do you
to
see?
share. Yeah. No. Now to clear.
My
Click on the
file,
click on the share.
Yeah.
Yeah. Now it is coming. Yeah. Verify.
Okay.
Yeah,
Thank
it's
you
okay.
very much. I am sorry for inconvenience which was caused
You don't worry,
by
Professor. Doesn't
technical
matter.
reasons.
You are most welcome.
Okay,
Yeah.
thank you very much. Thank you.
Yeah, very good. Very good.
The title of my presentation is Parameters Estimation of Sub.
Yeah, now you can make it full screen, Professor. Professor, now you can make it full screen, if it is possible.
I have. This is full screen.
Yeah.
This is full screen.
This is full screen. There is a you can just shift F5, or otherwise there is a symbol to make it full screen. View is there. Or in the bottom there is a symbol to make it full screen.
Go to PowerPoint presentation.
Yes,
go
this
to
is PowerPoint presentation.
Yeah. At the end there is full screen.
Sharing PowerPoint.
PowerPoint. This is PowerPoint. Oh. This is
At
PowerPoint.
Right end.
Screen. White show. Click screen arrow.
Just Dr.
Sashish, do you see my file, my presentation?
Yeah, we can see you, Professor.
And what problem is?
Yeah, but
What problem is?
Yeah. In the bottom there is a
Yeah, next to that, right? Go to right. Yes. Next. Yeah, this is one.
It is good?
Yeah.
Is it good? Can I start presentation?
Yeah, it is good, no problem. But the screen is small.
Unfortunately, here aren't any button that I can use for increasing of this. Okay. Show presentation view.
Slide presentation.
Slide presentation.
It is last one in the bottom.
Yeah. Next. That is correct. That is good.
Okay.
You have to click on there.
Can I start? Can I start?
Click on that. Click on that position. Just to click.
Can I start?
Okay, Professor.
Okay. Can I start?
Yeah, that is not working because I don't. Yes, Professor. Yes, can start.
Okay.
We can think of later if needed.
Presentation title is Parameters Estimation of Some Irregular Probability Distributions. On this slide is presented presentation structure. After short introduction, estimation of the parameters is offered in item 2. And the next item, iteration algorithms for computation of estimates of the parameters is presented. in item 4, concluding remarks are given, and finally, references are presented, which we are used working on this probability distribution of the random variable is called irregular if domain of definition of this variable is bounded and depend on the distribution parameters. As examples of irregular distributions, the following can serve: uniform, right-angled, triangular, trapezoidal, antimodal 1, antimodal 2, truncated relate, and beta distributions. All these are probability distributions of the continuous random variables. These distributions are used, for instance, at approximation of measurement errors when solving the problems of control and management of the quality of the environmental objects. The uniform distribution is simple and perfectly studied distribution, therefore we will not consider it here. The expression and graphical forms of densities of other distributions are the following. This is distribution density of right-angled triangular distribution, and on this figure is presented its graphical view. Triangular distribution density has the following form, and this is appropriate graphical graphical form. The probability distribution of trapezoidal distribution is the following, and this is its graphical representation. Antimodal 1 distribution density has the following form, and this is its graphical graphical form. Antimodal 2 distribution density is the following, and this is its graphical form. And truncated probability distribution density of truncated relay distribution is the following, which has two parameters, A and sigma square, which must be determined by the sample, and depending on the values of these parameters, this distribution density takes different forms, and some of which are shown on this figure. The generalized beta distribution density has the following form. It has 4 parameters, 2 endpoint parameters and 2 shape parameters, and the appropriate distribution function is the following, and this distribution is quite good studied and presented in this monograph. This distribution is very flexible, and depending on the values of its 4 parameters, it takes many different forms, some of which are the following. For different values of shape parameters when endpoint parameters are equal to 0 and 1 respectively. Let's consider estimation.
Excuse me, Professor.
Of the,
excuse me, Professor. The slides are not moving. Slides are, yeah. Your slides, the PPT presentations slides are not moving.
Not move, not move.
Yeah, not move. Yeah, Professor.
In my computer, they move.
Oh, okay. Well, what I don't know whether others.
Now, do you see item 2, estimation with title estimation of parameters?
What about Raki?
What?
What about the others? Whether it is moving or not?
This now I show slide which has title estimation of the parameters. Do you see this file, this slide?
No, only first file is seen.
Yeah,
first
Professor.
page. First page.
Now it is moving. Now it is moving. Yeah.
Do you see this?
Second
now
slide.
it is up. Now it is moving. Now you can see estimation of the parameters. That
okay, estimation of the item 2, estimation of the parameters. Do you see this slide?
Please continue, Professor. Okay, Professor.
I cannot understand.
Yeah.
Now I'm going to talk about item 2, estimation of parameters, and I show this slide. Do you see this slide?
Yeah, now we can visible. It is okay, Professor. Estimation of the parameters. Up to this time.
Estimation of parameters.
Yeah.
Do you see?
Yeah, we can see.
Okay.
Okay.
Okay. Let's consider estimations of the parameters of the distributions which we have presented in previous slides. Let's consider in the beginning the following distributions: right angle, triangular, trapezoidal, antimodal 1, antimodal 2, then truncated relate, and finally beta distributions. Maximum likelihood estimators of the parameters of the first group of distributions that determine their domain of definition are given by the formulae. These estimators. Do you see next slide?
No, Professor. That slide containing estimation of the parameters heading. That is here.
Yes, these estimations of the parameters A and B. Do you see this slide?
Yeah, that we can see. Okay. Next.
This is next slide.
Not visible, Professor.
The estimators of the parameters A and B are consistent and efficient, but biased. Do you see this slide?
No, Professor.
I do not know what.
If there is difficulty, you can please send to the slides to us, and we can present it from here.
Send this file?
If via email, if you can send to me.
By email, send this file to you?
Yeah, I shall present from here, Professor.
Okay,
so that,
okay.
Now we can see the movement is, now it is moved.
Now, you see now what is this slide?
Yeah, now we can, the movement is, you just move so that now the estimate, now you can see the estimation of the parameters. Next, just move, but return back.
Do you see this slide?
Yeah, here, the earlier slides, it is visible to us. Estimation of the parameters.
Can I continue?
Yeah.
Can I continue?
Yeah, please.
Okay.
Just to move, please.
Okay, next. Do you see next?
Yeah, now, okay.
And
Can
this
move.
one?
Yeah, that's good.
Okay. Then I will use this format. I will not increase in size of these slides. Okay.
Yeah, Professor. Okay, Professor.
Okay.
Yeah.
For the first group of distributions that are right angle triangular, trapezoidal, antimodal 1, antimodal 2, estimation of the parameters of this group of distributions can be determined by this formula. These estimators are consistent and efficient, but biased. Indeed, from here, it is seen that mathematical expectations of these estimations are biased, where alpha of n is computed by this formula. It is not difficult to be convinced that consistent and unbiased estimators of A and B are computed by the following formulae. For determination of the function alpha of n for the considered distributions, the following formula can be used. Where f is Gauss hypergeometric function. Applying this formula, we obtain for the triangular distribution for alpha of n function, we have the following formula for computation of alpha of n. For trapezoidal distribution, expression for alpha of n is the following. For the antimodal 1 distribution, this formula takes the following form, and the for antimodal 2 distribution, this formula is the following. There are used the recurrent formulae for computation of hypergeometric polynomials, and these recurrence formulae are given in this monograph. Maximum likelihood estimators of the parameters of the truncated Rayleigh distribution are the following. It is obvious that when A tends to infinity, it is for usual Rayleigh distribution, the maximum likelihood estimator of the variance is this one. Mathematical expectation of maximum likelihood estimation of parameter A is the following, where bias delta of n is computed by this formula, where phi is standard normal distribution. It is difficult to find an unbiased estimator for the parameter A because in the expression for the bias, the same parameters are incorporated. Therefore, instead of unbiased estimators, we use quasi-unbiased estimators obtained by iteration process when in the beginning for computation of estimation of the parameter A, estimation of sigma square is computed by formula 2, which is formula for usual Rayleigh distribution, and then for computing estimations of the parameters A and sigma square by formulae introduced above, their values from the previous stage are used and so on until difference between neighboring computed values were not less than given accuracies. The comparison of mean square deviation on biased and quasi-unbiased estimators shows that the quasi-unbiased estimators are more efficient. Indeed, this is curve which describes mean square deviation change depending on n for biased estimation. And this is the same characteristic for quasi-unbiased estimation. The same fact takes place for other irregular distributions considered above. These unbiased estimators are more efficient than biased estimators. Examples of the application of the obtained results for computing estimators of the unknown parameters of the considered probability distributions are given in the table 1, which is presented on the next slide. For the truncated Rayleigh distribution, letter B is used for the denotation of the parameter sigma square. For all the considered distribution laws, the number of generated random variables used for computing the estimators of the appropriate parameters is equal to 50. In this table are given exact values of parameters of these 5 different irregular distributions.
Given is a Japanese manga series written and illustrated by Natsuki Kizu. It has been serialized in the bi-monthly manga magazine Sherry Plus since 2013 and has been collected into 6 tankobon volumes by Shinshiken. The series follows a group of 4 students in an amateur rock band and the dual romantic relationships that form among them, between electric guitarist Ritsuka Unoyama and vocalist Mafuyu Sato, and between bassist Haruki Nakayama and drummer Akihiko Kaji.
Distribution. It is irregular as its domain of definition depends on the distribution parameters. It is seen from these distributions that it has 4 parameters as we mentioned it above, 2 endpoint parameters A and B, and 2 shape parameters P and Q. Their determination is quite difficult problem in general. When the values A and B are known, the parameters P and Q can be quite good estimated using, for example, the method of moments with the first 2 moments, sample mean and sample variance, as follows. These formulae are obtained by the method of moments and they are given in this monograph. The method of maximum likelihood for P and Q consists in the solution of the system equations where C is the gamma function and G of X is gamma function. It is easy to be convinced that the maximum likelihood estimators of parameters A and B are biased, and this fact is shown in this work. Therefore, it is obvious that they are used in the formulae obtained by the method of moments and by maximum likelihood method for finding the estimations of P and Q deteriorates for accuracy, deteriorates the accuracy of estimates. For avoiding this lag and obtaining a simple, fast, and easy to realize technique, an iteration algorithm for computation of effective estimates of the shape parameters of beta distribution using the unbiased estimators of the endpoint parameters of the random variables is developed. The following statistics are the unbiased estimators of the endpoint parameters A and P, where G small of n is computed by this formula and G big of n is computed by this formula. They do not depend on the parameters A and B, as these functions depend on only P and Q and the sum size n. For determining estimators of unknown parameters on the basis of the sample with size n, there is offered the following iteration algorithm. Compute the maximum likelihood estimators of the parameters A and B, compute the estimates of the shape parameters P and Q by formulae obtained by the method of moments. Using the computed values of P and Q, compute the unbiased estimates of the parameters A and B by formulae given above. And on the next stage, by A unbiased and B unbiased, compute new estimates of the parameters P and Q by formulae obtained by the method of moments. And using these values, compute new unbiased estimates, A unbiased, B unbiased, and so on. Define the stop time of the iteration process by the minimum of Kolmogorov-Smirnov statistics. It is by minimum of this expression, which is maximum value of maximum absolute absolute divergence between empirical and theoretical distribution functions. The results of computation obtained by simulation of the appropriated data confirmed high quality of the offered method. In particular, the dependencies of the accuracy characteristics Kolmogorov statistics on the sample size are shown in figure. From here it is seen that for different values of parameters, Kolmogorov-Smirnov statistics decrease depending on n. N increase, this characteristic of accuracy decrease. From here, the basic property of estimates is obvious. With the increasing sum size, Kolmogorov-Smirnov significantly decrease. The following regularities can be derived from this data for obtaining the optimal estimations in the sense of the offered method. For small values of P and Q, least iterations are necessary. For big value of n, least iterations are necessary. For big values of P and Q and or a big difference between them, a large number of iterations are necessary for the same n. When P and Q or both are bigger than 10, a large number of iterations are necessary for getting the proper estimates, and their accuracy deteriorates. In these cases, the use of the optimization algorithm offered below is preferable. Sometimes the estimates of the parameters differ significantly from their exact values, but the appropriate Kolmogorov-Smirnov statistics is quite small, and the beta distribution with these values of parameters approximate well the data. It seems that the regularity 5 occurs due to the flexibility of the beta distribution, which causes the similarity distributions with different parameters and the impossibility of Kolmogorov-Smirnov to react to small differences between empirical and restored distributions. If highly accuracy estimates are required for big P and Q or a big difference between them at a least number of observations, and we are not restricted by time for obtaining such estimates, it is possible to define the more precise estimates of all parameters using the following one more stage of computation. This stage has the following form: to solve the following constrained optimization problem. It is to minimize by all parameters of beta distribution absolute value of maximum divergence between empirical and theoretical distributions at the following restrictions. Via P iteration and Q iteration are the estimates of appropriate parameters obtained by the iterative method. For solving this stated problem, optimization problem, we used the method of possible directions, which is described in this monograph. As a starting point for the parameters in the optimization method, we use the estimates of these parameters obtained by the iterative method. Examples of the graphs of the divergence between empirical and estimated distribution functions by the sample of different size n for the parameters, for the following values of parameters are shown on this and next slides. This is empirical and restored distributions for n equal to 20, and this is dependence on x of Kolmogorov statistics. Here are the same characteristics for n equal to 30. And the same characteristics for n equal to 50 and 100, and from here it is seen that for n equal to 100, accuracy is quite good. N size of sample increase and accuracy increase, and for n equal to 50, n equal to 200, 500, and moreover, 1,000, 10,000, this approximation is very good. Excellent. For 20,000, it is very excellent. The proposed method was used in biometric systems of electronic verification of people on the basis of measurement information of a fingerprint reader. This is described in this work. It must be noted that there was recently published a very good qualified paper, Parameter Estimation of Generalized Beta Distributions, and its application to a historical tsunami magnitude dataset by Meno and Shibuya. Oh, I'm sorry. Some problems arised in my computer. Just a moment. Okay.
Okay, Professor, let us wait.
For estimating the generalized beta distributions, Nagatsuka-Balakrishan, Kamatsuka transformation, and Hall and Wong's empirical Bayesian likelihood are applied in the paper to the shape parameters and the location scale parameters, respectively. A new estimators of the parameters is proposed here. The proposed method is applied to a historical dataset of the tsunami magnitude scales. The authors of the paper compared by simulation the quality of the estimations of the parameters of beta distribution obtained by their method and the iteration method considered above in this work, in my work, without optimization. The results confirm the correctness of the given above regularities, also high qualities of both methods. On this slide and on the next slide are given references which we used at working of this presentation. And finally, thank you for your attention. And I'm sorry for difficulties and for problems at my presentation.
Thank you, sir, for this wonderful presentation.
Thank you. I'm sorry once again.
No, it is okay, sir. No problem. So we can follow your talk. So audience, do you have any doubts, any clarification, please ask to Professor. Discussion session, you can ask questions to Professor for clarification.
You ask this question, I must answer your question, or I'm waiting for questions.
Anybody? Any doubts? So, okay, I think that we can make a conclusion. Thank you, sir, for this presentation. And thank you, Sadish sir and the department for giving me an opportunity for participation in this program. Thank you, sir.
Thank you, Professor Kachashvili, for your wonderful presentation. Thank you. In fact, we, on behalf of our department and associated societies, ISPS and KSA, we would like to extend our gratitude to you, Professor Kachashvili, for your nice presentation. And also, Professor, we extend our gratitude to Sita Lakshmi teacher for chairing this session, and Dr. and Rakhi Ramachandran, Ms. Rakhi Ramachandran to co-chair this session. And we have a very nice sessions. And now let us move to the next session. Thank you so much once again. Thank you, Professor Kachashvili and Professor Sita Lakshmi teacher.
Thank you, sir.
Thank you, sir.
Thank you. Thank you.
Let us move to the next question. I think there is a slide. Yeah, it is time. What about the speakers of the next session? Everyone are okay? In fact, there is 5 minutes if needed. We can take gap, or otherwise we can move to the next session. So that without much delay. Yeah. Nowadays, in fact, those who have any questions or anything like to ask, nowadays you can interact with online via your email. So Professor Kachashvili's email is also you can available. Simply just to click on the Google Meet, on the Google browser. And in the next session we have 2 speakers. In fact, it is concentrating on the medical side. As it is a special section, special invited session. And our speakers are Anil C. Matthew and Yadav. Professor Madhugar Malliya will chair this session, and supporting Dr. Dilip. Hello, Dilip?
Yes, sir. I'm here.
Yeah. Dilip is also here. Malliya sir is here. Okay. Dilip, I shall introduce simply Dilip because Dilip will carry over the other part. Dilip is a very active researcher, and he is presently a faculty member of the Department of Statistics, Calicut University, University of Calicut. And we hope a good researcher from him. And he has several publications of his to his credit, in fact, and also he won several awards. He's a very enthusiastic person. And Dilip, you just give a brief introduction to our chair, Malaya sir, Professor Malaya, and thereafter support chair to carry over the remaining part of this session. Okay, the proceedings of the session. Okay, okay, Dilip, please carry over.
Thank you.
Over to you.
So first of all, I welcome everyone to technical session 17. So as you all know, already Sadish sir already mentioned, this session will be chaired by Dr. V. Madhugar Malaya sir, and he was the former head of postgraduate and research department of mathematics, Marigonis College, Trivandrum, and currently is working as a professor and head of the department of mathematics and science, Mohandas College of Engineering, Trivandrum. And he has more than 40 years of teaching experience and produced 4 PhDs and published more than 100 research papers. And he's a life member of various subjects associations, including Kerala Statistical Association also. And he's a reviewer of AMS mathematical reviews also. So we are very grateful to have you, sir, to chair the session. So I formally invite Malaya sir to take over the session.
Okay, thank you. Okay, can you hear me?
Yes, sir.
Okay. First, let me thank Dr. Sadish Kumar and his team for giving me a chance to participate in this event and chair this special invitee session. Now, the first speaker is Dr. Anil C. Matthew. Okay. So I'm happy to introduce our first speaker, Dr. Anil C. Matthew. He is a professor of biostatistics, PSG Institute of Medical Sciences and Research, Coimbatore. His main area of interest includes epidemiology of non-communicable diseases. He is having various international collaborations with researchers and universities. He is also an adjunct faculty at the Department of Medical Education, PSG IMSR. Dr. Anil C. Matthew got his postgraduate degree in biostatistics from CMC Vellore and a PhD from Bardiyar University, Coimbatore. He has published 42 research papers in various national and international journals and has carried out various epidemiological research projects. He has also delivered several invited lectures. He is a reviewer as well as editorial board member for various national and international journals. Dr. Anil received WHO scholarship to attend the Southeast Asia Regional Meeting of the International Epidemiological Association at Dhaka, Bangladesh in 2008. He is a member of various subject associations in India and abroad. He is a recipient of Suraj Kali Jain Award from Indian Society for Medical Statistics. Today, as special invited speaker, Dr. Anil C. Matthews is going to give a talk on longitudinal data analysis methods in clinical research. So we'll have a 5 minutes discussion after the talk. The time is from 4:05 to 4:40.
Thank you, sir.
Okay, sir. Start.
Sir, is it visible and audible?
Yeah.
Yes, yes, sir.
So,
Yes.
It's visible and audible? Yes.
It's okay. It's okay.
Yeah. Thank you, sir. Satish Kumar sir, for inviting me to give a session talk on this international conference. And it's a great is mainly addressing for the postgraduate students and the researchers to get a motivational message on the subject on repeated measurement data analysis. And this presentation, it's very interesting that I have not included much statistical symbols and notations, but just see my own experience sharing over the past 30 years, what I have learned, especially in the field of medical and public health. Let us see that two terminologies come parallelly, longitudinal data and the repeated data. What is the difference between these two? I have referred so many textbooks, and some books says that...
Professor, you have not opened the slides.
Slides are not opened. 1 minute. Stop sharing.
You can see the folder containing that that's PDF or PPT. Repeated measurement data analysis that we can see. I think that is, yeah. Oh.
Now you can see, sir?
No.
Not yet.
Was gone away.
Now?
No, Professor. Yeah, just start. Repeat it once again. The sharing. Please share it once again.
Share is not.
It's not.
Tab. Is it now? You can see, sir.
No, sir. Yeah, now it is coming. Now it is coming.
Yeah. Now it's coming.
Yeah, now you can see.
Okay.
Yeah, longitudinal and yeah. You can make it full screen, Professor.
Sir, yes, sir.
Now it is okay, but it is not full screen. That is in the bottom. There is a right. There is a cup symbol. You can just click on that, or you can go to the slideshow and make it full screen.
Slideshow.
Yeah, upper there slideshow is there. Slideshow button.
Sir, not here.
Yeah.
Yeah, your cursor comes. I think this is
visible.
This is visible, no problem. In the bottom, yeah, your cursor is moved.
Yeah.
There is a slideshow button is in the above. There is can see.
Now is it visible, sir?
It is visible. It is visible.
Yes.
Visible, no
It's
problem.
visible.
But,
You
yeah,
can start
but
the slideshow. That's all.
Yeah. The above file, home, etc. There is slideshow. Can you see?
Oh,
Yeah.
yeah.
Yeah,
Just before that.
Yeah, from the beginning. From the beginning. Yeah. Now is it okay, sir?
It is the same thing as the earlier one. This is not the slideshow. I think you double click that. Single click.
Yeah, there is a full screen maybe option is there.
The full screen option is over here, sir. Now can you see full screen?
No, this is not slideshow because you can see the display on the left.
Yeah.
So this is actually not the slideshow.
No.
In the first, there is from the beginning you can click. Or you can move that side type of a symbol is there in the bottom. Can you see?
Yes, sir. They already clicked on that button.
This one.
Yeah. That's right.
Sir.
The clicking on that also not working well. Yeah. Then it is okay. You can move in this way itself.
Maybe do that.
Is it okay, sir?
It is the earlier version with indicating this left side, etc.
So actually, the clipboard is there. That is a.
Yeah.
Without the clipboard, it would have been larger.
Yeah.
So if you start the slideshow, that clipboard will not be there.
Yeah. You can. There is a start slideshow button. Yeah. Now it's
earlier.
Start slideshow. Yeah. Start slideshow. There is a
slideshow. Yeah.
Slideshow from beginning. Slideshow from beginning.
Is it okay, sir?
From beginning.
Sir, even when we press that, you can see only this.
Okay.
This one.
Okay.
Yes, please click on the enable editing button.
Hello, there is, it is in the protected view.
Yeah.
Just
enable
it and then do. Enable editing.
Enable editing, yeah. That's good.
And then just to
go to the.
Okay.
So now, sir?
Now
everything gone away. You have to start.
We've done the enable editing, sir.
You just start it once again, so that share it once again.
Yeah.
Repeat the earlier procedures. Share.
Yeah. Then.
Now it is coming. Yeah.
Yeah. Is it okay, sir?
Now slideshow. Now click on the slideshow.
No, you present it. That is, there is a small cup in the bottom. Just
yeah, that's it. Correct.
Bottom, there is a small cup you can see.
Is it okay?
Is it okay? No problem. But if it is,
the other would have been better.
Yeah.
The slideshow is though it would have been better.
Yeah. Or otherwise you can continue.
If it's not possible, we can start from here. No problem. Anyway, it is visible. No worry.
Visible.
Yeah.
Thank you, sir.
Don't worry.
Thank you, sir. We tried it, but somehow the technical system we could not able to such. But anyway, this session is basically, as I mentioned, there is not much of the statistical symbols and other things are not there. Just my 30 years of life experience in PhD. What are things which I am observing in this field? Just sharing, that's all. Especially some motivation for the postgraduate students. First thing is, what is the difference between longitudinal and repeated data? This I have checked with the 2-3 textbooks. In one book, it was mentioning longitudinal data is a special case of repeated data when measurement factor is time. So in that way, longitudinal data is a part of repeated data. Repeated data is the broad spectrum and the longitude is a sub part of it in that school of thought. But in another school of thought, what it says that repeated data is a special case of longitudinal data when measurement factor is for a short period of time. For example, if anesthesia department, we are taking values 1 minute, 2 minutes, 3 minutes, or 4 minutes, or 5 minutes. That is called a repeated data. Whereas in community health, school children, we are doing follow-up for 10 years or 20 years. We call it as a longitudinal data. Now let us start with the basic things. Paired data is the basic of this repeated data. left and right eye measurements of the same person, or husband and wife voting preference, twins, same persons in a crossover designs. All these things are paired data. So it's a very simple way. If you look into it, observations from the same pair tend to be more similar than observations from different pairs. That is, observations within the pairs are correlated. They do not each contribute independently. I just take an example of two treatments. One is surgery plus new eye drops, one treatment. Another is surgery. It's a randomized controlled trial. For each of the 5 patients, randomized one to receive treatment
Slide. Excuse me. The slide. You have kept the first slide itself. So just move on the slides.
We are moving, sir.
Okay.
Just not moving.
So you just click on the left clipboard. To select the slide, you click on the left clipboard. If you want to go to the second slide, just click on the next slide.
Now you can see it. Second. Now you can see.
Now it is okay.
Okay. So, what do I mean by paired data? Various examples we have, like left and right eye measurements, or twin value, or same persons in a crossover time over several times. Why we different methods for the paired data? Observations from the same pair tend to be more similar than the observations from different pairs. Let us have an example. Compare 2 glaucoma treatments, surgery plus new eye drops and surgery alone. For each of the 5 patients, this is a randomized control trial. Randomize one eye to receive treatment 1 and the other eye to receive treatment 2. And our primary concern is the laser flare photon values. The lower the value, which is the better. I have the small test. I'm not teaching you big things. We have the treatment 1 and the treatment 2. And the first patient, left eye, we give the treatment 2. And the second treatment is given to the right eye. And for the second patient, the right eye, we give the treatment 1 and the left eye, we give the treatment 2. And this is the values which we are getting. And mean value of the treatment 1 is 26 and mean value of the treatment 2 is 30.6. I wanted to do the analysis. The simplest analysis which we can do is independent t-test. So the null hypothesis is very simple, everybody. I don't think it's very difficult. Mu1 is equal to mu2. And the difference in the observed mean is minus 0.46, and the 2 sample t-test which we are doing p-value, we are getting 0.25. And what is wrong with this analysis? Everybody will ask you. Then the immediate answer from all our students is, sir, what you did is a very wrong analysis because independent t-test is not the suitable test for this analysis. You have to do paired t-test. So when you do the paired t-test, you will get statistically significant results. That is a common answer which most of the students tell to me. The reason why they are telling is at each of this session, what there's some logic is there for each patient. Treatment 1 having lower values, so which we have to look into it. That is the logic behind of that school of thought. And now let us see the same data when I did this paired t-test. The logic which I have mentioned is for each patient I receiving treatment 1 did better. Can we use this information to perform a more appropriate way? And when we did the paired t-test, according to our expectation, what we got is that d bar is equal to, as we told, minus t value, which is statistically significant. P value is less than 0.05. And we all say this is the way which we have to do it, the applications of the paired t-test. Like that way, we will tell it. Now, accidentally, I did one more analysis for the same data set, like a randomization test. Yesterday, we have a very big elaborate session on this particular topic. Man-VTU test, the improved approximations for these things. The professor was presenting in yesterday's conference. Anyway, I have done the randomization test also. But in SPSS, we don't have the randomization test. We usually call Man-VTU test equivalent to this randomization test. But again, the shocking part of the study is that again, it is not statistically significant. So which result I should take it? That is my question. Wilcoxon sign rank test is equivalent to the randomization test in SPSS. The p-value is again like 0.0625. So in the large sample test, it doesn't make much a difference. But when it becomes small sample test, which we are automatically are forced to look into the non-parametric part of it also, because t-test and other things are directly related with the confidence intervals. So basically what we should do is probably a man-with t-test may be a better reliable result than the so-called parametric test. Now let us have an expansion of this concept, univariate methods of looking into the repeated data. Let us have a small expansion of this data set. A small example which I was taking is the data ventilation volume of 8 subjects under different temperatures. We have -10, 25, 37, 50 and different temperatures, and there are 8 patients. We are taking these 6 values at this different temperature. Basically what we would like to check is, as the temperature increases, this ventilation volume decreases or not. So when I was studying my MSc, what I was taught is all these ventilation volumes, you keep it as the dependent variable and the temperature as the independent variable, and find out the slope of, in each case, you find out the slope for it. I have found out the slope for it and asked me to teach this so-called t-test or a Wilcoxon test. So we are getting the statistically significant result. So we have a feeling of saying that as ventilation volume tend to decrease as the temperature increases. But again, I was all trial and error experiments when I am doing it. Later, I was taught this concept of t-square statistics, hoteling of t-square statistics came to the picture. It is readily available in the SPSS, and even if you don't have the SPSS in your hand, still you can do by computer programming and other things, you can get it, this t-square value. But when we did this t-square statistics, the finding is that the result is not statistically significant. So later, after years later, we were taught this. So according to the t-square statistics, what we are seeing at the 5% level of significance, there is insufficient evidence to conclude that the mean ventilation volume at the 6 temperature differs significantly. Then again, as we are growing over the past 30 years, another new concept which came into this field is repeated measurement data analysis. The null hypothesis is mu1 is equal to mu2 is equal to mu6. And we are taught on doing this repeated measurement data analysis. And when we did this, F value is 3.10, P value is 0.02. But this SPSS also, we are insisting there's a condition called a sparsity assumption, and which is very difficult to get satisfied. But in this case, I got satisfied as the sparsity assumption. So the conclusion is this result is statistically significant. So now the question for you is, but of course, now the question for you is which I should believe it. When I did this univariate one sample data, the difference is statistically significant. When we did unstructured multivariate approach, there is no statistically significant difference. When we did this repeated measurement ANOVA, that the results are statistically again significant. So 1 and 3 methods, when we look into it, it is statistically significant. And the second method, when we look into it, it is not statistically significant. Especially I being in the field of medical field, most of the clinicians are more concerned about the outcome of the study. They are not much concerned about the theory of this part. They are more concerned about the outcome of the study. So what outcome, what result which we are forced to give to them. So basically looking into this type of scenario, I feel that unstructured multivariate approach is more reliable, especially a non-parametric approach. We may have to resort into it because other things again depends on the confidence interval and other things plays a low look into it. Now years later, we have the advanced method came for the linear mixed models came into the picture. The linear regression models that contain both the fixed and the random effects models. And this is relatively new tools useful for correlating or continuous outcomes. The non-linear mixed models available for binary or categorical outcomes. And parallelly, we look into the GE also came into the picture. That's also an added thing in this scenario. Now, I just talk something about the linear mixed model in this last 20 minutes or 15 minutes time. There are many names for this linear mixed models. One is for hierarchical linear models. Some people will call it as multi-level models. Some people will call it as random coefficient models. And some people will call it as growth curve models. Just for the beginners, I just introduced this small concept. I have taken a data from the American Heart Associations. A common program is the BMI reduction among the school children. And we have it's a randomized control trial. Half arm we are doing the intervention and half arm will give the control arms. and probably yoga and other things are the commonly used methods. And we take the values of the BMI, visit 1 and visit 2 and the visit 3. Though we call it as a BMI reduction program among the school-going children, and those who, the doctors, physicians who know this field, they know that BMI will not reduce over this period. Especially for the children, BMI will increase only. So basically what we are looking for is this rate of increase is our primary concern for it. So basic questions which you would like to address is, do the groups differ with respect to change in BMI from baseline to post-intervention, V1 to V2, controlling for other important variables? And also we would like to know, do the groups differ with respect to change from baseline to 1 year the following in the V1 to V3, controlling other variables, or whether this differs much or not? That's what which we would like to look for it. Now let us say how to look the basic question which we will ask is V1 to V2 or V1 to V3 or V1 to average of V2 or V3. The question for you is how the baseline value we should adjust for it, the so-called Y0 value. When I looked into the literature, we are seeing 3 different ways which we can look into the baseline value. The first is called analysis of covariance, which they tell Yj is a function of Y0. In some school of thought, they are telling it's better to do Yj minus Y0 as a function of Y0. And third school of thought, they say Yj itself, keep it as a dependent value and do that. But these 3 models are not equivalent. But my personal preference is for the 3, which I just explained you for the beginners. What is the difference between these 3? Let us see the data set. We are measuring BMI at 3 different times: baseline, post-intervention, and 1 year later, which is called BMI 1 and BMI 2 and BMI 3. And we have treatments and various covariates are there. And we are particularly interested in the influence of the treatment on the BMI, adjusting the effects of the covariates. So long time back, it is called old-fashioned data entry structure. We keep BMI 1, BMI 2, and BMI 3 like this format. But now, including SPSS and SAS, they have changed the format. Visit 1, visit 2, visit 3, and BMI. This is the way which we used to do t-test and all other things. SPSS insists us to do these things. Now, when you look into these 3 models, the first model, what they are telling is keep the Yj and, for example, visit 2 and visit 3 value and keep the Y0 as baseline value as the one of the independent. That is a model 1, which we conventionally call it as analysis of covariance. That's one way of seeing it. Second way of seeing it, take the difference of Yj and Y0, express this as a function of Y0. That's the second way of seeing this function. And third way of seeing it, keep the Yj itself. It includes the baseline value also as a function of the treatment and see the effect of the treatment on the BMI value. And in this is actually what we are looking into the linear mixed model. And the linear mixed model, one part of it only I just would covering it, which is called a random effect model. Especially those the beginners, many of the PG students or research scholars, they may not be getting an idea of what is this linear mixed models. So the explanation is actually according to their faith. So there are 2 children when you look into it. I have taken from the data set one ID number 106 and ID number 102. There are 2 children out there. But the fact is that this first child grows above the raw mean value, but the second child goes below the average intervention value. That means the children are not growing in the same, not in the same format. This is the main concept in the linear mixed models. So 102 data all fall below the population line, whereas 106 the data all fall above the population line. So the conveying message is data for some kids cross the population line. So kids differ from one child to another child. We don't expect all children to grow at the same rate. So what we have to do in this scenario is, there are 2 errors are there. One is called a subject effects and the second is called a visit effect. Both of these things comes under the category called the correlation models. We keep under the correlation model. Now let us take the BMI model, BMI IJ. We keep this model BMI IJ B0 plus the treatment factor and visit 2 and visit 3 and treatment versus visit 2 interaction and treatment versus visit 3 interaction and rest of all the control arm values and alpha E and EIJ. Alpha I is the child variation and EIJ is the observation variations. So BMIJ is the jth observation from the ith child. Alpha is the random effect for the ith child. EIJ is the random error for the jth observation of the ith child. And alpha I, let us say, for a normal 0 sigma square B, and EIJ, let us for normal 0 sigma square W, and alpha I and EIJ are mutually exclusive. So in mixed models, what we look into is fixed effects contribute to the expected mean values, and the random effects contribute to the correlation or variance covariance models. Now, let us see the difference between linear regression versus mixed models. Linear regression, y is equal to beta naught plus beta 1x plus epsilon. Epsilon follows normal 0 sigma square. Whereas in mixed models, what happens is y is equal to beta naught plus beta 1x plus alpha I plus Eij. Alpha I follows normal 0 sigma square B, and random error for the jth observation follows normal 0 sigma square W, and alpha and epsilon are independent. Just to get you a basic idea, let us borrow the day 1 standard of the BSc Statistics, first day of the class, basic properties of the expectation. Let us borrow. I am not going to take much in depth of this. The 5 important formulas which we studied in the BSc Statistics day 1. Expectation of A is equal to A. Expectation of AX is equal to A into expectation of X. Expectation of A plus X is equal to A plus the expectation of XY, and variance of AX is equal to A square variance of X, and variance of A plus X is equal to variance of X, and variance of X plus Y is equal. These things are which required in this analysis. Similarly, covariance of X plus Y, X plus Z plus W is equal to this covariance, and particularly the last result is more useful. Covariance of A plus BX, C plus DY is equal to BD into covariance XY. Now let us apply these things in the difference between the linear regression and the mixed models. What we'll see is that the expectation of Y remains the same for both linear and mixed models, but the difference happens for the variance part of it. Variance of Y in the linear model, it is sigma square, and variance of Y in the mixed model is sigma square B plus sigma square W. So now, the same logic which we do it, the covariance part of Yij and Yik, if you see the correlation, the interesting part of this finding is the last 3 columns become 0, and we are only first row is remaining covariance of alpha I and alpha I, which is called as sigma square B. So, what does it actually tells is, in the random model, like everybody, like simple formula like a correlation of Yij by Yik, what will happen is that you will get sigma square B by sigma square B plus root of sigma square B plus sigma square W into this. So this will become 0. So basically what the conveying message is, it is a compound symmetry assumption is what which we are getting in the random effect model. That means what does it mean is the correlation is the same regardless of how far the observations are. So basically it have a form, it will get a form of 1 row, 1 row, and row, and 1 4 we get it. So this is what which we are assuming in the random effect model. But now let us take the expected values of the BMI. Expected value of BMI for the visit is 0, for the visit 1 for the treatment 0 is beta naught. Simple simplification only. Visit 2 for the treatment control arm is beta naught plus beta 2. And visit 3 for the control arm is beta naught plus beta 3. Whereas intervention group, visit 1 for the treatment 1 is beta naught plus beta 1. And visit 2 for treatment 1 will be beta naught plus beta 1 plus beta 2 plus beta 4. And visit 3 for treatment 1 will be beta naught plus beta 1 plus beta 3 plus beta 5. So what actually happening is that in this story, if you wanted to see the group differs with respect to change in BMI from baseline to post-intervention, we have to subtract these two mean values. That means basically it is the regression coefficient of beta 4. That is what which I want to convey. Many often I have seen students are making mistake in this particular scenario. So actually this beta 4 is the regression coefficient of treatment and visit 2. This regression coefficient is what we should report to this change in B1 versus B2. And thus the null hypothesis for the primary question is reduces to null hypothesis beta 4 is equal to 0. Estimate of beta 4 is equal to minus 0.16 and p-value is 0.068. So answering our questions of interest, do the groups differ with respect to change from visit 1 to 3? Again, we can simplify it, which I didn't do the simplification. When you simplify it, it is beta 5 is the regression coefficient which we needed it. So basically this intra-class cluster correlation which we are going to get is 0.961. That is same in this compound symmetry assumption, which is under a random model. Usually when we do randomized control trial, we are having usually conventional, it is not a textbook based, we have only two options. One is either assume random effect compound symmetry model, or we have the model of assuming the unstructured model, which is actually what we call the variance. There is a variation in the correlations. So when we do this unstructured model, this is the way which we are getting the correlation structure. Now the question for you is which we have to choose it, unstructured or compound symmetry. This also I have referred to textbooks. The conventional method is BIC is one of the recommended method for this choose. In this study which we have looked into it, the compound symmetry for BIC is 6259 and unstructured it is BIC. So actually unstructured is a more recommended method in this scenario than the compound symmetry. But however, I have checked the p-values. P-value didn't change much in both of these situations. But again, the old question is still remaining, whether the old unstructured methods are still necessary when we have linear mixed models. The unstructured methods are valid methods of analysis when repeated measurements are obtained, a fixed set of time points, and there are no missing data, based on fewer assumptions compared to the linear mixed models. Unstructured methods perform better in small and moderate samples than the linear mixed models. But over a long data, and we have missing values, LMM is more recommended. And what are the other methods which came to the picture? G for linear regression when the outcome variable is continuous is another thing. G for the logistic regression came. G for the Poisson regression came. G for the proportional odds came. Generalized linear latent mixed models. These are the newer other methods which is in this picture. And in SPSS, we have both options are there. The advantages are mixed models can fit multiple levels of correlation. For example, longitudinal data from children clustered within the school. G is generally restricted to one level of correlation. Mixed methods can fit subject-specific models, whereas G can fit marginal models. But the main disadvantage is mixed models require normality assumption, whereas G allow for weaker distributional assumptions. This is a way which we have to enter the data in the SPSS, and this is the SPSS commands which we have to do it. And I don't know these things. And software, if you are doing SAS software, the plot mix is the command which you have to give. Statile XTMX mix this command, and SPSS mix this the command which you have to give for the linear mixed model analysis. And my first experience in the repeated data is 88 when we conducted an Indo-US workshop on longitudinal methods at New Delhi. That was the first time I was listening all these various sessions for the repeated data. From ever since, I got various opportunities to look into this subject. Very recently, I attended a PhD examiner in the All India Institute of Medical Science. Dr. R.M. Pandey was the PhD guide, and I was the external examiner at the Viva was conducted. He has conducted various other methods like variance correlated methods, Anderson-Gill independent methods, all these type of new methods, standard probability models, conditional probability models. It's a good thesis. I have done microscopic evaluation for the thesis. There's not a single mistake. I could find it out. It's a very good thesis, which is some of these methods which research scholars can look into it. And we have good interesting books like Deagle's books, Davies' books, and all very good books on the repeated measurement of data. And thank you for these things.
From the audience, any questions? It is time for questions. From the participants, any doubts or questions? I think somebody wants to ask any questions. You can do. We have 1 or 2 minutes left.
Maybe I can give some comments.
Yes, sir.
Okay.
Yeah, he had mentioned several statistical tests. A lot of students are here, so I just wanted to add one point. So whenever you are looking for data, you have to see the structure of the data. So accordingly, one has to choose the right statistical tool. Otherwise, you may arrive with the wrong conclusion. That's what the message he given.
Yes, sir. Yes, sir. Really, really true, sir. Because especially the medical field, the conclusion what we are going to give is more important than the theory. So we have to be very careful in what conclusion that is the conveying message, sir.
Any question more? Okay. Then thank you, Dr. Anansi Matthew, for giving an excellent talk.
Thank you, sir.
Okay.
Thank you, sir.
Thank you.
Sorry for the 5 minutes delay happened in the early. Sorry.
No. Anyway, you have completed in correct time.
Thank
By
you.
4:40, you have completed.
Thank you, sir. Thank you.
You have maintained time. Okay.
Thank
you so much. Thank you so much. Oh, second speaker is there?
Yes, I'm here.
Okay. Our next speaker is Dr. Yadav. I am happy to introduce Dr. Yadav, who is a friend of mine. Dr. Yadav is a surgeon and a clinical epidemiologist in the Department of Surgery at Government Medical College, Trivandrum in Kerala. He is an eminent researcher in this field. He is trained in epidemiology, qualitative research, biostatistics, and data analytics with coding expertise in Stata, R, and Python. His major interest is in mixed method research and has published about more than 11 papers in international refereed journals. He is a reviewer for various journals and is an associate editor of a BMC Springer Journal of Medical Case Reports. He holds several positions at various local and state level research and ethics bodies. At present, he has multidisciplinary collaborations, works with the Rajiv Gandhi Institute of Biotechnology, CSIR, NIIST, Global Institute of Public Health, Pallium India, and NIHR Global Health Research Unit on Global Surgery. His research projects in pipeline on surgical site infection after laparotomy is funded by the State Board of Medical Research and on zebrafish modeling by ICMR MRU. As our special invited speaker today, Dr. Yadav is going to give a talk on designing a clinical study, the role of graphical causal models with statistical assumptions encoded in. Welcome, Dr. Yadav.
Thank you for the kind introduction. Thank you for inviting me to the workshop. Let me share the screen. Can you see the screen?
Yeah, it is too small.
No, sir. It is visible.
Visible, but too small. Can you enlarge it?
Yeah. Now you can see your desktop.
Can you see it now?
Your
laptop. Yeah, now it is.
Now
can you see it now?
Okay.
Yeah. Designing a clinical study.
Okay. My topic is the designing a clinical study, the role of graphical causal models with the statistical assumptions encoded in. First, I'll give an outline of the top different headings in which I will be talking today. First, I'll be discussing about the design workflow we follow in our research unit. Then I'll be discussing a few words on counterfactual theory, potential outcome, then the graphical models and the condition for causal association observation studies and how you implement that with the help of R or Python. First, let me tell you how we design a study in our unit. We have a clinical research unit in our department. If our colleagues or the residents or other researchers come to us for designing a study, what we do is we first team up with three kinds of people. First is a subject expert, then a clinical epidemiologist myself, then one statistician. The most important role there statistician has a role to do in this team. Whenever we have a controversy, we have a written protocol that there will be a controversy between the on a particular topic or a particular idea between the subject expert, clinical epidemiologist, and statistician. Statistician should say the last word. And it is very important that we have to include the statistician in the design phase. Now, once we have the question from the clinical researcher, we categorize those into the four categories. One is whether it is a descriptive question, or it is an associational question, or it is a causal question, or it is a predictive question. In our field, most research questions will be almost descriptive type of questions, and a few will be associational type, and very few will be causal and predictive. But what will be the type of the design? We have a model thinking, like we think of a descriptive model, or whether it fits into a causal model, or whether it fits into a prediction model. Then what we do, once we categorize the design of the study into these categories, then we go into the design proper. Here, though we decide, though the researchers say that there is an association study, most often, whenever we say association study, we have some causal intent. That is actually true. So this descriptive study, these associational studies and causal study can be lumped together under one category. And the prediction questions we usually answer in prediction modeling, diagnostic modeling, and scoring systems, etc. Then, here, actually, there is a difference between a causation prediction when it comes to clinical study. When we say causation, we imply that whenever there is a change in the X, there will be a corresponding change in the Y. Example, when we intervene, or when we manipulate the X, there should be a corresponding change in the Y. Then only we call it causal. Or we put in the counterfactual intent. We will be discussing about how we can frame that in a counterfactual way in the next few slides. Then, if it is a prediction question, whether it includes whether it is included in the diagnostic model or a prediction model. Then, but for the causal questions and the associational question, the most important thing is change in the Y, whether it is reflecting the change in the X reflects in the change in Y or not, because it is very important when it comes to interventions, policy changes, and population strategies, etc. So we give more importance to causal questions or associational questions. Now, once we have decided the questions, we have a very strict format that for how to frame a question. That is called a PICO format. We create a question based on that. Then we do extensive literature search. But in a causal models, actually, we don't go for statically derived Ender method or stepwise method or other kind of regression. We don't go for. We actually go for an a priori model that will be coming in the next few slides. Because the data-driven methods may underestimate or overestimate most of the times the effect size, and most of the covariates for a causal model need not be adjusted, because in a study there may be a lot of covariates. We don't have to adjust all these covariates. There is a minimum subset of covariates that we need to adjust. This can be informed by a priori modeling. So we usually, what we do in causal studies and associational studies, what we do is we have a priori set of variables, and we specify the model a priori with the help of a statistician. Then the next phase, what we do is we do an extensive literature search, because this is to be informed by the existing theory and the consensus, especially these variables. So what we do is we do an extensive literature search involving the subject expert as well as myself or a clinical epidemiologist. Here we use PubMed or other databases. In addition to that, we use various packages like RISMED. Then we do the text analysis. Ultimately, we come up with a digital index card. In the digital index card, all abstracts and all the citations and everything will be encoded. Then after the literature review, what we do is we conduct a mini FGD. FGD means focus group discussion. Usually nowadays we do it in a WhatsApp group. We put the questions in the WhatsApp group and the expert answers, and they come up with some variables. So we have two groups of variables from the literature search and from the FGD. Now, this is one example of the literature search we conducted for this this study, DVT. In 2020, there are 17 studies related to that, and we have the digital index card here, abstracts and literature review, everything. This is a model, index card only. Now, we have the variable extracted. Now, we group the variables into two categories. One, those variables with a strong theory and plausibility proven. Then there are other groups with the equivocal proof or doubtful. Now, usually this comes from the consensus opinion and from the literature search, as well as the strong theory-driven variables as well. Then we come to the proper designing part. Here we create a conceptual model with the statistical assumptions included. Before 2012, what we do was we are just creating a conceptual model. When we came to know about this directed acyclic graph and causal inference, then we resorted. Now what we depend on is we create a conceptual model with the help of a directed acyclic graph. Then now we go. Now we discuss about. We'll be discussing a few words on causal framework. Actually, there are a lot of causal framework are there. We depend on two kinds of causal framework. One is a counterfactual or potential outcome framework. Actually, this was put forward by Neyman in the context of randomized control studies. Later, it was taken up by the Jamie Robbins, and that was extended to the observational studies. This counterfactual potential outcome theories. Then there is another theory by Julia Pearl, whose one famous book is very famous, a book of Y and causality. He put forward the graphical causal models, and it was taken up by Miguel Hernan. Then there was another graphical model that was by the Sprice et al., but that is a graphical accuracy model. Then now we discuss a few words on the counterfactual model. The counterfactual model is actually, whenever we discuss about the causality, this is to be viewed from a counterfactual angle. Suppose in the setting of RCT, suppose I am taking a medicine, like one medicine I am taking for reducing my BP. So if I have to say the particular medicine has got some effect on me, that means an individual, then he should satisfy one particular criteria. That is a counterfactual criteria. That means at the same time, there should be two me's. That means I and an alternate world, I am another I. And I am given the medicine, and the alternate I am not given medicine. So when I am given a medicine, and I am being followed up, and I get an outcome. Then I go back in time, and for the same myself, I don't give any medicine, or I don't take any antihypertensive, then that particular me is also followed up, then I get the result. So the difference between these two things is actually the actual causal effect. But the problem is it is never observed, because one is counterfactual. Because whenever we give a medicine, before giving a medicine, there are two possibilities. One is I can have this outcome. There are two potential outcomes. Like I can have a potential outcome if I take this one, and I have another potential outcome on the other world. So the actual outcome is actually the difference between these two. But this is the inherent problem of causality, because we can never assess the individual causal effect. Then what the circumvent is very a simple philosophical concept. That is, if I can find a me almost similar to myself, that means a group. There is another group almost similar to me, and if I can give that medicine to that group, and I can give to I am not giving the medicine to another group who are not like myself. So there are two groups, and in between these two groups, there is a control group, and there is a group who take the medicine. So it is very easy to find the difference between these two groups. This is the basis behind the RCT. So what we do is, instead of the individual causal effect, what we do is an average causal effect. It's an expectation in the population. So that is the basis of the counterfactual theory. So the counterfactual, one of the problem is, once you have assigned the patient or the group, or one of the patients in a particular group to a medicine, he can have only one outcome. The counterfactual outcome will be never observed. So there are two things. One is potential outcomes. Then one of the potential outcome is an observed outcome. The other potential outcome is a counter to the factual outcome. There is a counterfactual outcome. This is never mentioned. But this can be clearly demonstrated or implemented in an RCT. We'll come to that later. And in association and in observation study, if we can we can have something so that we can come up with a conditional exchangeability, we can satisfy same principle. So before the treatment, suppose X is the exposure or treatment treatment, then there are two possibilities, and X can be 1 or X can be 0. Then the outcome can also be Y is equal to Y is 1 or Y is 0. These are all observed things. But the notation for the potential outcome is superscript with the superscript. So Y superscript X1 means what could be the outcome if the exposure was 1. And the second thing is Y superscript X is equal to 0 means what could have been the outcome if there was no exposure. These last two, these are the potential outcomes. So each potential outcome has got two possibilities, two possible values. One possible value is, okay, we are assigning the patient. So yeah, Y superscript X is equal to 1 could be 1 or it could be 0. So the two possibilities are there for the two possible exposures. So once the problem is, once the treatment is assigned, we have only one observer, some other is counterfactual. This counterfactual thing is, there is a one, that means there are two potential outcomes. One of the potential outcome become an observed outcome, and the other potential outcome is actually a counterfactual outcome that we can never see unless in a group. That is actually a mathematical formulation. So this counterfactual outcome can be considered as a missing data. So there are methods to look into the problem and solve the whole thing as considering the counterfactual outcome as a missing data. So as I mentioned just now, the individual causal effect is very difficult to get. So actually it is an observed outcome minus the counterfactual. That means Y superscript X is equal to 1 minus Y superscript X is equal to 0. Then what we can do is we can find out the average causal effect. The average causal effect is an expectation that we can found out from the population average causal effect. This is also known as average treatment effect, average causal effect, etc. This is a difference between proportion of the outcome. This is actually probability of the Y X is equal to 0, X is equal to 1 is equal to 1 minus probability of Y superscript X is equal to 0 is equal to 1. Actually, these are the potential outcome notations, but this can be actually offset in the groups. The question comes down to how we can have this potential outcome differences in an associational causal ratio or causal difference. So here the associational difference is actually probability of Y is equal to 1 given X is equal to 1 minus probability of Y is equal to 1 given X is equal to 0. So the question is how to make it causal. So that probability of Y superscript X is equal to 1 is equal to 1 minus probability of Y superscript X is equal to 0 is equal to 1. So here there are some conditions. We have to, if we satisfy those conditions, from the offset thing we can extrapolate to the actual causal effect. Is also known as average causal effect. It is never individual causal effect. So this is a counterfactual view. Then the same can be seen from a graphical causal model, but it is easy for non-mathematical people like us. Here, all of the assumption can be encoded in the various graphical edges and vertices. Here it helps in encoding, assessing the conditions. Actually, it is so easy to comprehend and plan. There are alternatives for the graphical causal models. One is a combination of the counterfactual model plus the graphical model. Is also known as single word intervention graph, SIG. Actually, we use SIG only in repeated confound days with time repeated confound days. That is a multiple confound days occurring at multiple time points. So T0, T1, T2. When we get this kind of data, we apply the single word interventional graphs. Otherwise, we go for the normal DAG only. So Now we discuss the before we go to the Python code, I mean the R code today, R code. We will be discussing how a basic structure of the DAG is. DAG is a directed acyclic graph. Actually, it is composed of a vertex and a edge. Vertex will be like this. Edges will be like this. Here, the edges encode the directions also. So it is suppose this is exposure E is the exposure. Then outcome is the O. Then if you draw a line directing from the E to Y, this become a directed graph. But it never comes back like this. So it is acyclic. There are different types of edges here. One edges could be fork. Fork means you will have something like like this. This is like a fork. This is from exposure or some variable. It is connected by a edge into another variable, and like this, two edges like a fork. Inverted fork is like it is the opposite of this one. That means there is a variable there. It goes to the from the outcome and exposure, suppose it goes to Z like this. So it is an inverted. So this particular name for the inverted fork is a collider. The name for the fork, one type of fork is confounder. We'll come to that later. Then there is another way edges can be occur is the chains. Chains means like this way. We have multiple chains in both directions. So we have the basic structure of how an edge and a vertex is formed. Now we connect the edges and forks with the variables we already assimilated with the help of literature review and from the expert opinion. Here we will have two kinds of pathways. One is a causal pathway. Actually, this is only the causal pathway in which we are interested. But there are biasing pathway which contains various confounders or colliders. Sometimes selection bias also, and measurement bias. These are the systematic errors that can be that may be there in the biasing pathway, and we can encode that in the biasing, but then we can find out those which needs to be adjusted and which need not be adjusted. That is the beauty of this DAG. Then there are some sufficient conditions whereby we can extrapolate the associational risk ratio or causal risk difference to a a causal thing. The first is associational. We have to convert those into causal risk ratio or risk difference. For that, we need to satisfy a few conditions like temporality, causal consistency, conditional exchangeability with the positivity, and no measurement errors, and in the correct target population is also very important. This correct target population is very important because we start with the target population, then we have a source population, then we take the sample from the study population. If there is a contradiction or some issue between or the study population doesn't represent the target population, we are left with the selection bias. Usually what we teach in our classes for understanding the selection bias is, suppose this is a X and this is a Y, and suppose there is no relation between this X and Y. So this is a target. Suppose there is a selective mechanism, selection mechanism through which the population sieves down, and what you get is something like this one. Then when you look at the X and Y, there is an association. So we may think that there is an association between the exposure or the treatment and the outcome if there is selection bias. So this can also be picked up easily with the help of your graphs. Then the various assumptions can be easily encoded in the graphs. This X and Y, this direction, the edges pointing towards the Y. This points towards the Y. There are 2 points here. One X occurs before the Y, and the direction is also encoded. So consistency also, consistency means the treatment is always consistent, and there is no difference in the treatment variation. Is a particular word we use is that there is no treatment variation irrelevance. It is also known in some parlance as stable unit treatment value assumption. Here, what we can do is to reduce this particular problem. What we can do is we can imagine the observational study as being conducted in a RCT. How we would conduct the RCT if we have a chance, but we are doing an observational study only, but we will imagine what we will do if we would have conducted a RCT. That particular method of thinking is called target trial. These particular things will take care of the consistency problem. Then comes the most important things that is encoded in the DAG. DAG means the dialectic acyclic set. This is exchangeability. For the RCT, exchangeability is very simple because we have a treatment arm here, then we have an outcome here, and here suppose Z is the set of confoundees. Actually, if you can break this pathway from the Z to treatment group, then we can easily have the causal pathway alone. That means we have to break this one, Z to X. So there is a X, there is a Y, there is an Z. Z is a confounding set. So if you can break this XY axis, that means we are left with only one causal pathway. This cutting is made possible by the randomization. This is also called the assignment mechanism. But this is possible with the RCT only. But the beauty of the DAG is, or counterfactual theory is, if we can implement the conditional exchangeability, then we can actually do that. The conditional exchangeability, we all know that is for that it is actually we do the conditioning of the variables. So if the Z is conditioned, then actually we can have some kind of exchangeability. There's a conditional exchangeability in observation studies. Here in RCT it is possible with the randomization, but in observation study what we do is there is something called de-separation or backdoor criterion. It essentially results in conditional exchangeability. So when we attempt the conditional exchangeability, there is one problem. Sometimes we may left with no cells in the columns. It's called a stochastic positivity. Sometimes there is a situation where suppose when we condition on a particular Z, here Z is a set of confoundees. Suppose he is a pregnant, Z is on pregnant or not, and once we condition, then we are left with only pregnancy or that. That means there is no pregnant woman in our data set, in our condition DAG. So that is a problem because the positivity is not satisfied. Then what we do in that situation, this all occurs before the study design. Then what we do, if you think of that particular situation, when we write the protocol, we exclude the pregnancy. Now we come to this is only the theoretical basis of how we do it, but actually doing it is very simple. We just draw a model. That model means model based on the theoretical knowledge and the consensus. We have already got all variables. We have the question clear, everything clear. Now we can draw the model in a paper. That is what we used to do before we started doing the DAG. Initially, we depended on I will come to that later. How we can have this conditional exchangeability in the algorithmic way, but manually. But now we have a lot of packages, and the packages one can use is GGDAG, DAG, or DAGSim. But we have an in-house packages. I have developed my own packages. We use that. And we have Python. There is Python package for that. One is causality, other is a causal info, also do-why, and there is a Julia package also. We are in the process of assorting a Python package and a Julia package and an R interface for the Julia at present. And here are the rules. How we can accomplish the what you call conditional exchangeability, leaving only the causal pathway, blocking all biasing pathway. So our aim in a DAG is we should be left with only a front door. Front door means there should be an arrow only from treatment to outcome, or from X to Y. There should not be any connection between Z and X or Y. So we have to break that thing. How we can do that? There are some rules written by put forward by Nigel Herman or the UDAPL. The 4 rules are there. First rule is delete all arrows that begin at the exposure. Then locate the path which begin with an arrow into the exposure, then end with an arrow into the outcome. Then the third category is the third thing we have to satisfy is each backdoor path decide whether the path is open or closed. Paths are open unless there is one or more colliders. We'll discuss that everything when we demonstrate this. They contain one or more colliders, or we have not conditioned on those colliders. It's very important. If you collider in a pathway, backdoor means the pathway that not in the main pathway we are interested in, the other pathway involving the Z and other set of variables. Here If there is a collider, it is actually blocked. That path is blocked. There is no biasing pathway. But if that Z contains a confounder, that means it is open. There is a backdoor path open. That means information can flow from the X to Y, not only through the front path, but also from the back path. So what we get as the average causal effect, associational causal effect will not be equivalent to the average causal effect. That is what we get is a marginal effect. So we have to cut the connection so that we will be left with only with the front pathway or the real causal effect. This can be accomplished with these four principles. Then the last condition is all open paths are considered as confounding path, and all variables on such path are considered confounders. Actually, the confounders can be considered as a set of variables containing A, B, C, like that. So usually what we used 10 years back was we will be conditioning every confounder, all covariates that occur in the that we are aware of. But actually we don't need to condition or control all these variables. There are a minimum set of variables, actually more than one or two minimum set of variables that we can come up with. Each set of variables that can be adjusted, that will not contain all possible covariates. That is only a minimum sufficient set. This can be one or two. If there are more than one, means there are two pre-specified models. But actually at present there is no need to do it manually, but it is better always when we start doing it manually. We used to do it manually actually with various replicas on a table. So we arrange everything like a chessboard, then we will find out the result. But with the algorithms it is very easy to do that. It can be implemented with the help of packages. Now we go on to the how we can implement that in the packages. Here we today we used a R only. Here it is an R notebook. We usually use R notebook. That we load the package ggdag, and you can actually load DAG-R, or there is another called DAG-SYM. Suppose DAG-SYM is very useful. We will be discussing it the last part of the discussion. Then once we then how we can create the DAG. There is a particular function known as DAGify. DAGify create the DAG for us. So the symbol DAG, the representation of symbol. So suppose this is X is a exposure or the treatment, and this results in a Y or outcome. So how you draw this? The equivalent function is DAGify Y tilde X. Exposure, we define the exposure X and we define the exposure Y. Then we can use the ggdag. A lot of function is there, but we have our own function so that it become just on sentences. When we run the function causal model, we will get the visualization. We will get the minimum sufficient set of adjustment variables needed. We will get the front door, we will get the back door, and everything. So what we get will be like something like this. I think you can see this here. X is the exposure variable that is written here. Then you have an outcome variable. Actually there is only, this is a causal pathway because there is no other set of confounders here. So we are left with only this. So here the marginal model itself is the final model. Now in the same function we will be dealt with something, we will be having something called de-relationship. This is very important. De-separation. There is a word called de-separation. De-separation means conditional exchangeability. This is similar to our statistical independence. Statistical independence is encoded in the graph at the de-separation. So this is a colored. So we have easily colored that with the red and white. If there is a G connection, means G connection can occur in the front door. X and Y, this is the front door. Back door means anything other than this is a back door. We are not interested, that is a back door. Front door is what is we are interested in. So here it is only the front door, because there is only one arrow from the X and Y. So it's a simple thing. So we don't have to adjust anything. This is how we created DAG. Then open path also, there is only one open path, that is from the X and Y. Then adjustment, any adjustment needed? No adjustment needed because there is only one path. Then backdoor, then we have another function which actually tells you whether we need to create any, we need to condition any particular variable, and that we return backdoor path unconditionally closed. That means there is no need for anything because there is only two variables, x and y. Now we see another situation where there is a confounder, only one counter. No, usually when we say confounding, we will be considering a set of variables, set of confounders. But here we have only one set. So here the code is very simple. Here the GG DAG, the beauty of GG DAG is you can easily encode that with the, as you usually do in a modeling, in a regression like that. The Y here become outcome, the tilde become tilde, you have the exposure, all things are almost similar to our GLM function. There is here it means outcome tilde exposure and confounder means there is an arrow from the exposure to outcome and there is another arrow from the confounder to outcome, and there is another arrow from confounder to exposure. This is what we have the typical confounder. But when we encode that, when we have the visualization, we'll understand better, and we define. This is how we get. See, this is the x exposure, this is the outcome, and there is a directed arrow from the x to y. So this is the front door, or this is an actual causal pathway we are interested in. And there is a back door here. This back door is a confounder. There is a single confounder with an arrow from the confounder to the outcome and the arrow from the confounder to exposure. This is very important. This the definition of the confounder is that it should satisfy three conditions. One is it should be associated with the outcome unidirectly. It should be associated with the exposure unidirectly. That, or in another way, it could be a causal factor of both outcome and exposure. And it should not be in between the exposure and outcome. That means there is another possible DAG. There is a XY, like this X, M, Y. What happens in X, M, Y? Here, the problem is M is a mediator. We call it mediator or intermediate variables. When we previously there was a very good article on mediator, that is a Baron Gillis. At present, but we use the DAG to decide how do we analyze the mediator, etc. Okay, now confounder is over. Now now whether we have to adjust the confounder or not? Yes, we have to adjust it. See, this is a dark in color. And it is unadjusted. That means we have to adjust that. The same path. Now, in the last figure, the function will give everything easily. The last figure, it will even tell you what we need to adjust is the confounder alone. But this is easily imaginable from the simple DAG itself. We don't need an algorithm. But the algorithm is needed when you have a lot of variables, as in the last example, DVT. And confounder example here, suppose here we took the confounder as the age. Now we go into collider. Now we go into collider. Collider is actually what you mean by collider is there is an X, there is a Y. This is a front door we are actually interested. It's a causal pathway. Sometimes there may be some Z, or we call it M, or we call it C. Suppose it's a C. There is a C here. There is a C here. This is a collider. Here the difference between the collider and the confounder is actually collider is the progeny or the child of X and Y. So the arrow is reverse. It's an inverted fork. So here it is very important that we should never condition these variables. Unless we draw a DAG or we think counterfactually, we will be conditioning on a collider. So collider identification very easy with the DAG. There is another situation where the collider means there is actually the path is blocked. You know, if you see to the C, there are two blocking pathways. This comes and meet together, these two edges. So this is already blocked. This is already blocked. There is no connection. But if we condition on this, and what happens? If we condition on this, what happens is this become open. That means we are biasing the pathway. This usually happens in selection bias. Actually, selection bias is a kind of collider condition. So collider condition is for the short form for the how you represent collider is conditioning is by square. Variable is represented by round and a square is by the conditioning. So if the collider is conditioned, actually the path is open. Selection bias is a typical example of the collider condition. Then similarly, we have another. So here there is a collider, and when we whether we have to adjust the collider or not, that is easily understandable from this particular figure. Backdoor path is unconditionally closed. That means we don't need any kind of conditioning on a collider. This is actually given by the function. See, there is no. It is also there is a deseparated. This is actually deseparated, unadjusted, and adjusted. There is no need for adjustment. Now. Then there is one more variable that can come in. That is a mediator or intermediate variables. Intermediate variables. When we discuss the intermediate variables, is a x from the x you have a mediator. It passes to the mediator. Then it passes to the. Y. So actually, this is there may be some biological mechanism through which the X act on Y. So actually, there are two kinds of effects. Here, there could be the effects could be X to Y, and it could be due to, through M to mediator to Y. So there is a direct causal effect. There is an indirect causal effect. Most often, unless we are studying the mechanism by which the Y is caused, we will be taking both together. That is a total effect. Total effect is actually the effect passed through the mediator as well as the direct effect. So unless we are studying the mechanism, we will never do mediation analysis. So then another one more thing we have to discuss, that is an instrument variable. Instrument variable is also.
Excuse me.
Yes.
Time is running out. Can you?
Okay, I will stop now. We'll stop now. Just
conclude. Can take 2 more minutes. Okay.
Just okay. So there is an actual implementation of a variable we will show. So this is a DVT study. The question was, there is an actual association between DVT, COVID and DVT. That means the COVID results in DVT or not. We draw the DAG and we use the implementation DAG implementation for finding out the causal pathway. And we are this is a pathway we got, and the minimum adjustment set what we needed was this one. There are two models we got. Two models are this one. That means we have two models. One model is age, cancer, sex, smoking, and steroid injected. This is one minimum sufficient set. Another minimum sufficient set is age, immunocompromised, sex, smoking, and steroid. So we have two pre-specified models. This pre-specified this we will be considering at the time of modeling. And now what we do is we have the preconceived a priori models or model. Then what we do is we simulate the data. We have the all variables needed. We simulate the data. We create an Excel. From the Excels we do the analysis also. We follow literate programming. That means we write all codes, run the simulated data. We come out the results. We come out the tables, figures, everything. At the time of protocol submission to the ethics committee itself. Then we take the data. And when we take the data, do the study, then we do the analysis. Actually, we had already created the model, pre-specified models, then even the simulated data. We have analyzed the data with the simulated data. We have created the tables, everything, and we have the code ready. At the time of the actual data implementation, we just need to run the study. This is the way we conduct studies at our department. Thank you. I think. Hello? Yes.
Okay.
I think I stopped. I stopped with this. There are some other slides. Okay, I will stop.
Okay. Actually, it is interesting. Anyway, we don't have much time.
Okay, I can understand.
So it was quite interesting. Now, a very quick question from the audience. Anybody want to comment or put a question?
Actually, there are very good studies, very good courses conducted by our Jason Roy, Dr. Jason Roy. He is here. There is a course by him in Coursera and all. There is a very good course.
Okay. Any question? Okay, Dr. Yadav, thank you very much for your excellent talk. We all enjoyed very much, and actually would have given some more time for completing the talk.
Okay.
But we have other session also. Okay.
Okay.
Thank you, Doctor, so much.
Okay. Okay.
Okay, Doctor. So I would like to thank Dr. Sadish, co-chair, Dilip, and all the organizers for giving me a chance to chair this session. Also, I would like to thank both the speakers, Dr. Anil Matthew and Dr. Yadav, for their excellent presentation. Thank you all.
Thank you, professors. Thank you, Professor Anil Matthew and Professor Yadav, for your wonderful presentations. And in fact, our students are very much interested because how the statistics works in the medical area, and very motivating things are there. In fact, we need more time in that respect, but we are tightly scheduled. And anyway, let us find some time in future. Professor Yadav.
Okay, thank you.
Yeah, thank you so much. Thank you so much. Yeah. Thank you, Professor Malaya. You are for chairing this session in a nice way and strictly following the time schedule and helping the other organizers in a great way. And also Dr. Dilip to support Professor Malaya sir in doing everything in a neat way. Once again, on behalf of the Department of Statistics and in the ISPS, KSA, etc., I wish to extend our gratitude to each of the professors. Thank you so much. We expect your support in future also. Thank you all. Now let us move to the next session. The next session is a special invited session from on the current innovations in statistical methods and their applications that also related to a medical field, biostatistics and related areas. And this session is in fact organized by Professor Jaya Sadagopan, an associate of our, in fact, regular, our associate of our department and a well-wisher of our activities. And we are always grateful to her. A team, gigantic team, in fact, with her. Let us invite them for this session to chair. We have our Professor Joniskaria is here. Welcome. And Dr. Subha to support the chair as the co-chair of the sessions. Once welcoming each one of you, let us, Dr. Subha, please take off.
Thank you, sir. So actually, welcome.
Please.
Thanks. So welcome all of you once again to the special invited session on the topic current innovations in statistical methods and their applications, which is organized by Dr. Jaya Sadagopan, ma'am. So First of all, I like to say that I'm extremely happy to be a part of this session because Professor Jaya Sadagopan is actually, as Sir correctly pointed out, is a continuous associate of our department, and we are extremely happy to have you, ma'am, here. I would like to introduce the session chair of this, session. Professor Joni Sakriya, sir. He's a retired professor of Nirmala College, Department of Statistics, Nirmala College, and an alumni of our department as well as Cochin University of Science and Technology. He's a person who is continuously interested and involved in active research. And we welcome you, sir, on behalf of the department. And I request you to take over the charge as the chair of this session. Welcome you, sir.
Thank you, Shubha, for the nice words. First of all, I congratulate Professor Satish and team for organizing such a wonderful 4-day international webinar. I also thank Satish for inviting me to chair the special invited session. And this session, the theme of the session is current innovations in statistical methods and applications. I hope this session will give more insights to the applications of statistics in biology. And we have 4 speakers in this session. First speaker, Professor Jason Roy. Second is J.M. Sadagopan. And Gray Vivian Lee and Zoimer Rivera Nunes. These professors are from Rutgers University, State University, New Jersey, USA. Okay. The time allotted to each talk, the maximum time maybe 25 minutes and 5 minutes to the interaction session. Let us start with the discussion. The first topic is, first invited speaker is Professor Jason Roy, and the topic of discussion is Bayesian non-parametric inference for causal effects of meditation. I invite Dr. Professor Jason Roy to deliver your talk. Okay.
Dr. Subha, whether to anything?
I think we can go for the talk, sir, because yes, okay. Yeah. Welcome you, Professor Jason Roy, for the talk.
Great. Thank you. Namaste and happy National Statistics Day. And really thanks for organizing this really engaging program. It really looks great and I'm very happy to be a part of it. So let me, if there are any problems seeing these slides, let me know. Hopefully you see my title slide right now and hopefully you can hear me well. Okay, great. So I'm Jason Roy and I'm a professor of biostatistics at Rutgers School of Public Health. And you can see my email address if anybody has questions or wants to reach out. I'm always happy to discuss any of these topics more or be involved in collaborative research. So I'm going to cover causal mediation, and just to sort of ground you in sort of the main idea, what we're going to be thinking about here is situations where you have some treatment that I'll call Z, and some outcome that Y, and our interest is then in how much does Z affect Y directly versus how much is Z affecting Y through its impact on some mediator, some intermediate variable M. So Z is like maybe treatment, and treatment could affect the outcome directly, but it also could affect it indirectly. It could impact some intermediate variable M, and then affect the outcome. So this would be an indirect effect of Z through M, and this would be a direct effect. So we might be interested in both of those. And then there could be some kind of confounding between M and Y. There could be other types of confounding, but we could imagine, right now we could imagine, like, let's say we're randomizing treatment, but then there could be confounding between M and Y. So that's one example, but we certainly also could have confounding over here. So that's sort of what it looks like in a picture. So as notation, as I mentioned, we'll have an outcome Y, a mediator M, treatment Z, and then possibly some confounders X. And then we imagine that we've collected data on N subjects. So our data is this collection of X, A, Z, and Y. I'll give you a hypothetical example, and then I'll give you a real example later, but I think the hypothetical example might be helpful for thinking about what we're talking about here. So, there's this notion of risk compensation that you might be familiar with. It's common in the, in the economics literature, they talk about risk compensation. So I'll give you an example of how risk compensation is really a mediation question. So imagine that we're interested in like whether bicycle helmets, let's say having a bicycle helmet law would be beneficial. So it could be that a government is thinking about, should we require people who ride bicycles to wear a safety helmet? And so that's a causal kind of question. If we did have that kind of a law, would it improve the health of people? In other words, maybe your outcome is concussions, and would requiring people wear helmets when they ride a bike decrease the rate of concussions? That would be the sort of hypothesis. However, there could be an intermediate variable which has to do with your bike riding behavior. So if you're wearing a helmet, maybe you ride a little faster, or maybe you take more risks because you feel safe, right? So it could be that wearing a helmet affects your behavior, and this is the risk compensation idea. So we might want to know, what it would be the overall impact of this law that requires people to wear a helmet, and we would call that a total effect. But we might also be interested in sort of the direct effect, where we sort of, in some way, kind of controlled for the bike riding behavior, sort of made that not impacted by the treatment itself. So what would the impact of the law be if it did not affect the bike riding behavior itself? So that would be a direct effect. So we might be interested in both of these things. So we want to figure out, okay, how can we get at that from data? You could imagine that even if we're randomizing Z, there could be confounding between M and Y, because the types of people who maybe might ride, take more risks when they're wearing a helmet might also have already a priori been at higher risk for a concussion or something. So there could be confounding there. There could be, and then, there could be, like age, for example, could be a confounder between M and Y in this case. You could imagine there might be differences by men versus women, all kinds of different things. So there could be confounders here. So we want to figure out, have statistical methodology that would allow us to estimate these kinds of effects. So we're going to get at what are known as natural, direct, and indirect effects. And I'll talk about what natural means. So first, we're going to need some notation. So I'll use potential outcome notation, and I'll kind of walk you through it. So first of all, we could think of having potential outcomes on the mediator. So I'm going to use a superscript for potential outcomes. So this notation, M with the superscript little z, would refer to the value of the mediator that would be observed if we were able to set treatment to value little z. So if little z is 1, for example, that would mean, what would your mediator value do if you wore a helmet? So in other words, what would your bike riding behavior be like if you wore a helmet? And M0 would be, what would it be if you didn't wear a helmet? And for what we'll make this consistency assumption, which just says that our observed mediator is exactly the same as the mediator under the actual treatment, capital Z here, under the actual treatment received. Then we can also have potential outcomes for our outcome itself, but those are going to be superscripted by both treatment and the mediator. So it gets a little more complicated, but we can still kind of read it off. So this specific thing here is the outcome that would be observed if treatment was set to little z, and the mediator was set to the value that it would have taken if treatment was set to some value z prime. So you'll see that the outcome depends both on treatment and the mediator value. In our example, whether or not you're wearing a helmet and your sort of how safely you ride your bike. So it depends on both of those. And again, we have this kind of consistency assumption where we map our observed data Y to what we really see, the outcome when treatment is set to capital Z, which is what we actually observe, and then the mediator is set to capital M superscript Z, which is what we actually observe for the mediator. So that's how we're mapping potential outcomes to observed data. So in our example, I sort of mentioned this already, but what is your bike riding behavior if there's no helmet law versus what's your bike riding behavior if there is a helmet law? And you can imagine, let's think if there's some way to sort of quantify bike riding behavior. Maybe you have a scale of 1 to 10 on how safely you ride. Now we can do the same thing. We can sort of think about what each of these means in terms of our specific example. I'll go through like 2 of them. So this first one, Y0, M0, that would be your concussion status. Concussion is your outcome. If there's no helmet law, Z equals 0. And if your riding behavior is what would happen if there's no helmet law. Okay, so you're riding your bike just as if there was no helmet law, and you're also not wearing a helmet because there's no helmet law. Okay, so that's that. You could look at the second one here, which is concussion status if there's no helmet law, but you ride as if there was a helmet law. Okay, so maybe you're not wearing a helmet, but you're still riding your bike as if you were. Okay, so then what would your concussion status be? So you could go through each of these. So then we could get at what are known as natural direct and indirect effects. So this is a natural direct effect right here. We're contrasting 2 different outcomes, 2 different potential outcomes. So this is, and first notice that this expectation is over the whole population. I'm not conditioning on anything. So this is a population average. And what we're contrasting then is your outcome if you wear a helmet versus if everybody wears a helmet versus if no one wears a helmet, but everybody's bike riding behavior is set to what it would have been had nobody been wearing a helmet. So we're sort of we're fixing our bike riding behavior at what we're calling its natural value, the one that would occur if the state didn't intervene, if there was no helmet law. So what would your bike riding behavior be if there was no helmet law? We're assuming, what if everybody was doing that, but some people were then wearing a helmet and some weren't? Okay, so you can hopefully see that this is isolating the impact of the helmet law, because it's sort of it's basically saying everybody is going to ride their bike as if there was no helmet law. So we're going to isolate the impact of the helmet. So this you could imagine is something you would want to know. So this will get at the direct effect of the helmet law. So there's also what's known as natural indirect effects, and that would be kind of the opposite situation where we're saying, well, what if there's a helmet law? But then we're contrasting your bike riding behavior under a helmet law versus not under a helmet law, and then comparing concussion status. So here you could imagine everybody's maybe wearing a bicycle helmet, but some people's behavior has been altered by that. I mean, we're imagining what if everybody's behavior was altered by that versus what if nobody's was, and then what would the concussion impact be? So that would be getting at the indirect impact of this helmet law. So if there is an indirect effect, it could be that the bike riding behavior, the change in bike riding behavior maybe impacted the risk of concussions. So that would be the indirect effect. So right now we're not thinking about how to estimate this yet. It's just we're imagining this is something that we want to know. So our first step in setting up these kinds of causal problems is to identify estimands of interest. And that's what we're doing. So what we're saying is we want to know this natural direct effect. We want to know this natural indirect effect. And we also then can get a total effect. And the total effect is actually just the sum of the natural direct and indirect effects. You can quickly see the math there that it works out. This total effect is just the usual average causal effect, just isolating treatment. And here treatment is just the helmet law. So this does not take into account people's bike riding behavior. It just says, if we pass a bicycle law, are people better off in terms of concussion risk? And that is a decomposition of the indirect and direct effects. Okay, so this is just what we want to know. We would love to know all of these things. And then the question is, what kind of assumptions do I have to make to be able to identify that from data. And then how can I actually sort of go about the estimation process? So we're going to look at both of these things. But one thing to note is that these natural direct effects have one thing that might make you uncomfortable, which are what are known as cross-world counterfactuals. So we have to deal with cross-world counterfactuals to when it comes to natural direct and indirect effects. And one example of a cross-world counterfactual is this one, where we're looking at the outcome under treatment, but where the mediator is set to the value under no treatment. So there's no world in which this actually exists, so it's a little bit tricky to think about, in our case. What would the concussion status be if people were wearing a helmet, but they were riding their bike as if they weren't? So it's kind of a thought experiment where we're imagining, what if we could put a helmet on people, but they didn't know it, something like that. What would be the risk of concussion? So at least you can imagine what that would be, but there's not going to be probably any world where we can really make that happen without some sort of clever tricks. But so that may make some people uncomfortable with these cross-world counterfactuals. But if you're, but you can also, that's kind of the kinds of problems you're kind of stuck with causal mediation is you have to imagine being able to sort of manipulate these two different things. And you're going to get some subgroups for which, that's not really something that you observe in practice. So then the question is, how are we going to identify like a mean of this thing? Okay, so we're going to have to make some assumptions. So in our paper that this talk is focused on, we identified a couple of different sets of identifying assumptions, and you could pick whichever ones you're more comfortable with. But here's the more standard set of assumptions that people make, which are what's known as sequential ignorability. And what this is really just, what you could kind of think of this as saying is that essentially we have treatment being randomized given confounders. If we have an actual randomized trial, we don't really need to condition on X here, if Z is actually randomized. But this first one is saying that treatment's randomized, so it's independent of potential outcomes, potential mediator values. Oh, sorry, these should be superscripts. I changed to subscript, but these are superscripts. The second one here is saying that the mediator is randomized. When we say the mediator is randomized, it's sort of saying independent of the potential outcomes here, but conditional on confounders and treatment status. So what we're imagining is we've collected enough confounders that you could think of the mediator now as being randomized. So that would be one set of identifying assumptions which will identify the natural direct and indirect effects. In our paper, as I mentioned, we proposed an alternative set of assumptions that you could make to identify the causal effects. So the nice thing is the identification problem is kind of separate from the statistical problem, which we'll see. Right now, we're just thinking about how we can identify the causal effects, but we're not really thinking about estimation yet. So these set of assumptions will identify the causal effect. Now, the most common thing that people do for mediation methods is they just fit a couple of parametric models. So for example, you could have a regression model for your mediator conditional on confounders and your treatment. So something like this, a linear additive model. And then you could also fit a separate regression model for your outcome given treatment, mediator, and confounders like this. And then it turns out the natural direct effect is exactly this thing here, theta 1 plus theta 3 times beta 0 plus beta 2 transpose x. You could prove that, it's not too difficult, by combining it with this assumption and the consistency assumptions that I mentioned earlier. You can actually prove that the natural direct effect is exactly this. So the nice thing about this is you can just sort of fit these two models and combine these regression coefficients and you'll have a natural direct effect. And you can do the same kind of thing with a natural indirect effect. So that's fine. But the problem is that you've now made some additional assumptions. So for causal problems, we're stuck with making some causal identifying assumptions that you can't check from your data to see whether it's true. These are just assumptions that you have to make about the underlying process. So we're already stuck making those. But if you also fit parametric models, you're making additional modeling assumptions. So now you've made statistical kinds of assumptions, and you've also made causal assumptions. And so there's multiple ways you could be wrong and have bias. So what we want to do is say, we still have to make these causal assumptions, but let's not make the modeling assumptions. Let's be very non-parametric about these models. So we're going to use a Bayesian non-parametric kind of approach for the observed data distributions that we need. And specifically, we're going to use a Dirichlet process mixture model, but there are other Bayesian non-parametric methods that you could use. So I'll show you what we specifically used, but first let me show you the identification. So the most difficult thing to identify is this one, these kind of cross-world counterfactual potential outcome thing here. And you can show from the sequential ignorability assumptions and the consistency assumptions that in fact it's exactly this here. So, and this is all only involves observed data. You'll notice there's no potential outcomes here. And hopefully it's kind of intuitive, right? Because this is the outcome if treated, but the mediator is set to its value under no treatment. Well, to get at that, what we need is this regression y given the mediator, given treatment set to 1, right? Treatment, the outcome is under treatment. But we need the mediator to be under its value if there was no treatment. So what we do is we integrate over this mediator distribution, but it's a mediator distribution under no treatment. So what we're basically saying is, using our observed data, we can learn about the relationship between y, m, and z, and x here. And then we can average that over the distribution of the mediator under no treatment. And we can learn about that distribution, right, from the people who weren't treated and have these values of x. So we can learn about this distribution, and then we can do this integration. So the point here, so the thing is now, all we need is we can be non-parametric about this thing, we can be non-parametric about this thing, and then we can compute this. That's what we're going to do. So here's our actual Dirichlet process mixture model that we used. These obs here just means the observed values of, and not the mediator, not the potential outcomes, just to be clear. So we have our observed y's, our observed m's, our observed x's. We take this joint distribution and we say this is it's normal. We could weaken this assumption if we don't have continuous data with some mean mu, some variance, covariance sigma, but you'll notice that there's an I here. So every person has their own parameter. So that makes it non-parametric. The number of parameters grows with the sample size. So it's really, you can think of it as infinite dimensional kind of parameter. But then we put a prior distribution on this thing, and we say, so the mu and sigma have some prior g, and then g follows the Dirichlet process. And then what that means is that, so because the Dirichlet process, is a discrete kind of distribution, what you'll end up with is basically ties or clusters. And so even though we're allowing each person to have their own, mean and covariance, ultimately when we fit this, because we're specifying a Dirichlet process, it's going to say, well, some people have the same values of the parameters. So we'll end up with a mixture of normals for this. So it'll be essentially this is an infinite mixture of normals, but in reality, in any given step in our algorithm, it'll be a finite mixture model. But the key difference is, compared to finite mixture models, is we're not saying how many mixture components. It's really unbounded how many mixture components are needed. And when we do MCMC, these Bayesian methods, in fact, the number of clusters will change, iteration to iteration. So you could think of this as roughly an infinite mixture. So it's really this can handle any shape distribution. So then once we fit this, we use MCMC to actually fit this. So then we can actually compute this thing. We can approximate this thing. So what we do is we draw all our parameters using Markov chain Monte Carlo. Then now I have then basically at any given step in MCMC, I know the parameter values, so I know this expected value. I know this distribution. I can use numerical kind of integration to actually compute this thing. And I can do that at every step in the MCMC. And because of that, what I can do is I can do MCMC, I can save all the parameter values, and then I can run this numerical integration in parallel. Because I can just store my parameter values, and then I can use parallel computing and get a whole bunch of values of this and store it. And then I can summarize the natural direct and indirect effects, using the posterior, as a posterior distribution. I can, I'll have thousands of values of the natural direct and indirect effects. So I'll have a posterior distribution, and I can summarize it in the usual way. So we did some simulations. I'm not going to go into details just because of time, but here's one example where we assume the mediator was from some skew normal distribution, and our outcome, was a normal distribution, but it had a bunch of nonlinear kind of terms in the regression. So it was so we generated data from the kind of model that it would be hard to get right if you were doing parametric modeling. And so over here are the results by fitting a parametric model, and here's the Bayesian non-parametric version. And what we saw is that, as expected, is that we basically, with the parametric models, we had a fair amount of bias. This is natural indirect effect, natural direct effect, total effect. And really the total effect, well, is I don't might not be as hard to estimate, but these you would expect to be quite a bit off. And so we saw quite a bit of bias with the parametric models, and much lower bias with the non-parametric. So that did basically what we kind of expected, is that we're able to estimate these effects pretty well, even when the data generating situation is kind of complicated. And we did a lot more simulations, but this is just one to just give you the main idea. So what I'll finish up with just a real data example. And so these are real data that we use to implement our methods. So there was a randomized trial that was looking, and the goal was to increase physical activity among sedentary adults. So they randomized people, so this was a real randomized trial, they randomized people to an intervention versus a control. The intervention had to do with delivering individually tailored messages to individuals. So they're getting tailored messages, basically kind of, encouraging them to exercise and to be more physically active. And so the one question was, does that help in terms of people actually exercising more? So our outcome is, how much do people actually exercise? But they hypothesized that there might be a mediating process and intermediate variables here, which they refer to as behavioral processes. So these could be like strategies that make it more likely to exercise. So for example, one of the things they asked about was a question like, I reward myself when I exercise, or I have someone who provides feedback about my exercising. So this could be a friend or something who is encouraging them. And maybe they put things around their house to remind them to exercise. Maybe they have sticky notes, and it's like, don't forget to exercise today. And so the idea would be that these tailored messages might sort of affect how many of these behavioral processes you're doing, and that might affect how much you exercise. Or maybe the intervention is not really affecting these behavioral processes, but is more directly affecting the outcome. Okay. So they were interested in how much is direct, how much is indirect.
2 minutes more, Professor.
Okay, I'll wrap up. Thank you. So they were interested in direct and indirect effects. Let me scroll here. I just wanted to show you, these are the actual, these are draws of the blue, which you might not be able to see, but those are the ones that is the outcome distribution, minutes of exercise. You'll notice there's a big cluster at 0. And then the reds are our draws from our model, from our Bayesian non-parametric model. And you'll see that even though we did not tell it that there's, a cluster of outcomes at 0, it figured it out. It's a non-parametric model. And so you can see that we actually fit the data really well, even though we didn't give it any instructions that the data look like this. And then we found some results where we saw that we reported the natural indirect effects, direct effects, and total effects for different age and BMI categories. And we saw that the direct effects seemed to be a direct effect for the higher age groups, and people who have lower BMI. So you could sort of, we could look at this in more detail in the paper, but we did actually implement this and look at the direct and indirect effects in a variety of situations. So kind of to wrap up here, causal mediations often of interest. You can use non-parametric methods to model these observed data distributions. And if you do that and then have causal assumptions, then you can actually compute direct and indirect effects. So you don't have to use parametric models. We also use informative prior distributions for sensitivity analyses around some of the non-identified parameters, but I didn't go into details about that here, but you could look at it in the paper. We're currently working on high dimensional mediation problems and mediator selection, like in microbiome kinds of problems, where you have maybe hundreds of thousands of mediators, and how do you select them? So here's some acknowledgements, collaborators. We do have an R package called BNP Mediation that will do this. And this is the paper that appeared in Biometrics that most of this was based on. So thanks. And if there's time for questions, I'll take them. Or if there's time after, that's fine too.
This is time for interaction. 1 minute. If you have any question, please ask or a comment. Okay, thank you, Professor Jason, for a wonderful talk on the causal effects of mediation. Very nice presentation. Dr. Shubha, please introduce the speakers.
Yeah, sure. Sure,
The topics.
Yeah.
They are from the same institute,
Yeah.
Rutgers State University, New Jersey, USA.
Yeah. So thank you, sir. So once again, thank you, dear Professor, for the very informative session on Bayesian non-parametric inference for causal effects of mediation. Before moving on to our next speaker, let me say or share some facts regarding our earlier speaker, that is Professor Roy. Professor Roy is actually a well-accomplished academician in the area of statistics and biostatistics. He is currently a professor of biostatistics and the chair of the Department of Biostatistics and Epidemiology. He is the director of Rutgers University Biostatistics and Epidemiology Services and the co-director of Biostatistics, Epidemiology and Research Design Core, NJACTS. Previously, he was professor of biostatistics in the Department of Biostatistics, Epidemiology and Informatics at the University of Pennsylvania. His research interests include methodological research in developing flexible Bayesian methods for large observational studies, especially data from EHR and mobile health. He is particularly interested in causal inference problems where Bayesian non-parametric methods can be used in conjunction with G computation. He is also interested in functional clustering methods, which can be very useful for extracting features from intensely collected data. Much of his collaborative research is in pharmacoepidemiology. With a number of articles to his credit, he is actually the associate editor of the journals Statistics in Medicine, Statistical Science, as well as Biometrics. He has received a number of awards, including the Excellence in Research Award from New Jersey Health Foundation in 2019. He's a fellow of the American Statistical Association and has received the David P. Baer Young Investigator Award from ASA Biometrics section. We are extremely privileged to have you among us, dear Professor, and we thank you once again for sharing your work with us and for being a part of this webinar. Once again, on behalf of the University of Kerala, the Department of Statistics, as well as the organizers of the webinar, I extend our heartfelt gratitude to you. Thank you. I would now like to go to our next speaker, which is Professor Jaya Sadagopan. Actually, I'm extremely happy and delighted to welcome you, Professor Jaya Sadagopan, for this session. She's actually the organizer of the session. Currently, she's a professor in the Department of Biostatistics and Epidemiology and the interim associate dean for faculty affairs. She received her PhD in statistics from the University of Wisconsin-Madison. Her research focuses on statistical genetics or genomics with applications in cancer epidemiology and tumor biology studies. Her research topics include cost-effective study designs for genome-wide studies, estimating the lifetime risk of cancer in mutation carriers, dimension reduction, and Bayesian shrinkage analysis methods for evaluating multiple disease risk factors, and methods for evaluating gene exposure interactions. She recently completed a master's degree in science communication and public engagement from the University of Edinburgh. She is establishing the Rutgers Center for South Asian Quantitative Health and Education. The center will study the risk of cancer and allied diseases and determinants of risk in South Asian communities and develop health communications aimed at promoting cancer prevention, control, and care in these communities. She has also a number of publications in various areas of biostatistics, and she has developed methods for evaluating additive statistical interactions between biomarkers and treatments in relation to time to event endpoints, and applied these to digitally extracted data from phase 3 cancer trials of metastatic melanoma and metastatic colorectal cancer. She is she is a member of the editorial board Genetic Epidemiology, the program chair-elect, section on teaching of statistics in health sciences, American Statistical Association, member of the board of directors, International Genetic Epidemiology Society. She is also the elected fellow, American Statistical Association, and an elected fellow. She's an elected fellow at the American Statistical Association. More than that, she is a well-wisher of our department and an associate. And actually, the University of Kerala is also going hand in hand with Rutgers University in her projects. We are delighted to have you here, ma'am. And I hand over the mic to the chair for welcoming you for the next talk.
We are lucky to hear such a wonderful personalities. Next speaker is Jaya M. Sadgovan. Her topic on Bayesian penalized regression methods for matched case control data. Madam, please.
Thank you. Let me share my screen. Are you able to see my screen?
Yes, yes.
Yeah.
Thank you. So I'm presenting from two screens. So I will be looking at the slides in one screen and answering questions on the other. So if I turn my face away, it's not because I don't want to see you or anything. It's just I'm using two screens. So first of all, hello everyone. Good evening and good morning to people from different continents. And many thanks to the webinar organizers for the opportunity to organize this session. And also congratulations to the conference organizers for organizing an engaging program. Today, I'm going to share with you some results on Bayesian penalized regression methods for matched case control data. This is a joint work with several colleagues, and I also want to acknowledge funding support from the National Institutes of Health. I will use a motivating example to put the work in context. First, non-Hodgkin's lymphoma is a type of cancer that originates in our lymphatic system that helps our body to fight germs. Here, I consider non-Hodgkin's lymphoma in general without focusing on a specific subtype such as diffuse B-cell lymphoma or follicular lymphoma. So I will focus on non-Hodgkin's lymphoma as a whole. An important risk factor for this disease is exposure to chemicals, which is a strong environmental component for this disease. Certain chemicals used in farming to kill insects and weeds can increase our risk of developing non-Hodgkin's lymphoma. One class of chemicals that is suspected to increase the risk of this disease is called polychlorine biphenyls, also known as polychlorinated biphenyls, and abbreviated as PCBs. PCBs are man-made chemicals. They are used widely in farms before 1979, but their use has since declined due to their established environmental toxicity. But because of their continued presence in soil and sediment, PCBs continue to create health problems. Hence, there is considerable interest in identifying specific PCB congeners associated with increased risk of different diseases, including non-Hodgkin's lymphoma. The Janus cohort of the Cancer Registry of Norway has surveillance data on many cancer types. Excuse me, please. Appa, can you turn off your volume, please? Appa, can you turn off your volume, please? Thank you. Yeah. Sorry about that. The Janus cohort of the Cancer Registry of Norway has surveillance data on many cancer types, and Engel and colleagues conducted a matched case control study of 190 matched case control pairs and measured the presence or absence of 36 PCB congeners using serum specimen. The cases and controls were matched on age, sex, and county of residence. Our goal is to identify congeners associated with disease risk. Now, PCB congeners affect human health through different mechanisms. The congeners have different biological activities. Some of them have estrogenic properties. Some of them have anti-estrogenic properties. Some of them have enzyme-inducing roles. All of these are associated with adverse health outcomes from different perspectives. And in fact, some of the congeners may also have unknown biological activities. Our goal in relating the PCB congeners to disease risk is to use this biological information, activity information of these congeners. So typically, the congener information and the disease information are available from the Janus cohort, whereas the biological activity information is available from an entirely different database. So we want to put these databases together, this information together, to learn what is the role of these PCBs on disease risk. And throughout, our analyses are adjusted for body mass index and smoking categories, although I will not emphasize this moving forward. So when we have matched case control data, a natural approach to relate disease risk to risk factors is through a conditional logistic regression model. We considered an additive logistic regression model, that is a model without any interaction terms. And these 36 PCBs, also known as PCB congeners, are binary variables. So you can think of each congener is present or absent in an individual, in a study subject. And we have 190 pairs of subjects. The contribution to the conditional likelihood from the ith case control pair is given by L subscript I, and it's shown by the equation here. This is a very familiar likelihood equation for conditional logistic regression, and it depends upon, on the right-hand side, the disease status indicated by Y with some subscript, and the vector X of the binary congeners for several individuals, and the effects beta. And it is straightforward to obtain maximum likelihood estimates, which we denote as beta hat full, and the corresponding variance covariance matrix. This approach is very simple, and we all know how to obtain maximum likelihood estimates using available statistical software packages such as the R programming language or SAS or whatever you would use. And the drawback is that this does not use any congener groupings. This does not use information about which congener has estrogenic property, which one has anti-estrogenic properties, and so on. So one way to incorporate these biological properties is through a dimension reduction strategy. We can create a weight matrix denoted W. It's a matrix with number of rows is equal to the number of congeners, which is 36, and the number of columns is the number of biological activities, in this case 4. I show this in the table on the slide, where there are 4 columns corresponding to whether a congener has estrogenic property, anti-estrogenic property, enzyme-inducing property, or unknown property. And instead of relating our disease outcome Y to X, we can relate our disease outcome to Y to Z. Z is a set of new risk factors obtained by post-multiplying X by W. So what happens here is in the matrix X, every row contains a binary information on the 36 congeners for each study subject. whereas in the Z matrix, each row consists the aggregate weight information for each biological function. So once again, to go back to the W matrix, in each row, I show values ones or zeros. These are weights. And here what I mean by weight is a particular congener. If it is an estrogenic congener, I give it a weight 1 and give weight 0 to all the other biological properties. Some other congener is an anti-estrogenic congener, so it has weight 1 corresponding to that column, and all the other columns carry weight 0. But other values of weights are also feasible depending upon the context of analysis. And we can now fit a conditional logistic regression model relating our disease outcomes Y to our new set of risk factors Z, and we will have a set of model parameters gamma. There are only 4, the Z matrix has only 4 columns, so gammas, there would be only 4 of them as opposed to 36 values of beta. So in this sense, it is a dimension reduction strategy. So we can now fit a conditional logistic regression model and estimate our gammas. But if our goal, which it is to obtain the effects of the individual beta parameters, we can get the beta parameters by pre-multiplying by our gamma with W. So I'll call the estimated betas in this manner, beta hat under subscript red for reduced model. And we know how to obtain the variance covariance matrix through standard procedures. Now, the objective here is to estimate our beta hat red, and the goal here is not to decide how to choose W. So we say that our W is given based upon how we choose to define the weights using external databases that provide our biological functions. So now, once we obtain beta hat full and beta hat reduced in this manner, we can compare those to understand what have we gained? Have we gained anything at all by reducing the number of parameters, by incorporating these biological information in order to gain insights about our betas? So there are 2 figures here. The left figure compares beta hat full on the horizontal axis and beta hat reduced on the vertical axis. The dashed lines are the null values, zeros for beta hat full and 0 for beta hat reduced. And there are 36 dots here corresponding to the 36 congeners. And under the full model that does not use any information about W, 3 congeners were statistically significant. These are indicated by the 3 arrows here. 2 of them are anti-estrogenic properties, and 1 congener had an unknown property. Whereas when we focused on statistical significance at the 5% level in a frequentist sense, using beta hat reduced, none of the congeners were statistically significant. But that alone is not a reason to make decision about which approach is good. Nonetheless, we also looked at the variance of the beta hat full and beta hat reduced. And of course, as expected, the variance of beta hat reduced is very, very small compared to variance of beta hat full, as we can see from the magnitude of the values on the vertical and the horizontal axis. So the use of W in a very naive sense that I showed in the previous slide leads to a reduced model, and it has attenuated effects and variances. It has attenuated effects, as we can see from the magnitudes on the vertical axis versus the horizontal axis, and also attenuated variance. This leads to shrinkage, but this is a rather naive approach for gaining shrinkage. And other shrinkage methods are also available that focus on optimizing certain loss functions. In the shrinkage that we achieved in the previous slide, we are simply using a very naive approach to incorporate W without focus on optimizing any loss function. So one approach that allows us to achieve shrinkage by optimizing a loss function is the empirical Bayes type shrinkage approach. The difference between beta hat full and beta hat reduced is known as the discrepancy between what we would achieve by estimating beta without incorporating W and what we would achieve by estimating beta by incorporating the W. And the Bayes estimate of beta The Bayes estimate of beta can be obtained as beta reduced from the reduced model plus some discrepancy measure R. And an estimate, a naive estimate or a good estimate of R is essentially the difference between the maximum likelihood estimate beta full and the maximum likelihood estimate beta reduced. And we know that under large sample properties, this can be taken to have a normal distribution with some mean, the true effect R, and some variance covariance matrix sigma that can be obtained using the variance covariance matrix of this difference. And the technical details are available in our paper. And we can also impose, in order to obtain a squared, minimize the squared error loss function, we can also do this by imposing a prior distribution for R, which also has a normal distribution with mean 0 and some prior variance covariance matrix A. And what we did is to, if we plug in all of these after some simple algebra, we can obtain our Bayes estimate of beta as, in fact, beta hat full minus some matrix which pre-multiplies our R hat, the MLE of the discrepancy measure. And incorporating different values of A will give us different empirical Bayes estimators. So we can obtain A empirically in different ways, and we consider two different approaches, taking A as R times R hat, or taking A as R transpose R divided by P. P is the total number of congeners, which is 36 in our example, times the indicator matrix. So we can obtain the variance, we can obtain our Bayes estimator in this form. We can obtain the variance of this Bayes estimates and also obtain 95% confidence intervals or credible intervals using bias-corrected bootstrap approach. There is a large body of literature on empirical Bayes estimation method. This is not new to us, and justification for the choice of priors are also available. And also bias-corrected bootstrap approaches are also available, for example, through the works of Efron and Tibshirani. So our derivation of this Bayes estimator of beta borrows generously from this literature. Now, the question now is whether these empirical Bayes estimates perform better than the beta hat full, which is the standard maximum likelihood approach that does not use the W matrix. And to answer this question, we looked at bias variance trade-off. In doing so, we treat our maximum likelihood estimate beta hat as our gold standard, because we all know how to fit those kind of models, and those are very popular. So the figure here shows the figure here shows beta hat full on the horizontal axis and beta hat B, Bayes estimate on the vertical axis. And on the right-hand side, we see the variance of the beta hat full and the variance of beta hat Bayes estimator. Interestingly, the empirical Bayes approach has much larger variance than the maximum likelihood approach. I show two kinds of Bayes estimators here with black dots for the EB1, one way of estimating the A matrix, and EB2, another way of estimating the A matrix. So what this figure tells us is we do achieve shrinkage. We do achieve shrinkage, but at the same time, the variance or the uncertainty is so large that there is simply no point in using this type of a Bayes estimator that we have derived. But this is not the only way of achieving shrinkage. There are other ways of achieving shrinkage by incorporating W, which is what we want to achieve. So we looked at 3 additional shrinkage estimation methods based on hierarchical modeling approaches. First, we examined a hierarchical modeling approach, which we will call the 2-stage lasso. In this 2-stage lasso, the first stage involves obtaining beta hat reduced by incorporating the W matrix. This is a naive shrinkage estimation approach, the dimension reduction approach that I showed in an earlier slide. In the second stage, we do what is the following. We find seemingly better estimates of beta, the individual components of beta, by penalizing the log likelihood function of a conditional logistic regression model by specifying that the absolute value of the individual components of beta parameters must be close to the corresponding components of the naive estimate of reducing the dimension. So this type of penalization is equivalent to maximizing the log likelihood function by placing some hierarchical priors, where each component of beta has a normal prior with mean as the naive dimension reduction approach, and variance, which is the product of two types of variances. And one of those components in the product has an a priori Rayleigh distribution, and another term in the product has an inverse gamma distribution. And in this type of, this approach takes the naive estimate of beta at face value without incorporating the uncertainty or the variation surrounding its estimation into this hierarchical process. And this type of work also has some parallels or some foundations in prior works of Malik, Casella, and others. A second hierarchical Bayes estimation approach we considered that would incorporate W, which is what we want to achieve, is the hierarchical Bayesian lasso, where the log likelihood is maximized as before, and each component of beta has a normal distribution, but with mean not as the naive estimator, but as a product W times gamma, and the variance as before, and we place a normal prior on the gamma. And the a priori assumption we have is that this reduced rank model is valid, this W is valid. All other priors are as in the previous two-stage lasso. And finally, a third approach is what we call the Bayesian ridge, which is very popular approach. Once again, we will estimate our betas by penalizing the conditional log likelihood function of the conditional logistic regression model, except that the prior of beta has a normal distribution where with the variance is not two components but a single component sigma square, which is effectively setting the tau square is equal to 1. And under all these hierarchical Bayes approaches, we can estimate betas by applying a Markov chain Monte Carlo approach and by following all the standard procedures of running a Markov chain Monte Carlo procedure. And we can also obtain summary statistics based on the posterior distribution of beta. We can get posterior means, posterior median, posterior variance, and also obtain the 95% credible intervals. And in the maximum likelihood estimation approaches, typically we will use p-values to as a summary measure of judging hypothesis tests. And we developed analogous measures here to determine whether any specific congener can be deemed to be associated with disease risk. We call our measure as the posterior association summary. For each component of beta, we look at its posterior distribution, and we look at the values that we obtained from the Markov chain Monte Carlo, and we define a one-sided posterior association summary as the posterior probability that a specific component of beta is positive. And we can also obtain a corresponding two-sided summary by defining it as the posterior that the component of beta is positive, and also calculate the posterior that the component of beta is negative and take the maximum of those two. And for example, we may deem variables for which the posterior association summary to exceed 80% or 90% or 95% to be interesting and worthy of further investigation. Now, treating the maximum likelihood estimates once again as the benchmark for comparison, we examine the bias variance trade-off of our hierarchical Bayes estimators. For the non-Hodgkin's lymphoma data, the summary is that the Bayesian lasso approach had very similar estimates as the two-stage lasso, but it was also better than the Bayesian ridge in the following sense. If we look at the variance of our hierarchical Bayes estimator, this line is a 45-degree line. When the hierarchical Bayes estimates have the same variance as the beta hat full, then all the variance estimates will lie on the bold line. The fact that they're all lying below the bold line says that the hierarchical Bayes estimates, as one would expect for shrinkage, many shrinkage estimates, they have smaller variances. But even in this context, the Bayesian lasso and the two-stage lasso estimates have much smaller variances than the Bayesian ridge. And we also, using our posterior association summaries, we found that several congeners it had posterior association summaries exceeding 80%. And the 3 congeners that were identified using maximum likelihood estimation also were identified as having posterior association summaries exceeding 95%. But what is missing from this slide is, under the maximum likelihood approach, none of these congeners had were statistically significant or had even p-values anywhere close to 0.20 or anything. They were fairly large p-values. And we also identified congeners having not just anti-estrogenic properties, but estrogenic properties and enzyme-inducing properties, which are very important for adverse diseases. And we also identified congeners having unknown disease properties. We also conducted extensive simulations. I will not go into the details of the simulations. These are available in our paper. And our simulations, which I do not show, demonstrated that the Bayesian lasso provides estimates with small variance in general. And these are closer to the true values of beta. And even if we specified W matrix, the weights, incorrectly, the Bayesian lasso was able to recover the appropriate congeners as being associated with disease risk because of information sharing across the congeners through a shrinkage estimation process or a Bayesian process that we have shown. So in this sense, the Bayesian lasso estimates were quite robust. I just have a couple of slides to wrap up. In summary, the Bayes estimation approach allows us to incorporate external information about the biological functions of congeners that are typically available from external data resources. And the estimation process that combines this external information focuses on shrinkage. And through shrinkage, we are able to identify congeners in a better way with better bias variance trade-off, especially smaller variance. And empirical Bayes estimators provide estimates that minimize the posterior risk, and we have used the squared error loss function. The prior variance A for empirical Bayes estimators can be specified in many ways. And we estimated the standard, we estimated A empirically using the methods that I showed earlier. And we also estimated the standard errors using bias-corrected bootstrap approach. But in contrast, what we found is hierarchical Bayes methods offer computational easy solution to obtain shrinkage estimates, and they also have much better variance properties. In our analyses and in our simulations, the Bayesian lasso estimate was a robust estimator. And finally, polychlorinated biphenyls are major risk factors for various diseases, and especially non-Hodgkin's lymphoma. And one way they promote cancer is by affecting the hormones, and they affect our immune system by affecting the hormones. And incorporating the weight matrix W allowed us to identify various congeners over and above those identified by the standard maximum likelihood estimator. So these in red, I show what we identified using maximum likelihood estimation, especially for anti-estrogenic congeners. But we were also able to identify other congeners that are important for the etiology of non-Hodgkin's lymphoma. And these are also studied extensively in other subsequent and prior works, these particular congeners. And more work is currently underway to examine such approaches for risk factors associated with cancer survival. The technical details that I presented are of the work that I presented are based on 2 publications that are available to you directly through a Scholar Google. But if you are unable to access it, I'm happy to send these to you. And I use the technical details presented in these work to analyze the non-Hodgkin's lymphoma data that I presented today. So that is all I have to share with you today. Thank you very much for your attention, and I'm happy to take questions.
Any questions or any comments? It's interaction time. You have 2 minutes.
Hi,
Thank
madam.
you, madam. Okay.
Hi, Jagat.
Hi, madam. Actually, this uncertainty what you are talking about on the shrinkage estimate, whether it is quantified or based on the variance you are saying that the uncertainty is more.
I use the variance of the beta hats that I obtained using shrinkage estimation, and that is those variances were small.
Okay, thank you.
Yeah, but I did calculate the bias by taking the maximum likelihood estimate as the gold standard in the data analysis. But in simulations, I already know the true beta, so I can calculate the bias there. But for the data analysis, I calculated bias by treating maximum likelihood beta hat full as the true values, because we do not know the truth there.
Yeah, yes. Thank you.
Any questions? No. Thank you, madam, for your nice presentation on Bayesian penalized regression methods, logistic methods, then regression estimation. Your presentation is very useful to the new researchers and the. Okay.
Thank
it is
you
very
very much.
interesting, and your presentation. Okay, what a simple language, and all things are explained here. Thank you very much.
Thank you.
Next speaker, Shubha, please introduce the third speaker.
Thank you, Professor. Yeah, sure. I'll introduce her. Thank you, Professor Sadagopan, for the wonderful discussion of the topics that you presented. Now, I would like to welcome our next speaker, Dr. V. Vivian Lee, who is the Assistant Professor, Department of Biostatistics and Epidemiology. She received her PhD degree in statistics from the University of California, Los Angeles. Prior to joining University of California, Lee received her BS in statistics from Haushong University of Science and Technology. She's interested in developing interpretable and tractable statistical methods for making biological and biomedical discoveries. Her broad research interests are statistical questions arising from large-scale biological data, with a focus on statistical genomics. As technology breakthroughs enable genomic research at a single-cell resolution, in addition to the traditional bulk tissue studies, Dr. Lee aims to tackle statistical challenges in the burgeoning single-cell field, as well as developing powerful statistical methods to improve the accuracy of analyzing bulk tissue genomic data. In addition, Dr. Lee is also interested in general statistical methodologies with wide applications, such as the asymmetric binary classification methods. A recipient of many awards, including the Statistician Award from the University of California, Los Angeles in 2019 for the Most Outstanding Statistician Award, as well as the Fellowship Award for the Dissertation Year Fellowship from University of California, Los Angeles. Again, the Most Promising Computational Statistician Award, as well as the Most Promising Computational Statistician Award at the UCLA Department of Statistics in 2015. She's a person who is very much interested in statistical research, especially in the field of biostatistics. So I return back to the chair to invite Dr. Lee for the session.
Next speaker, Wei Vivian Lee. She will present the topic on selecting gene features for unsupervised analysis of single cell gene expression data. Madam, please.
Thank you both for the nice introduction, and also thank you, Jaya, for the invitation to speak at this wonderful session. So let me share my slides. Okay, so today I would like to introduce several computational and statistical methods for selecting gene features in unsupervised analysis of single-cell gene expression data. And most of my talk is based on a review paper that I recently wrote with Jie Sheng, a master's student in data science at University of Wisconsin-Madison. Our manuscript is still under review, but we are submitting it to archive, and it should be available online soon. So feature selection is a traditional task in supervised learning, and it refers to the process where we either automatically or manually select the features that contribute most to our prediction variable or the output that we're interested in. And by removing those irrelevant features and only retaining the most relevant ones, usually we can increase the performance of our prediction models and also reduce the computational time at the training stage. Also, after feature selection, usually our trained models will be much easier to understand and interpret. And traditional statistical methods that can perform feature selection include ridge regression, lasso, and also decision trees and random forest. However, all this happens in a supervised manner, which means that we need to depend on a predictor variable in order to search for the well-performing subsets of features. And today, I would like to introduce a feature selection problem in an unsupervised manner because there's no predictor or target variable available for us to select the best features in a supervised manner. So what is a single-cell gene expression data set? Such data is generated by the so-called single-cell RNA sequencing technologies, which have emerged as a powerful tool in order to capture the genome-wide cell-to-cell variability in gene expression. And compared with the traditional technologies, single-cell RNA-seq can enable the quantification of intrapopulation heterogeneity, and it can help us review gene expression dynamics in complex tissues. And this diagram is a typical workflow of the single-cell RNA-seq experiments. So it starts with the collection of a solid tissue sample, and then single cells or individual cells are isolated from the sample. Next, the RNA molecules from the single cells are extracted. So in the cells, if a gene has a high expression level, then it will make more RNA copies. And in contrast, if a gene has a low expression level, then it will make fewer RNA copies. And once we get the RNA molecules from the individual cells, after the library preparation step, the sequencing machine is able to read the nucleotide acid sequences in the RNA fragments. And after the sequencing machine reads these sequences, we can compare these sequences to the sequences in the reference genome to determine the number of RNA fragments coming from each gene. And finally, we can summarize a count matrix. Usually, we organize the matrix such that the rows represent different genes and the column represent different cells. So each entry represents the number of RNA fragments produced by a gene in a single cell. And if we can think of these different genes as different features, but since this is the only output from the single-cell RNA-seq experiment, there's no direct predictor or target variable available for supervised selection of the gene features. And in data analysis of single-cell data, a very critical step is to perform an unsupervised clustering analysis so that we can divide these cells into different cell clusters. And then by comparing the gene expression patterns in these different clusters based on domain knowledge, we can annotate them as different cell types. So based on this workflow, we can see that in single-cell analysis, the cell clusters need to be inferred, and cell type labels are not directly available as a predictor variable in single-cell analysis, presenting challenges to select biological relevant gene features in a supervised manner. And since the invention of the single-cell RNA-seq technologies, single-cell analysis has been a very important tool to study development. In this example, the authors sequenced around 2,000 single cells from the human embryonic cortex to study the developmental landscape of human cortex. And after they get the gene expression matrix, they use clustering analysis and identified around 6 major clusters from this cell, and this including neuron progenitor cells and interneurons. And also by comparing the gene expression patterns between the single cell clusters, we can also identify gene signatures that are specifically highly expressed in a specific cell type. This is a very important way to discover gene signatures that have specific biological functions associated with a particular cell type. And in addition to physiology, single-cell analysis has also been very important for studying different types of disease. In this example, the authors explored the disease trajectory of COVID-19 by performing longitudinal single-cell analysis in blood samples from both healthy subjects and hospitalized patients. And the demonstrated single cells were collected from 14 patients at different disease phases, so including healthy, critical, complicated, and recovery. And after unsupervised clustering analysis, the authors were able to identify different types of immune cells from these blood samples. And based on results from the clustering analysis, we can compare the cluster proportions in patients at different disease phases to better understand the development of COVID-19. So even though single-cell gene expression data can be collected from different tissues, organs, and platforms, most studies will use a similar workflow in the data analysis. And after the sequencing step, we get a count matrix where rows represent different genes and columns represent different cells. And we can think of this count of RNA fragments as a representation of gene expression levels. Next, after quality control to remove the genes and cells with low quality, usually there's an additional step called batch correction. If the data were collected from multiple labs, multiple time points, or different batches, then we need to perform normalization or the so-called batch correction to remove this known technical effect in the gene expression matrix. And then there's a critical dimensionality reduction step. Usually it's consisted of 2 sub-steps. The first step is gene feature selection, and the second step is further dimensionality reduction using methods such like principal component analysis. After dimensionality reduction, we can perform unsupervised analysis such as clustering and trajectory analysis to identify different cell groups. And once we annotate the cells based on domain knowledge, we get the annotated profiles, and we can perform different types of statistical analysis based on biological questions of interest. A typical analysis in disease studies is to compare the proportion of a particular cell cluster between healthy subjects and hospitalized patients. And based on this workflow, we can see that the selection of gene features is a crucial step in single-cell RNA-seq analysis and can greatly impact the downstream computational analysis and data interpretation. We can also compare single-cell analysis without and with gene selection using this toy example. In this example, we consider two mostly widely used analyses in single-cell studies, the clustering analysis and the trajectory analysis, which refers to the procedure to computationally infer the pseudotime order of individual cells along a developmental trajectory. And we can see that genes whose actual abundance do not vary much among different cell clusters or cell states will contribute technical noises to the calculation of cellular similarities. And this will compromise the accuracy of unsupervised analysis if we do not exclude such genes. And in our review, we based on statistical methods being used, we divide existing gene selection methods into three major categories, and we call them empirical distribution-based, generative model-based, and distribution-free methods. In the remaining time, I will introduce the most representative methods in each category and compare them with a case study. So first of all, I want to introduce several notations that are used throughout my discussion. After the single-cell RNA-seq experiment, we denote the summarized count matrix as X. And suppose there are M genes and N individual cells, we use Xij to denote the count of RNA fragments corresponding to gene I in single-cell J. And we also use Xi bar to denote the sample mean of gene I. So these are the row means of the count matrix. And we use Si squared to denote the sample variance of gene I. These are the row variance based on the count matrix. And so first, let's talk about the empirical distribution-based methods. These methods have a similar framework that they first directly calculate summary statistics of all the genes based on the empirical distribution of gene expression across the single cells. Then they will select the most important gene features by ranking these summary statistics. And mostly widely used statistics include empirical gene expression variance or expression dispersion. Therefore, genes with high ranks will often be referred to as highly variable genes, or HVGs, in single-cell studies. The advantage of empirical distribution-based methods is that they're computationally efficient and do not require any prior knowledge about which genes are involved in a particular biological process. But the weakness is that they require users to set an arbitrary threshold on the summary statistics in order to select gene features from the ranked list. And in this table, we summarize 7 methods that belong to this category. We can see that these methods do not have specific assumptions on distribution of the RNA fragment counts. And after they calculate a variability or dispersion measure to rank the genes, they can select the most important genes from the top of the ranked list. And most of these methods were implemented as R packages. As one example, I will talk about this method called VST, which is short for variance stabilizing transformation. And this method accounts for the variance mean relationship of gene expression with a regression model before selecting the gene features. This is because a widely known feature of single-cell data. So if we take a count matrix from single-cell RNA-seq experiment and calculate the gene expression mean and gene expression variance of all the genes, we will see that genes with a higher mean expression level tends to have a larger variance. Therefore, if we directly select genes using variance as a measure without accounting for this variance mean relationship, usually we will just select the genes with the largest mean expression levels, and genes with medium expression levels will not have a chance to be included in the downstream analysis. And in the VST method, the first step is to calculate the expression mean and variance of all the genes. Then it will apply the log transformation to both the mean and variance. And then it uses a lowest regression model to fit the relationship between the gene expression mean and the gene expression variance. Suppose we denote the estimated variance by the lowest regression by VI squared. The next step in VST is to calculate a z-statistic, which is the difference between the raw count and the gene expression mean divided by the estimated standard deviation of gene I estimated by lowest regression. And finally, for each gene, VST can calculate the variance of these z-statistics across all cells, and it will select the genes. Sorry about that. And we can calculate and we can select the genes with a large variance of these statistics and use them as the highly variable genes. So basically, the VST method is selecting genes whose variance is large compared to other genes with similar expression levels. And other empirical distribution-based methods, even though they have different procedures, most of them will also consider the mean relationship in the single-cell data in order to select the most important gene features. And so now let's talk about the generative model-based methods. These are the methods that use generative statistical models to describe the joint probability distribution of gene counts, and then select gene features based on the estimated gene expression parameters. And the main advantage of the generative model-based methods is that they're very flexible to account for different sources of cell-specific effect. And some methods are able to borrow information across cells or across genes, usually using a Bayesian framework. And these methods can lead to more robust estimates when the single-cell count matrix is very sparse and noisy. And also, these methods allow the decomposition of gene expression variability into biological and technical components. And this allows us to select gene features based only on the biological variability. The downside is that usually the generative model-based methods are more computationally intensive than the empirical distribution-based methods. And in our work, we summarized 7 methods that are based on generative models. And we can also see that some of these methods can provide inference tools for testing the significance of highly variable genes. And this will eliminate the need to arbitrarily set a threshold on estimated parameters for gene selection. And within this category, we further divide the methods into 2 subgroups, depending on whether the methods require spike-in information in order to select gene features. So what is a spike-in? The spike-in RNAs are synthetic RNAs with known sequences and concentration in order to calibrate sequencing experiments. If spike-in RNAs are included in the experimental design, then they will be added to each cell's lysate with theoretically constant and known concentration. So these spike-in RNAs are not subject to biological variability. And if they're available, we can use the counts from these spike-in RNAs to quantify the effect of technical noises, such as molecular capture efficiency or other unexplained technical sources. And currently, there are
3 more minutes. Already 3 more minutes.
Okay, thank you for the reminder. And currently, there are 2 methods available for selecting gene features based on spike-in information. And they both rely on a Poisson distribution to model counts of biological and spike-in genes. In the Poisson model, we use Rij to represent the library-specific effect and use Qij to represent the abundance of RNAs from biological or spike-in genes. And then the two methods will add further assumptions that are different for biological or spiking genes in order to estimate the variability. The rationale is that we will first use the spiking genes to estimate parameters regarding technical variability, and then model the counts of biological genes to estimate parameters of biological variability. And because many single-cell datasets do not have the spiking information, in those cases, we need to rely on methods that can directly select gene features without using spikings. And we can see that most of these methods assume a negative binomial distribution to directly account for the over-dispersion in count matrix. And in addition, there are another two methods that depend on multinomial or Poisson models to select gene features. And the last category are the distribution-free methods, which do not assume a specific statistical model and instead directly calculate a dispersion measure to quantify the variability of gene expression. So this dispersion measure, most of them are directly borrowed from the widely used Gini index or information entropy. And in order to figure out how people select and use gene features in real practice, we surveyed about 400 studies that were published last year or in the first quarter of this year based on a curated database. Find that about 70% studies used a software called Surat, followed by Transform and a method called ScanPy. However, because both ScanPy and Surat are single-cell analysis toolkits that have multiple functionality, including normalization, clustering, and visualization, it's not clear whether this software were selected because they have better performance in gene feature selection or because it's more convenient to use this software. And we also summarized the number of gene features used in real practice, and we can see a mode at 2,000 genes. But this is mostly because this is the default parameter set in the Surat package. And in order to investigate how the choice of gene selection methods and criteria affect single-cell RNA-seq analysis, we performed a case study to evaluate the downstream clustering accuracy. And we use this particular single-cell dataset because it comes with cell type labels that were identified by a technology called flow cytometry. In this case, we can treat these cell type labels as the ground truth information for our clustering analysis. And we considered two subsets of the original gene expression matrix. One has a lower sparsity and another has a higher sparsity. This can help us evaluate the performance of gene selection methods for dataset with different level of sparsity. And after selecting the gene features, we performed the clustering analysis using the Surat software, and the accuracy evaluated using the adjusted rand index. So the most important message from our case study is that the generative model-based methods tend to have more advantageous performance when data is relatively sparser. And for low sparsity data set, methods that are based on empirical distribution-based methods also has a nice performance. And in addition to selecting genes based on the software's default parameters, for 9 methods that can output calculated gene-wide statistics, we also try to select different number of gene features, including 500, 1,000, and 2,000 genes to better compare their performance in different scenarios. And based on our analysis, we find that some methods, including SC transform and MB-DISP, were more sensitive to the number of selected gene features, while methods like MB-DROP and TANS are more robust. We also find that for half of the methods, the default parameters did not always lead to the highest clustering accuracy. This suggests that it would be helpful for the software to output calculated selection statistics in addition to an arbitrary list of selected genes, and this will allow users to adjust the number of selected gene features in their analysis if the default settings cannot lead to satisfying performance. And since our case study is based on one data set, we also hope to perform more comprehensive comparisons when high-quality data with ground truth labels become available. So to summarize my talk, we discussed statistical and computational methods for selecting gene features in unsupervised analysis of single-cell gene expression data with unified notations and statistical frameworks. And we categorize these methods as empirical distribution-based, generative model-based, or distribution-free methods, and they have different applicability, distributional assumptions, and gene selection criteria. But regardless of the statistical framework being used, most methods will account for the relationship between the gene expression variance and the expression mean in order to select the truly informative gene features for unsupervised analysis and downstream statistical analysis. We hope our discussion can provide a useful summary to help practitioners select the most proper methods based on their assumptions and applicability, and also to assist method developers in designing new computational tools for unsupervised learning of single-cell RNA-seq data. So that concludes my talk, and thank you very much for your attention.
Any questions, please? One or two questions? Or comments? Neil Matthew, have you any doubt? Okay. Let us thank the speaker. It's a very informative talk on selecting gene features for unsupervised analysis of single-cell gene expression data. Next speaker is Zorimar Rivera Nunes. Shubha, please introduce. Okay.
Yes. I'm extremely happy to introduce Dr. Zorimar Rivera Nunes. She's an assistant research professor, Department of Biostatistics and Epidemiology. Dr. Nunes holds a BS in microbiology and an MS in environmental health sciences from the University of Puerto Rico. Her doctoral degree is from the University of Michigan. She completed a National Academics postdoctoral fellowship at the U.S. Environmental Protection Agency in Cincinnati. Before coming to Rutgers, she was on the faculty at Washington University and public universities in St. Louis, Brown School Public Health Program. Dr. Rivera Nunes studies chemical exposures and its effect in early life and subsequent health. Most of her research focuses on the effect of measurement error characterizing environmental exposure, the utility of biomarkers identifying windows of exposure and susceptibility, and the effect of perinatal exposures in birth outcomes and children's development. Dr. Rivera Nunes is interested in exposure assessment of endocrine disruptors during pregnancy and early life. Dr. Rivera Nunes and colleagues are another area of research of Dr. Rivera Nunes is exposure assessment of drinking water contaminants. Her postdoctoral work documented the change in drinking water disinfection treatment from chlorination to chloramination in the United States drinking water systems and their impact in pregnancy outcomes. Some of her other areas of interest are she's also interested in analyzing large data sets and its utility in public health. And she has a number of publications in these areas and is also actively involved in the works of Society of Pediatric and Perinatal Epidemiology Research, International Society of Exposure Science, International Society of Environmental Epidemiology, etc. A very eminent researcher and a great statistician in the area of epidemiology and biostatistics. I welcome you, Dr. Rivera Nunes, and I'm handovering the mic to the chair of the session to introduce her topic. Thank you, sir.
The final presentation will be done by Dr. Rivera Nunes, and the topic on metals as endocrine disruptors in the Protect Birth cohort. Doctor, please.
You are mute, doctor. Your mic is mute.
There you go. Sorry about that. So many months and I still make the same mistake. Thank you for the invitation. I'm going to share my screen now.
Okay.
Are you able to see it?
Yes.
Okay, great. Well, we have been talking heavily about stats, methods, and different approaches, and I'm going to switch the topic a little bit more. I'm going to do some epidemiology for the next 15-20 minutes. So I'm going to be presenting on the PROTECT birth cohort, and I will introduce the cohort very briefly. I'll talk a little bit about endocrine disruption, birth outcomes in Puerto Rico, the PROTECT cohort, and this particular piece of research out of that. So my background, it's most of my work recently, it's prenatal epidemiology. And one of the things that I'm focusing more is the hormone environment during pregnancy. So during pregnancy, there's a very delicate hormonal balance that coordinates everything from conception to delivery. And variation to that balance may have adverse outcomes, including different pregnancy complications and birth outcomes like preterm birth or low birth weight. Now we have around 20 years of data behind the developmental origins of health and disease theory that, particularly for hormones, suggests that the prenatal hormonal environment may contribute to children's later health and disease risk, including neurodevelopment impairment, polycystic ovary syndrome, endometriosis, and some hormonal-related cancers like prostate and breast cancer. So that's kind of the outcome that I'm going to be presenting. In terms of the exposure that I'm aligning with this outcome, it's metals and metalloids. Metals are well studied for years and years and years. We know the toxic effect of many metals, including the most relevant in terms of toxicity, right? Mercury, cadmium, arsenic, and lead. And we know that they have adverse impact in pregnancy. However, less is known about the effect of essential metals like cobalt or manganese, which are essential for many biological and physiological functions in the human body. There's mostly experimental data suggesting that metals and metalloids can act as endocrine disruptors. And for example, lead and mercury can reduce the levels of testosterone. And mercury can also stimulate the progesterone production. Some of these metals can also bind to estrogen receptors and can initiate the transcription and activate different genes, including estrogenic genes. Despite all the evidence from animal studies, less is known in terms of human populations. Actually, before this study, there was just only one other study looking at the impact of metals during pregnancy, and that study was particularly focused on thyroid hormones. So let's talk a little bit about Puerto Rico here. This is for context. This is the map. This is the island of Puerto Rico, and this is Dominican Republic and Cuba. This is the United States that goes up here. This is the state of Florida. And here at in the south part of Puerto Rico, it's South America, this is Venezuela and Colombia. During the 80s and 90s, Puerto Rico adverse outcomes, like in terms of birth outcomes, like preterm birth and low birth weight, were very comparable or lower actually than the main USA, right? However, as the 90s started and by the end of the 90s, the rates for some outcomes, including preterm birth, were higher here than in other parts of the states. And preterm birth, it's all babies that are born less than 37 weeks. And that is important because all these babies have, babies are not born at term after 37 weeks. They have higher risk of multiple morbidities, and they're at higher risk for mortality. So morbidities like neurodevelopmental diseases, different conditions, asthma. There's a long list of adverse outcomes that they have a higher risk for. So if you can see here in this figure, this is 2009, the risk for the rate for preterm birth was 17.6, and it kept going higher and higher until we have been able to stabilize it a little bit. And in the recent years, it's starting to increase again. You may ask how this compares to the rest of the U.S. This is a map of the U.S. It's color-coded, and this is out of the March of Dimes, which is a foundation that focuses their work in reducing the rates of preterm birth in the U.S. They use a grade system to kind of grade each of states in terms of the rates, right? So the best states are these blue shades, are the best rates. So they go from 7 point something to 9.8 in terms of the rate of preterm. So if a state it's 7, 8, 9, that is a good rate, right? That's a good rate for preterm. But then as you go and move forward in the colors here, you go orange, like this yellowy orange, and red, those are the states with the highest rates of preterm birth. And that's when you see Puerto Rico here together with a cluster of states in the south. Another characteristic of Puerto Rico is that they have more than usual places of environmental contamination. So sites that have been polluted either by different manufacturing procedures or companies or different events, including nature events, right? These sites are under the Superfund program. And the Superfund program in the US, it's kind of a trust fund that came out of regulation in the US Congress to handle emergency and hazardous waste sites that need long-term cleanup, right? So there's a fund, they allocate this money, and they evaluate different sites for potential contamination, not only for the contamination, but the main point being, is this contamination going to migrate and affect populations around it? So each of these sites is evaluated going to a list, and they one by one are evaluated and further clean up. Some of these sites are cleaned very quickly, but most of them, it takes long because all of these chemicals, most of these chemicals they just stay there for a long time. They have long half-life, and they're very difficult to clean. So Puerto Rico, it's only 100 miles per 35 miles. And the last list for Puerto Rico in terms of Superfund sites was 18 different sites. So the Puerto Rico birth cohort comes from trying to see what is the impact of all of this pollution that they have in birth outcomes, particularly for preterm birth, because the rates for preterm birth were really high. And so the project just wants to look at the impact of pollution, particularly all those chemicals found in Superfund sites in relation to preterm birth. PROTECT is a very large project. It has multiple projects in it, and I'm not gonna discuss all of them because we can stay here longer than 20 minutes for sure. So I participate in project number 1 here, biomarker epidemiology of exposure to mixtures, oxidative stress, and adverse pregnancy outcomes in Puerto Rico. So that's kind of what I'm gonna focus today. So under that, that's when the cohort of pregnant women was recruited, right? So right now there's around 1,500 women recruited into the Protect Birth cohort. They are most of them low-risk single-term pregnancies. Women are 18 to 40 years old. They're all residents in the North Karst zone of Puerto Rico because they have more Superfund sites in that area. No use of oral contraceptive and no use of in vitro fertilization. And it's a cohort, right? So we follow them through their pregnancies. And there's have 3 different visits, around 18 weeks, 22 weeks, and 26 weeks of pregnancy. We also talk to them and collect different biospecimen and different information during birth. Among the biospecimens that are collected is urine, blood, cord blood, placenta, and buccal swabs. And I'm going to be talking about metals today, but there is a long list of different chemicals from parabens to pesticides that have been analyzed in the biospecimens of these women, and they have been assessed through pregnancy. So the metals that we looked at, some of them were analyzed in blood samples and some of them were analyzed in urine samples. But it's a list of around 16 different metals and metalloids. And we also collect covariate and outcome data as we visit them through pregnancy, right? So that's when the demographic data comes, food consumption, personal care products, different supplements, water intake. At birth, we collect all the birth outcomes information from their medical register, from the medical records. And in those biospecimens, in addition to measure all the chemicals as exposure, we also measure other endpoints that we're interested in. In this case, we were interested in maternal hormones. So we measure sex steroid hormones, thyroid hormones, and CRH, or corticotropin releasing hormones. So these 3 groups of hormones were measured at 2 different points during pregnancy. So these were, same for metals, we measure them at visit 1, which was week 18, and then at visit 3, which was week 26 or above. Some cohort demographics, some summary of the women that are enrolled. Participants were around 27 years old in average. Most of them were married or in domestic partnership. Most of them, 77% of them had high school education. The majority of them were employed and 60% of them had a private insurance. Also, it's in terms of other exposures, they were healthy, relatively healthy. Only around 2% of them smoked during pregnancy, and barely no alcohol consumption also before they got pregnant or starting to think about getting pregnant and during pregnancy. So what did we find? So these are the median urinary and blood concentrations of metals for 1,040 pregnant women. From all the ones that are enrolled, these are the ones that have this number, 1,040 are the ones that are in this particular piece of research because they were the ones that had all the data that we needed. We have lead, some of the most toxic chemical metals that we always looked at, lead, cadmium, arsenic. Blood is gray and the pink color is urine. Overall, these women had, for most of the toxic chemicals, they had lower concentration in either blood or urine compared to other populations in the US. So because we collected information in different lifestyles and diets and demographics, we were able to look at what are the predictors of these metals that were detected in their biospecimens, right? So here we have urine, metals that were measured in urine and metals that were measured in blood. This consumption of rice and fish was associated with higher levels of arsenic in urine, and consumption of supplement, most of them, supplements are taken during pregnancy, like cesium, molybdenum, they were all associated with consumption of those were associated with their levels in urine. For blood metals, women that reported smoking ever or never, that was the definition, or current versus never. So smoking was associated with higher levels of cadmium in blood. And fish and canned food, consumption of fish and canned food was associated with higher levels of mercury and lead. Drinking water source, so which source they use, like public versus bottled water, was associated with lead. And these results here are very similar to other parts of the world and other parts of the US, where higher concentrations of lead here in the US, for example, are associated with particular drinking water sources, or smoking is a predictor of cadmium concentrations in other populations, not only in pregnant women. Same for fish and canned fish and the relationship with cadmium. Mercury. Okay. So in terms of what did we see in relation to the hormone levels that were measured in the women, we saw interaction effects between the time of the visit, when we collect that sample, study visit, week 22nd versus week 26 or over, there was an association there, an interaction effect for the association between some of the metals. Here I'm showing the nickel in blood, and CRH hormones. So depending of when in pregnancy the exposure occur, you're going to have different results, and that is important because we know that for some endocrine disruptors,
5 minutes more, maximum 5 minutes. 5 minutes more, 5 minutes more.
Okay, thank you. That is important because we know like timing of exposure is important during pregnancy. There's different development occurring during pregnancy, and it's not the same to be exposed, let's say, during the first trimester and the second trimester and the third trimester. Similar for, this is nickel and testosterone. We also saw an effect in between visits. Then the last result for the hormones, it's that we saw non-linear relationships for some of the essential metals, right? So not much attention has been paid to the non-essential metals because to the essential metals, because they're essential, right? And the expectation is like, they're not going to be toxic. However, we know, and there's literature in some epi studies and a lot of experimental studies where when we don't have the exact amount of an essential metal, that can be toxic, right? If we have very low concentrations or very high concentrations are toxic. And in environmental health and environmental epidemiology, we tend to look at linear regressions all the time. And it's much harder for us to figure it out what happens when relationships between chemicals and outcomes are not linear. So this is an example of that type of association and why we need to keep developing different models and statistical approaches to learn more about the non-linear relationships between chemicals and outcomes. So overall, like I mentioned, the timing of exposure is important, especially for sex steroid hormones that have a particular role during pregnancy. And their levels are different through different points of pregnancy. Once, for example, estrogen, say, increased through pregnancy, same for progesterone, and others increase in different rates. And when we have an insult during pregnancy, it is important when that insult occurs and what happened to those hormones. So that's for the levels of the timing of exposure in terms of metals. And then the other finding is essential metals. Like I said, they're not being studied, they're less studied in terms of adverse outcomes. And we know that some are very important for biological processes, but we don't know what happened if we're exposed to them and we can find them in levels that are higher. Like, for example, nickel can trigger oxidative stress and inflammation, and that can lead to multiple adverse health effects. And during pregnancy, oxidative stress and inflammation can lead to parturition. So things like nickel needs further evaluation in terms of preterm birth. So we have some limitations like in any other study and some advantages. This is the first time we study metals and sex steroid hormones. It has a longitudinal design that would make us, we could look at multiple times during pregnancy. We study essential elements and we study CRH. CRH is the hormone that has been not linked to chemical exposures, but mostly because it has not been studied in that context. And CRH is very important for delivery. That's why it's included in this study, because higher levels of CRH in different times during pregnancy can trigger preterm birth. Some limitations, some metals were detected in a small number of participants, and we had to dichotomize the exposure for the modeling. The serum circulating hormones, that gives us an idea of the levels of the hormones, but that's not what, it's not fetal circulation, right? So it's more of a maternal marker. And we have 2 time points, so we measure all these exposure and elements, but that may not be enough to characterize all the exposure to pregnancy. So basically the conclusion is kind of what I just mentioned. Metalloids, metalloids can be endocrine disruptors. It is important to see when that impact is happening. So specific windows of exposure during pregnancy is important. And essential metals may contribute to adverse maternal and fetal outcomes. And definitely we need a little bit more research on those different pathways. Sorry there. And that's it. These are just some acknowledgement to the whole PROTECT team, which goes through multiple institutions, to my mentors at here at Rutgers, Dr. Emily Barrett, and the doctoral students that I work at Michigan that have been working with me in this and other studies, and all the PROTECT PIs for allowing me to participate as an investigator in this project. And with that, I'll take any questions.
One or two questions.
We can take some more time with the discussion if needed, because the next speaker has not joined yet.
Okay.
And he informed some due to some urgent issues, he can't able to join in time.
Any questions or discussions or clarifications? Otherwise, we thank the speaker. It's a very interesting topic. This is an example from biology. Okay, you have any questions? We have 4 deliberations. All of them are from the applied field. These works are giving very nice insight to the applied field of statistics, especially in biostatistics. I thank Jaya Madam for organizing such a wonderful session. My special thanks to Dr. Shubha for the nice introduction of the distinguished speakers. Okay. If you have further discussion, you can join with Jaya Madam or any resource person.
I want to say thank you to all the speakers, Jason Roy, Vivian Lee, and Zorima Rivera Nunez for excellent talk and for participating in this session and for your time, and for everyone for taking the time to join us today. Thank you.
Thank you. Thank you, all of you, for being a part of the webinar. Thank you.
Thank you, Jaya Madam. And thank you, Professor Jay. Sadish sir. Okay.
Sadish.
Yeah.
Okay. Good evening to all of you.
So before starting, Professor, I shall give a thanks to the earlier speakers.
Yeah. Yes, I think you should formally thank the earlier speakers and close the session.
Yeah, close the session.
Yeah.
I want to. In fact, Professor Jaya and his team have done an excellent job. A very nice session. Everyone enjoyed it, and I utilize this occasion to thank each one of you, professors, for your nice presentations, wonderful deliberations, in fact. Also, I utilize this occasion to thank Dr. Jonis Karia for chairing the session, and Dr. Shubha to support him as co-chair. Now I invite Professor
Okay, thank you very much, Sadish Kumar.
Yeah.
Okay, audience, this is going to be a disappointing kind of thing. Unfortunately, Ashish Sengupta is hospitalized for some reason. So we will not have this session as such. So as you all know that, yes, many people have joined only to hear him. So as you all know, he is one of the tallest statistician of India, having all regards from all corners, and is familiar to most of the Indian statisticians and university faculty members of statistics. And yes, it was actually there was a very interesting talk scheduled for that is test of homogeneity of means, but very unfortunate that I have to declare that this session is actually cancelled. But we can have some discussion if you are willing. Other experts, Professor Hira Cole is also joined. Kalyan Raman sir is also there. Balakrishna.
So today, hello to everybody.
Pardon, sir.
Can you hear me?
Professor Hira Cole is testing his mic now.
Yeah, we hear you, Professor.
It was my fault yesterday. When I logged yesterday, it gives a command. Will they allow Google to use the microphone? Will they allow Google to use camera? I did not look at that before. So now everything's okay.
Okay.
So I can give my talk again today if you want to.
Sir, okay. Now, I don't know the reason why he has been hospitalized. So
I just heard that. Thank you.
Yeah. Okay. So maybe we can have a small discussion or something which actually helps the students of or research scholars of statistics, because many people have joined. Even the results of the quiz competition is also out.
Yeah.
Out of 1,000 participants, more than 1,000 participants were there for the quiz competition.
Wow.
And out of that, many people from, there were a lot of representations from other states also. So I have seen the winners list. It's representing most of the
This actually shows this national characteristic.
Exactly. Even international character is also possible if they try a little hard. Next year they can try.
If the lockdown continues.
Yes.
Yeah.
Right. Professor Hirakol, sir, you are here in India or in, outside?
No, I'm here. I'm in East Lansing, Michigan, USA.
Michigan, okay, USA. Okay, sir.
Yeah. And,
okay.
Yesterday was a fiasco. I just didn't know, nobody knew what happened to the microphone. So I had to give that talk.
Dr. Satish, have you planned any concrete thing for this session now, other than because Professor Ashish is not coming? Do you have any specific plan?
No, as such, I don't think they have any specific plan. It was actually the 11th hour notice actually.
Yeah.
So
I think Professor Kaul, did you get the message now? But right now, Ashish Sengupta's talk was scheduled.
Yeah.
But unfortunately, he's not coming. He's not presenting. So now that the slot is free now.
I heard that. Yeah, I heard that.
Yeah, slot is free.
Yeah. So let me ask Satish Kumar, how many PhD students does the department have now? How many doctoral students do you have?
Yeah. Satish, you have to answer. How many PhD scholars are there in your department? How many PhD scholars are there in your department? That's what Professor Cole asking.
Yeah, we have around 20 research scholars in the department. Yeah.
Okay. All right. Well, I'll be here, but I'm going to take off. I'll move away from this for a while because I have some other appointments, but I'll be back in half an hour or so. Okay?
Okay.
All right.
I hope this session you can utilize by giving some motivational notes to our youngsters. So by the senior professors like you.
That's what Professor Kalyan Raman is there. Yeah, you may invite him.
If needed, we can take it a break. And in fact, Professor Bimal Sinha is there in the group probably.
Okay.
I think, but his talk is the next arranged. But we can. I hope so.
Yeah, I think you better stick on to the schedule because let Professor Sinha speak during his session only.
Yeah. That's good. So it's better.
We can go and have dinner.
Yeah, madam, if you can send some packets, we will eat it.
Not like North Indian food. We don't have South Indian food. We can.
No, Abhinav, we are happy with the North Indian food. There is no problem.
Yeah, virtual meals, virtual snacks.
Yeah.
Virtual eating.
No, I had dinner at madam's place. I know.
Okay.
You were in Chandigarh. I think you were fed up with North Indian. You can have it for I think 2-3 days. After that, it becomes difficult. Even when we come to South India, for 2-3 days, it's okay.
Anyway,
After that, we start yearning for our food.
Right.
So it's with everyone.
Balakrishna, you are muted.
Is situation bad?
Unmute. Balakrishna,
Okay, so during this kind of free sessions, people used to show their talents by singing and.
Yes.
I think if Sharda Bhatt is there, she would have started singing now.
Classical singing.
I thought you were going to sing.
She's a classical singer.
Yeah.
It will relax the tired mind. I think Professor Satish has been.
No, I request Dr. Satish not to sing. Anil Matthew, I don't know whether you have any extracurricular activities you can show now.
I can't.
Good evening, sir.
Gopal sir is there. Yeah.
Professor Gopal, joined with us. Yeah, Professor.
This session is cancelled, sir. Gopal, sir.
Professor, this session.
The session got cancelled here.
Yeah, Professor. This session.
Okay, we'll go and have dinner and come back.
I think it's only 20 minutes now remains, madam.
Yeah.
So not too much.
I think Professor
maybe this can be a break for maybe 10-15 minutes. Maybe it's good for, because you have started in the evening session from 5:30 onwards or 4 o'clock.
Yeah. In fact, there is no break at all.
Hello, excuse me. Hello, Satish. Hello.
Yeah, Professor. Hello, Professor.
Good evening.
Good evening, sir. Good evening, sir. Good evening. Yes, sir.
I see that you are doing some chit-chatting. Looks like kind of relaxing mood now. I can join in 20 minutes. Is that be okay?
Yeah.
Oh, that's
Okay,
fine, sir.
Professor.
That's fine.
Yeah, that's fine.
Okay.
Professor Muralidharan, sir, you can say something about the quality manage. You have the opportunities.
Yes. Yeah. Okay, I had my talk yesterday on quality management. I introduced my book also, and that was the main purpose of giving away that talk.
Yeah, I think I missed most of things because now the admissions are going and I am in charge of this admission of international students.
No, I can
Today is the
understand,
last day to upload all the details.
Yeah.
Now still, it is going on now also. It's not over.
Yeah. Yesterday also I had two talks earlier, and immediately I got into the talk for this conference because of 29th of June, National Statistics.
I think Professor Sinha is online. You can just convey the message to him, Satish.
No, he
hello,
told that
Professor?
he will be joining in 20 minutes time. So that's okay, no problem. Yeah. So regarding the book, even your, Satar is the head now, right, Satish?
Yeah, Professor.
He actually asked me the details of my books and all. So he told that he will be getting all the books in his library. That's fine. Now books will be available online also, but because of international publisher, it's going to be costly. So
I think
Amazon generally gives
the
30-40%.
library fund is there, one can afford.
Yeah, that's what you just get that book. Yes, that's going to be really.
This period, due to this corona itself, not much books are not purchasing.
Okay. Yeah.
The several. So there is a scope for excess fund.
How much is the cost? Is it in terms of pound or dollar?
It is going to be in dollar. It's going to be somewhere around 6,000
rupees.
Okay. That's not much.
No, 6,000 is not a big amount nowadays for a book because.
Yeah. 6,000 is not a big amount right now. Yes. See, that book actually I wanted to introduce to the Kerala Statisticians.
Professor, you just
in detail actually speaking. So I may look for some other opportunities where I can come and give a series of talks.
Okay.
Bala, it's you too also.
Yeah.
Kochi also,
So we'll see that. We'll see. We have enough time. So maybe in another 2-3 months, the corona will subside and movement. Even we can have it on webinar kind of thing also.
Okay.
Even from our side also, we are also getting busy every day now because the new semester is starting and other, activities like examination, everything is going on. So we can manage somewhere. No issue. I don't know. I was a bit apprehensive yesterday giving a talk in front of Kerala audience because yesterday I told you people are very strong in distribution theory, probability distribution, hardcore probabilitist. Okay, I like it. No doubt, I like it. I personally like the way you people are doing research. Now, quality management concepts.
But Professor, we have an applied statistics course. Applied statistics and data analytics program is here.
Data analytics. Yeah, that's what yesterday I stressed that particular point only. slowly and gradually the things are going to change in favor of statisticians. So we have to look for, in fact, we have to cross the boundary to some extent so that we can get into other interdisciplinary areas. And quality management is going to be a part of every activities.
Also in Kerala, we have started a series of MSc programs.
Yeah.
Data analytics as a specialization in this data
Right.
analytics.
Even MG University also started some new program on data analytics.
In Kerala, throughout in Kerala University, we have started it first. Thereafter, throughout in Kerala.
Okay, yeah. That's
several colleges.
Yeah, it's very good. Data analytics is very, very important. I don't know, from the audience who listened to my talk yesterday, if they wanted to say something, I would be really glad.
Yeah,
from the audience, please. Student audience I am talking about. That's good. Okay.
Do you get anything on chat box?
Yeah, chat box yesterday there were a lot of comments, and today's chat box I have not seen, so there will be many comments. Yesterday there were a lot of comments.
So, Satish, when is the next schedule starting?
At 8:10 to 8:55.
So, we have 20 more minutes.
20 minutes. I think we can break now then. In that case, we can break.
I think you can give some break and then you can join at 8:05 or so.
That's right.
Okay, Professor. That
okay,
also good.
Thank you very much.
Okay. See you then.
Okay.
Maybe you can just say that we'll resume at 8:20 or something. You can just display.
8:05. That's better.
Is there a provision to when you open the site? Is there a provision to display this? We'll resume soon like that.
Yeah. Okay. 8:05 needs to rejoin. Sudish.
Sadev sir?
Teacher?
Yeah, I'll come back by 8:05, sir. I have joined actually. Okay, anyway, I'll come back at 8:05. Okay, sir.
Okay. Next, you have to say something.
Yeah.
While in the meantime, I forget one thing. Yeah, it doesn't matter. Kimia Chinani, whether you are here in the group, Chinani? So you have to say, yeah. In fact, the next talk is mainly concentrating on CRAU. Bindu teacher, Dr. Bindu, you have, you don't know, I think so. You have to introduce Professor Gopal. And thereby,
Professor Gopal is the chair, right?
Yeah, chair.
Professor Gopal.
He joined in the meantime, but I think he has also say something in the meantime to these scholars. Okay, anyway, let us meet.
Meet at 8:05, sir. Okay, sir.
8:05.
Okay, sir.
Can take 10 minutes. Now 10 minutes. Yeah.
Hello, Nikhil.
Hello, sir.
Hello, Nikhil. Thank you.
Yes.
Satish, I'm
Hello,
ready.
Professor. Yeah.
I'm ready.
Yeah, Professor.
Whatever you are ready, I'm ready. Okay. You can put the first slide. Just make sure that everything is okay.
Yeah, okay. Okay, just try.
Yeah.
Okay. How is Professor? Please check.
Fine. Thank you. Yeah, good. If you can make it, like I don't know, like full screen or whatever, if possible.
Yeah.
If not,
Please make it full screen. Yeah. Nikhil will operate it from the other lab. Professor, you have to give next or previous. Then
yeah. Okay.
do
Yeah.
accordingly.
I'll mention that. Yeah, I'll mention that. No problem. So let's go back to slide 1 and we stay there.
Yeah, slide 1 again. Slide 1.
Yes, please. Yeah, and we stay there. Yeah, that's it. So Thomas Matthew's seminar was yesterday, right?
Thomas Matthew, yeah. He.
That was yesterday.
Okay. Yeah, yesterday.
Okay.
It's over. Yeah. It was excellent.
As always, yes. I know him. Yes. Yeah, I have known him since 1977.
Okay.
he came to ISPS Calcutta for his PhD, and I was there.
Yeah. Okay. In fact, one of our my teacher, Dr. Lesida, he is the classmate of Lesida.
Oh.
Yeah.
Oh, Thomas Matthew. I see. Okay. That's
Thomas.
wonderful.
Yeah.
Sir, Satish sir.
Yes.
I like to share a slide. I like to share a slide about. I like to talk something about Vimal sir.
Okay.
Please
sir,
go ahead.
Professor, not started yet.
Yeah. When you start, you let 2 minutes.
Yeah, we start right at 8:10.
Okay.
By the time I have informed all others to join at 8:05.
Right.
Okay.
So, yeah.
So, Dr. Gopal, please go ahead.
Professor Gopal?
Yeah.
Yeah, Professor Sinha is asking something.
I'm ready to listen to you.
Yeah.
Govinda, go ahead.
Yeah. This slide I want to show.
Okay.
It is 1 minute.
Satish, who is the chair of my session? Is that you?
Yeah.
Okay, so Satish, I have a lot of slides.
Okay.
So you can, but I can always wrap it up whenever you want me to stop. I can stop. Okay.
Okay, sir. Okay.
Yeah. Mine is not going to be technical.
You can talk. You can show a lot of slides about C.R. Rao.
Yes, that's what I love to do. If you kindly allow me, yes.
Yeah.
Good evening, Professor Sinha.
Good evening. Good morning for me. Good evening for you. How are you doing? Everything
I'm
okay?
fine. Thank you.
All right.
Okay.
How is the COVID situation in your city?
In our city, in the state of Kerala, it is still a constant level of around 10 is continuing. The TPR, that is test positivity rate.
Yeah, okay. It's not good. Not good. Huh?
Yeah. I hope Professor Nagaraja is back in Baltimore now.
Not yet. End of August.
End of August, okay.
Yeah. He was here for his daughter's graduation, but then he went back.
Okay, yeah. That I think, that I know. He went to US for graduation ceremony, yeah.
Yeah, that's right. But yeah, he's back, and then hopefully another couple of months he'll be here.
Okay.
Hello, Bimal.
Hello, hi. How are you?
How are you doing?
Hira, please come and visit us. I know you have a relative in Colombia. Come, please. Whenever you come, let me know. Okay?
I was thinking of that. It was a year and a half since. I was supposed to come there last September. Remember that?
I remember that. Yes. It will be whenever you want to come.
Are you going to be there in end of July and August? Are you going to be there this July?
Yeah.
Of course,
end of July,
we're thinking of traveling end of July, and maybe I'll send you an email.
Sure, please do that.
Yeah. So, did you continue your bridge activity during this one last year, or was there some slowdown in that?
Let's slow down. Yeah. Right.
Slow down. Yeah. Let's see. So, Bala, how are you doing?
I'm good. I'm good. I think I sent an email in the evening today.
I saw it.
Okay.
But I haven't gone into it yet.
Okay, let us start our session.
Okay.
Now it's the time, and this session is, in fact, dedicated to Professor C. Rao, or in honor. This session is arranged as in honor of Professor C. Rao. About that, more than that, our Professor Sinha will also talk about C. Rao. It's in this real dedication, in fact. And this session, to chair this session, we have Professor Gopal, who is with us. And to support him, Dr. Bindu Krishna is also here. I invite Dr. Bindu Krishna. Bindu Krishna is presently Associate Professor of Department of Data Analytics and Statistics of Jain University. And she will introduce Professor Gopal, and thereby Professor Gopal will start the session with all the other proceedings. Yeah. Dr. Bindu, you please support
Yes,
Professor
yes,
Gopal
yes.
in all ways, in whatever
Yeah.
way. Yeah.
Good evening and good morning to all dignitaries. Of course, as Professor Vimal said, it's good morning to dignitaries. And Professor Gopal is the head of the department. He's the professor and head of Department of Statistics, University of Madras. And as Dr. Sadiq sir said, this is a specially invited session in the honor of Professor C.R. Rao. We statisticians don't need any introduction or anything from about this eminent, well-known personality. So straight away, I am moving to invite the chair of the session, Professor Gopal sir. Gopal sir.
Okay.
Okay, sir.
Do you see the screen? Do you see my screen?
But we can hear you, but your camera is off, I think.
I see. Yeah.
Is Malino's picture part of your screen?
No, he's coming.
Then we cannot see your screen.
Okay. Do you see my
Yeah,
screen?
now we are visible, yes.
The screen is there?
I don't see it. I don't know others.
Okay.
Yeah, but I can see Professor Gopal now.
No.
Yeah, okay.
It's screen. I am presenting something.
Yes, sir. It's visible.
You mean the Malnabi's picture?
No, the Word file.
No, it has not come. So you have to choose that present now option.
Yeah. Present now, the
entire screen.
It's there?
Not yet.
Okay, now I will just read. Voice is there?
Yes.
Yeah. You're audible. There is no problem.
Okay, that is fine.
Yeah.
Good evening, good morning to one and all. I am thankful to Professor Satish Kumar for permitting me to chair a session in WSTA 2021 organized by Kerala University. In fact, I am delighted to chair a session in honor of Professor C.R. Rao, the living legend, Padma Vibhushan awardee. I am specifically mentioning this award, only this award, Padma Vibhushan award, because we organized one program to honor Professor C.R. Rao at the University of Madras in 2006, and we printed his name, Padma Vibhushan C.R. Rao, and extended the invitation to him at his house. Immediately what he told was, this is not the right way to present my name, Padma Vibhushan C.R. Rao. You'll have to say Padma Vibhushan awardee. Like that, he mentioned by his own name. Then we reprinted the whole invitation. That is how C.R. Rao was so meticulous in everything. Anyway, please, sir. Yeah. Now I will just give you a brief profile of Professor Bimal Kumar Sinha. Professor Bimal Kumar Sinha and Professor Vikas Kumar Sinha, another renowned statistician, are twins. Were born to Brendranath Sinha and Jogmaya Sinha on 16th March 1946 in Babna in Bengal, the undivided India, now in Bangladesh. Professor Bimal Kumar Sinha being elder of the twins, the present speaker. The Sinha family migrated to Kolkata, now Kolkata, in 1958. The twins were extremely notorious and gave hard time to their mother, elder sister, and the near relations with the daytime harmful activities. Sinha brothers got admission in class 8th in a local school. They showed very early promise and secured top position in school exams. They passed the school final exam, class 10 in 1961, and got admission into pre-university course, 1-year course. In 1962, they got admission into 3-year degree course in a college under Calcutta University with honors in statistics and mathematics and physics as combination subjects. In 1965, they passed out with statistics honors in Calcutta University exam, holding first class first and first class second positions. Therefore, the first and second positions were shared by the twins. In 1967, they passed out in MSc Statistics from Calcutta University, again holding the top positions. Professor Bimal Kumar Sinha is senior of the twin brothers, and he held first position in both exams. During 1968-1961, they carried out doctoral research under the guidance of Professor H.K. Nanti in the Department of Statistics, Calcutta University. Professor Bimal Kumar Sinha worked in the area of Bayesian inference, while Vikas Kumar Sinha worked in the area of optimal designs. They were awarded PhD degree in statistics of Calcutta University in 1972-73. This is about the twins. Now about Bika Sinha only. Professor Bika Sinha joined the Indian Statistical Institute, ISI, Calcutta in 1971 and stayed until 1974 and left for the University of Montreal in Canada for his postdoctoral research. After staying for 1 year, 1974-75 at Montreal, Professor joined the Department of Mathematics Statistics at the University of Pittsburgh in 1975 and stayed there for about 10 years. In 1985, Professor Sinha joined the University of Maryland, Baltimore County, UMBC, as the founder statistics of the graduate program. He worked extensively on the number of research topics during the last 50 years, published numerous original articles in international journals, produced 30 doctoral students, and became IMS and ASO fellow. Due to his singular contributions in statistics, UMBC honored him with the title UMBC Presidential Research Professor. The University of Maryland, in recognition of Professor's tremendous contributions in statistics, offered him the title USM Research Professor. Professor Bimal Kumar Sinha's research contribution is global, with collaborators from many countries including Australia, Canada, India, Thailand, Japan, Taiwan, Germany, Sweden, and Portugal, to mention a few. Professor is co-author of 4 books, Academic Press 1, John Wiley 2, Springer 1, and has written more than 130 research articles with his national and international collaborators and students. Now it is time for Professor Bimal Sinha's session. Now I request Professor Bimal Sinha to proceed with his session. Thank you.
Thank you. Satish, I thank you for the kind invitation, and I thank Bindu and Govind for your kind words. And of course, I thank all the participants. It's very nice to be here all there virtually. But I see my Dada, Hirada, Dada Namaskar. Yeah, so Sunil, can you put on the first slide, please?
Yeah, Professor. Yeah, please.
Thank you. So yesterday we had National Statistics Day, June 29. So we have been celebrating, particularly it's national in India. So we have been celebrating National Statistics Day every year on June 29, which is the birth
Wait a minute.
of the
Wait a minute.
founder.
Wait.
Yeah.
Yeah. And if you can make it slightly bigger. If not, it's okay.
Wait a minute. Yeah.
Yeah. Good. Thank you. Yeah. So yesterday we celebrated the National Statistics Day, which is also the birth date of the professor at ISI, PCM, was born in June 29, 1893. And it was a very nice event yesterday. So I gave a lecture on the same topic yesterday in another school. And as you know, PCM, not only the founder of ISI, and he was the brain behind getting statistics in India way ahead compared to the rest of the world, compared to USA. That was back in 1925 when he invited Fisher to come to India. Of course, at that time there was no ISI. 1925, it used to be physics department in Becker Laboratory. Anyway, Fisher did come and they had some discussions, and that was the seed for starting the ISI, which was founded in 1931. Initially, the teachers were, PCM, our professor himself, and then R.C. Bose and S.N. Roy. But in the late 40s, right after the Second World War, both Bose and Roy, they left. They came to USA. They joined Chapel Hill. So professor was all by himself, essentially. Who took the responsibility to guide? Professor also was getting old. Who took the responsibility of shouldering the ISI and marching forward, keeping holding it very high? It was C.R. Rao. So today's session is on C.R. Rao, and I was very lucky and I was blessed not only to be a faculty at ISI, ISI Calcutta, that was in the early 70s, but I had the good fortune of being his colleague at the University of Pittsburgh for a number of years. Before I moved to UMBC, that was in the early 80s. So I want to tell all about that. Okay, so let's go to the next slide, please. Good. As Gopal mentioned, so during 60 to 65, my twin brother and I, so every day I remember our academic fathers. We all should, our respective academic fathers, So on the left is Dr. Chaudhuri, who taught us BSc Statistics Honours for 3 years. On the right is Professor Nandi, who taught us at the University of Calcutta, Masters, and then later on, of course, is our doctoral dissertation advisor. One more thing about Professor Nandi, when 1941, so ISI was founded in 1931. 10 years later, in 1941, the first postgraduate school statistics at the University of Calcutta. That was the first in the whole subcontinent, Indian subcontinent, nowhere except the British school. No stat back then in USA also. It all started around the Second World War, So that we had a really head start. So 1941, first batch of master's students started, and C.R. Rao and my advisor, Professor Nandi, they were classmates in the very first batch, 1941, 1943. 2 years, they studied together. And of course, after that, my advisor stayed with the University of Calcutta, which is in the south of Calcutta. And Dr. Rao, by then ISI was there, and Dr. Rao followed Mahalanobis naturally, and Dr. Rao moved to ISI Calcutta. So that's, in the South Calcutta is the University of Calcutta, and North Calcutta is the Indian Statistical Institute. About 1 hour drive, But of course, both Professor Nandi and Dr. Rao, they were busy, extremely busy in their own worlds, teaching and research and all that. Dr. Rao was, of course, extremely busy, and so was Professor Nandi. And Professor Nandi guided as giants, the giant like P.K. Sen, J.K. Ghosh. They are his, of course, myself and my twin brother. So Professor Nandi really had a very illustrious career, So Nandi and Rao, they met very rarely. Naturally, both of them were, and Dr. Rao, of course, he was traveling also. I remember on one occasion, that was 1969, the Indian Science Congress was held in Calcutta. And now I see that, I was a research scholar then, and my brother also. So we see C.R. Rao and Professor Nandi, in that open area, Indian Science Congress, big area, like a Maidan. So they are, they're approaching each other, and then, oh, what a beautiful. We had no cell phone back then, it would have been so nice. What a divine scene. They approached, then they embraced each other, Then they talked, maybe about 10-15 minutes. Or we could watch it only from a little bit of distance, What a beautiful scene. So I saw C.R. Rao. That's the first time I saw C.R. Rao. C.R. Rao and my advisor, they're together, That what a beautiful scene. Anyways, I pay my homage to my academic fathers, and I remember them every day. On days like this, Teachers' Day and National Statistics Day, we should definitely. So I pay my respect. Now let's go to the main event, C.R. Rao. Next slide, please. Born on September 10, 1920. Think about it. And Dr. Rao is still alive. So last year, globally, it was global celebration of his birth centenary. That in many places, of course, including ISI, and there are some conferences, national, international, all sorts of. In the USA also, there are many conferences. I took part in some of them. So Dr. Rao, naturally, as you know, legendary statistician, kind of a global figure, and maybe father of statistics. And by now, maybe grandfather of statistics. And undoubtedly, he's the number one, and he's the number one among the. He has always been number one among all the statisticians, living or dead. So on this, so today definitely we pay our respect to Professor C.R. Rao. Let us see how he started his life, and then slowly how he became, what he became. Okay, that's the idea. Next one, please. So what I'm going to do, I'll discuss some of my direct interactions with Dr. Rao, because I was his colleague for a number of years. I'll also highlight a few papers of Professor Rao towards the end, maybe how his papers on asymptotic theory. I know my Hira Dr. Kaul is an expert on asymptotic theory, but anyway, for me it was something new. How Professor Rao's initial work or fundamental work on asymptotic theory, how it motivated me during my very early career in the 70s and 80s. I was just a fresh PhD back then, So I'll mention how Dr. Rao's work influenced motivated me. Okay, next one, please. All right. So in summer of 2016, exactly about 5 years back, my brother is a frequent visitor USA, because his son and daughter, they are both in US. So Bikash will come to every year he will come. So we made it a point to visit Dr. Rao. He was 96 then, at his residence. Actually, he has been staying with his daughter Teja in the city of Buffalo. So we decided that we must meet him. So we are in touch with Teja, and Teja said, no problem, please come. And of course, both of us were very close to Dr. Rao. I was his colleague, and Bikash also, he's taught at the Indian Statistical Institute 1980 until he retired a few years back. And Bikash's doctoral dissertation, Dr. Rao was the external examiner. So Dr. Rao knew about Bikash's research also. And when I joined ISI in 1971 as a faculty after completing my PhD, so Dr. Rao knew about me also. Anyways, but of course I did not meet him at that time. He was in Delhi. So anyways, we made it a point. And we have here Dr. Kirti Shah, one of Dr. Rao's very close students, and very close, Dr. Kirti Shah from Waterloo. So we made it a point to visit Dr. Rao, and we spent one entire day. Dr. Rao, being 96, still he was very alert. He alert, and he has one nice room with all sorts of pictures all across the world. All pictures, all sorts of national, international pictures, and he also told us his old stories and all that. So he could recollect most of what happened way back in his career. So that was very, very nice experience for us. So I thought that I should share this picture. Okay, next one, please. All right. Now remember, there's a saying, and I think it is rightly so, that the eighth born child is destined to be famous or extra famous, whatever you say. So right now we have, remember in Dapur Jug, we had the Sri Krishna, Lord Krishna, eighth born, And now, of course, in Kali Yoga, we have C.R. Rao, the 8th born. In this, it's a huge family. You can say Dr. Rao was the 8th born, and naturally, certainly he was destined to be famous. And you see that, yes, he was like kind of world famous, Next one, please. A family picture. Yeah, next one. Yeah, a family picture, this is the 1931. So Dr. Rao was about 11 years old right here, along with, the parents, father here, mother here, and, other family members. Remember, 8 of them, and then plus auntie and all that, So it's a huge family. Next one, please. We have a picture of Dr. Rao at the age of 15. That was in 1935, out of his college magazine. Next one, please. Okay, this is very interesting, So Dr. Rao had a master's in math, pure math, I think from Andhra University. He got the degree in 1941. Think back, 1941. So we are talking about a long time back, 80 years ago. What happened? No job. Think about it. It's the British period. You have a degree in math, no job, nothing, So one of his relatives suggested that, well, it's a small town. Why don't you go to Calcutta? That's a big city. There are, we have the University of Calcutta there. And that relative heard about Indian Statistical Institute. Not knowing much, something like the ISI is there. I don't know what it is. But why don't you go there, go to Calcutta, try your luck, and maybe you'll be able to find something. And this is all fact. Hard fact of life. So here is Dr. Rao coming to Calcutta, not knowing anybody, no place to stay, no money, no Bengali. That's the language in Calcutta. So think about it. At the tender age of 21. Now you can all think what we did at the age of 21. What did we do? Nothing. I was just doing my master's. That's all. Think about going to another city, looking for a job. So only God favored C.R. Rao. Otherwise, it could have been down the drain. That's it. So God was there to guide him through. It's so nice, Think about it. You have to believe in fate. So Dr. Rao comes to Calcutta and he meets PCM, the professor. Okay, you have a degree in math. I'm not a mathematician. I started one ISI, something like this. And then if you want to, you're looking for a job, I can give you some desk job. I have some data. You can take a look at the data and do some, you can look at the data and do some punching and all that. That is the kind of job. Small money you can get. Maybe you can survive in Calcutta. And by the way, we also started this master's program. First time, postgraduate degree, master's program. We just started it for 2 years, 41, 43. If you want, I can enroll you in the master's program in Stat. So you have a degree in math, get a degree in Stat, another master's in Stat, and maybe your luck will favor you after that. But other than that, right now, I don't have any job for you. So think about it. So Dr. Rao, why not? So they are the first batch of students, 41, 43, along with my 15 others. But my advisor, Professor Nandi, also was a classmate. So 1943, done. Gets a master's degree and starts teaching at the University of Calcutta. My advisor also. I think in most Indian schools, that's what happens. You get a master's degree, then you start teaching. And then slowly you work your way up, get a PhD, part-time and all that. So Dr. Rao also started teaching at the University of Calcutta right after his master's. Back then, the University of Calcutta was a part of Becker Laboratories still in central Calcutta. Part of what I studied at the University of Calcutta, that's a different building. That was in the 60s, So back then it was still there. Anyway, so Dr. Rao started teaching. And we all know the famous story about Rao-Kramer inequality, So anyways, I'm not going to go through the details of that. So anyway, Dr. Rao proved what a beautiful. That's the cutest result in stat. Simple idea, so powerful, so useful. But Dr. Rao didn't realize that something he did which will make him so world famous. And that was naturally he didn't realize that at that time. Over time, of course, it becomes like that. Anyway, so Dr. Rao, and then PCM asked him to join the Indian Statistical Institute. That's what Dr. Rao did. And then PCM sent him to Cambridge to work under Fisher. So you see, there is Mahalanobis and C.R. Rao. You can see the bonding. So Dr. Rao went there and got his degree, came back. Now there's a nice story here. R.C. Bose, S.N. Roy, they left India just right after the Second World War. They came to Chapel Hill. So Dr. Rao, after finishing his degree from Cambridge under Fisher, he had the opportunity of goodbye, bye-bye to India. He had the opportunity. Already he was very famous by proving a lot of results and doing nice work. He had the opportunity of settling, coming to US, getting settled here, or go to whatever he wanted to go. But Dr. Rao made it a point. You are so kind of obedient in a way and very close to Mahalanobis. He promised Mahalanobis, right after my degree, I'll go back to India. I will be there with you as long as I'm permitted to work in India. Back then it was until the age of 60. So Dr. Rao came back and immediately PCM created this Research and Training School, RTS. When I joined RTS. So within ISI, we have this Research and Training School, RTS. So Dr. Rao, PCM established this RTS and told C.R. Rao, you are in charge, you're the director of this Research and Training. You guide it through, you make it however big you want to make it. Money is not a problem. Luckily, Mahalanobis, he was also the member of the first planning commission and very close to the Nehru family and Nehru also. So money was not an issue for ISI. So Dr. Rao got the free hand to build up the Research and Training School in ISI. So that was a kind of clue. And Dr. Rao, of course, stayed until he was 60. So he kept his promise to the professor that yes, and of course PCM. When I joined in 1971, in 1972, Professor passed away. But anyway, Dr. Rao stayed there all the way, as long as he could. Next one, please. So that's the Becker Laboratory. That's what Dr. Rao studied. During my time, it moved to, there some beautiful pictures of the University of Calcutta. Department of Stat was on the 5th floor. That's where I studied. That's where P.K. Sen, J.K. Ghosh, we all studied in this building. Next one, please. Yeah, Department of Statistics, University of Calcutta. Okay, we call it CARDS. Next one, please. Yeah, so so think about it. 1941, when C.R. Rao first went to Calcutta. Of course, this is a much newer building and gate and so on. But ISI was there, and Dr. Rao entered, or Mr. Rao, C.R. entered the campus of ISI as just an ordinary worker, barely trying to survive with a small job from Mahalanobis, doing some data punching and all that. That was his first entrance to this beautiful, world-famous campus. Years later, he became all in this. He became the director of the Indian Statistical Institute, and prior to that, he was the director of RTS. So that is the main gate of. I'm sure most of you or some of you have visited ISI. Next one, please. Yeah, that's the main RTS. When I joined in 1971, that was the building. So you can see how many hours Professor Rao and of course all of us who spent in this building, and you can see particularly how how seriously Dr. Rao worked here, for about 30 years, in this place here, and how dedicated this place was academically, So it's very, very nice academic atmosphere here. Next one, please. Yeah, so this is a library building. So you can see, you can just imagine that, how many hours Dr. Rao spent in this library, trying to prove theorems, and he worked on so many areas, so many topics. Next one, please. Then the time came. Yeah, I said Delhi Center. In the late 60s, we had this Naxalite movement. So we had a campus of ISI in Delhi. That was the second campus. Right now, I think there are about 6 all over India. So Calcutta was number 1, and then Delhi was number 2 back then. And because of the Naxalite movements and all that, it was not very pleasant. Also, many people left Calcutta. So I think PCM, through the blessings of PCM, the Delhi Center was created, and Dr. Rao moved to Delhi. So when I joined ISI in 1971, I did not see Dr. Rao. Maybe once in a while he will come for some meetings and all that. But Dr. Rao was permanently in ISI, Delhi. Next one, please. Families. It was time for him to get married. Yeah, we can go through some of these slides quickly. Yeah, so Dr. Rao getting married to, right here, wife is Bhargavi. By the way, Mrs. Rao, of course, I think I certainly know her very well. I'm sure some of you, or maybe most of you, know her. Very, very sweet lady, very nice, and of course, extremely bright also academically. So very good match for Dr. Rao, and an excellent cook also. Because we stayed so close. In Pittsburgh, so we visited them quite a few times. Next one, please. Okay, now comes the family, the son Veera and daughter Teja. Of course, they are grown up now. Teja herself a doctor, faculty, and he's an engineer. So there's early in there. This picture, by the way, is in ISI Calcutta. Next one, please. Dr. O is very fond of children. So some of these rare pictures you can see. Next one, please. Yeah, now the children are grown up. They're still in Calcutta. Next one, please. Yeah, now you can see the ISI annual convocation shared out the professor. As he was referred to, by the professor we really meant only Maulanovish. Next one, please. Yeah, so you can see, beautiful picture here with Fisher. Cambridge University with Fisher, Ronald Fisher, right here, discussion, showing some data and making some discussion. All right, it's a nice picture of Dr. Rao, very, very nice. Okay, next one, please. I think this is one of the Indian Science Congress sessions. We see so many Indians. Dr. Rao is here. Next one, please. Yeah, it's a very nice picture with Bartlett. Remember the Bartlett collection? So that Bartlett is here. Bartlett with Dr. Rao. Next one, please. And Dr. Rao, is very well. This is another. The Holden. He was at ISI. So the Maulanovish and wife Rani Maulanovish. By the way, because they didn't have any children, Maulanovish couple, so they considered Sher Rao as their own child, So Dr. Rao was very close to the Maulanovish couple and the family also. Next one, please. Rao Kramer inequality right here. Wow, what a nice picture, huh? Black and white. Rao Kramer inequality. Rao and Kramer. This is with Yeardsley Neyman at Berkeley. Dr. Rao with Neyman. Next. Rao Blackwell theorem. Wow, what a nice picture. I think it is during one of the World Congress of Mathematics. So David Blackwell represented USA and our Dr. Rao represented our country, India. Excuse me, I'll be right back. Okay, I'm back. I'm joining now.
Yeah, Professor, continue.
Yes, can you hear me? Okay, good.
Loud, Blackwell, clear.
Okay, next slide, please. Thank you. Okay, now, Dr. Rao, and naturally you can say they're very close and close bonding. Dr. Rao, you just came back from Cambridge, so British dress, beautiful. By the way, modern innovation, I met him, I joined in 71. I saw him briefly a couple of times in ISI, Calcutta. He's very tall, like a British complexion, dressed also like British, Okay, next one, please. After coming back from Cambridge, Dr. Rao teaching at ISI, and you see the British dress here. And I remember, I attended many lectures by Dr. Rao at the University of Pittsburgh. Very nice handwriting, a little bit curly and very nice handwriting. Next one, please. Highest honor in India, 1968. Highest civil honor. Next one, please. Okay, now let's see what's going on. 1979, Dr. Rao is 59. He made a promise to PCM. He would stay as long as he was allowed to stay, allowed to work, permitted to work. The retirement age is 60. Now it is 65, but back then it was 60. Dr. Rao is thinking now, well, so I'm 59. I kept my promise to my mentor, to my professor. Now I have to retire. What do I do now? So he had a choice of staying back in India, doing something, or maybe coming abroad, going to any. He could go to probably in almost any country, And by then, he was so famous. So we are, USA. That was very fortunate that he chose to come to US. And the person who was instrumental, two of them, one is Rustagi. So Rustagi from Ohio State, the Ohio State, invited Dr. Rao to come to Ohio State University for a year or so. And then very next year, P.R. Krishnaiah, who was at the University of Pittsburgh, and that's when I was there, P.R. Krishnaiah was able to extend a very nice invitation to C.R. Rao to join the University of Pittsburgh as kind of chaired professorship. And that was in 1980. So next slide, please. Yeah. So P.R. Krishnaiah was instrumental in getting Dr. Rao with Mr. Rao at the University of Pittsburgh. Actually, it was in 79. So 78, Dr. Rao was the Ohio State University. 79, he joined Pittsburgh, and I joined in 1980. So we had a few 80 until 85. So we had a few years common. But so Krishnaiah was really instrumental in getting Dr. Rao. Okay, next one, please. Okay, next one, please. So you can see. Yeah. Well, so it's a very nice picture. 1980, Dr. Rao was 60. So I was there as a junior faculty, and not so junior, I was an associate back then anyway. So Dr. Rao was 60, and the department, all of us, we celebrated his 60th birthday. And by then, there are about 25, 30 Indians.
Who is that guy? Who is that guy who got a hair on head?
What is it, Hira?
Who is that person who got a hair on his head?
I cannot hear you properly.
Okay, fine.
Sorry, yeah. Okay, anyway, so you were there, Hira? Did you attend? Maybe you did.
And last year I did.
Oh, you did, okay. That's nice, that's good. Okay, anyway, so 1980, but the point I want to make, so Dr. Rao, of course, he thanked all of us. He thanked the department for arranging his the 60th birthday celebration. But he also admitted Dr. Rao admitted with tears in his eyes, I remember, with tears in his eyes, he admitted that he was one of the 8 children in the family. No concept of celebrating a birthday. Only 8 of them. And, so the whole concept was not there. Maybe Dr. Rao's mother will make a little bit of maybe one spoonful of, we call it prasadam, pious, something like that. But there's no celebration. So he admitted that first time in his life at the age of 60, and he was deeply moved, and so are we, that at the age of 60, the first time there was a formal celebration of his birthday. So very, very nice. So I just, this picture, I asked Doctor, I'd like to have a picture with you. I'm so happy that he agreed. I'm glad he agreed. I took the picture and I saved the picture, so I can share with you. Next one, please. Yeah. A little bit of technical, not proving any theorem, So we call it Rao number 1. There's a number. This is a kind of idea, If you have a paper with Rao, Dr. Rao, then you are Rao number 1. If you don't have a paper, you may have a paper with like Hira. Hira has a paper with Dr. Rao, then I become number 2, like that, But fortunately, I was Rao number 1 because I had a direct paper with Dr. Rao. So this is the paper. 1982, it appeared in Statistics and Decisions, so along with Kasala Subramaniam. So what is the background of this paper? A little bit of background of this paper. Next slide, please. Okay, so that's at the University of Pittsburgh. I did not know that University of Pittsburgh was founded in 1787. So that's the campus of the University of Pittsburgh. Here is a big tower. Here we call it the Temple of Learning. Next one, please. Yeah, so that's what I spent. Dr. Rao also spent about 5-6 years here. Okay, and then I left Pittsburgh in 1985. Dr. Rao left in 87. That's because Krishnaiah, unfortunately, Krishnaiah passed away in 87. He developed kind of cancer, and that was very, very sad. Next one, please. Yeah. So this was during our stay in Pittsburgh. You can see the all Indian faculty, Indian friends. So we invited all of them. Here we have Dr. Rao. Then we have Krishnaiah here. Thomas Matthew is here sitting. This is Thomas Matthew and myself here. So Thomas, naturally you are very young then. 82, long time back. Next one, please. So this is a very nice picture, Dr. Rao, and as you can expect. So and when I saw them also, they are very, very close. Dr. Rao was like an elder brother figure for Krishnaiah, naturally, and Krishnaiah had a lot of mutual respect for each other. And I was very close to both of them. By the way, Krishnaiah, he was the founder of the CMA, Center for Multivariate Analysis at the University of Pittsburgh. He is also the founding editor of JMA, the Journal of Multivariate Analysis. Okay, next one, please. Yeah, I want to draw your attention to this picture here. C.R. Rao and J.K. Ghosh, Jayanta Kumar Ghosh. Jayanta Kumar Ghosh graduated from the University of Calcutta with a PhD under Professor Nandi. And Nandi is a classmate of C.R. Rao. That's the connection also is there. Anyway, J.K. Ghosh, after his PhD from the University of Calcutta, he came to Urbana-Champaign, spent a couple of years, went back direct to ISI, joined ISI, later on to become the director of the Indian Statistical Institute. He also became the president of the International Statistical Institute, just like C.R. Rao. Now, between the two, it's amazing that between the two, Dr. Rao knew that, Jayanta is a student of Nandi, and Nandi is classmate and a friend of Dr. Rao. But between the two, they had a nice bond. I have seen it so many times. So J.K. Ghosh regarded C.R. Rao as his kind of mentor and guru, classmate of Professor Nandi, And between the two, lot of admiration of respect. I can say that among all the Indian statisticians, C.R. Rao had utmost respect for J.K. Ghosh. I'll tell you why. Jayanta, what he did during his prime time, he read all papers of C.R. Rao. We are colleagues together. I've seen Jayanta, so we are kind of family friends. So Dr. J.K. Ghosh read all papers of C.R. Rao to get the ideas. What are the so many beautiful ideas in Dr. So once J.K. Ghosh told me, you must read C.R. Rao's papers also. We should all read, just to see the variety of ideas and the wealth of information in his papers. Anyway, that's what Jayanta did. Not only that, he picked up some problems from C.R. Rao's papers. And he went deep into it and solved those problems. So J.K. Ghosh, of course, he's no more. He was at Purdue. But during his prime time, he became the #1 asymptotic theorist in the world. J.K. Ghosh, he wrote so many fundamental papers on asymptotic theory, getting ideas from C.R. Rao's papers. So they had a lot of respect for each other. Okay, next one, please. Okay. So I'm a faculty at ISI Calcutta. That is why I joined in 71. So 72, J.K. Ghosh is there as a faculty. Molloy Ghosh is there. And D. Basu is there. All these big people are there. I'm just a junior faculty now. Now I see that there's a paper. Sankha is our own journal. This is ISI journal. This paper it came out in 1974. With J.K. Ghosh and one of his students, Kasala. Something called the second order efficiency of MLE. So now I'm wondering, so I know about the maximum, and by then I had a PhD and I was teaching at ISI. So I thought that MLE I know. What is second order? No idea. What is SOE? So I thought that, let me read this paper. Let me get an idea of, what is the second order efficiency and all that. So what I did, I just go to the library and get a copy of this journal, and I took it home, hoping that I should be able to read it very quickly, and maybe next day, and I'll have very good idea. And if necessary, I can talk to Dr. Ghosh, and I can see what's going on. So that was my hope. Okay, all right. Next one, please. So at home, I opened this paper, and I read this, and among other things, there's a theorem here. And it was, so shocking with a PhD in stat, about 2-3 years of teaching experience at ISI Calcutta, teaching all those giant, super brilliant students in ISI. I did not have the foggiest sense of what is in this paper. It was disbelief, and I felt so bad for myself that I have a PhD, I know nothing. So you should never feel bad, That was the feeling I had. This paper by J.K. Ghosh, I don't know, I'm sure Hira and some of you are maybe interested, or maybe familiar with papers by J.K. Ghosh. Anyway, I felt so bad. What is going on? Why do I have a PhD in stat? And I was already teaching in ISI, master students I was teaching, undergraduate and masters. So I felt so bad, what is going on? What's wrong with me? I read it over and over again. No, nothing. Then what I did, I went to the end of that's what you all do. I went to the end of the paper, look at the references. Maybe I should read some background material, before I delve into understanding what is in this paper. So I went to the list of references, and that was the turning point. Go down, please. Beautiful papers by C.R. Rao in a sequence. We call it trilogy, 1961, 62, 63. First, fourth Berkeley Symposium, 61. I'm sure here I must have read all these papers. The 62, JRSSB, 63, Sankha. So these are the key papers behind Jayanta Ghosh's paper. Then immediately I grabbed these papers. I really request, of course, those of us who work in asymptotic theory, we do, but just for fun, if you have time, you don't have to work on asymptotic theory. Just for fun, please read, some of these papers of C.R. Rao. It's a beautiful paper, not deep, not deep mathematics, ideas, lot of ideas in C.R. Rao's papers, because he wrote so many papers based on so many ideas, So that work really influenced me. That's what I did all these papers multiple times. Then, yes, that I could see what's going on. Then I could read J.K. Ghosh's paper. I could understand. So it took some effort. So I really, I was challenged, and I wanted to be really make sure that I understand it. And luckily, in ISA, you have the academic atmosphere also. So really, my heartfelt thanks and a lot of pranam to C.R. Rao for writing these beautiful papers. Not just me. Dr. Rao motivated so many people worldwide. Okay, next one, please. And now, so with this motivation from that I was able to write a paper with J.K. Ghosh. It appeared in the Annals of Statistics, another paper in the Annals, another paper in our local bulletin. And so all the next one, please. So I was able to run. I wrote here some papers here, some different journals. This one, of course, with Dr. Rao himself. So that was kind of, a lot of motivation from Dr. Rao's work. Okay. All right. I just continued working and so on. Next one, please. Yeah, we call it the Fabulous Five students of Sierra, among many, among many, the Fabulous Five. Fortunately, I know all of them. We should, D. Basu, then KRP, then V.S. Varadarajan, then Varadan, and Rango Rao. So all these are very famous names. We call it the Fabulous Five in ISA. By the way, all their PhDs are from the University of Calcutta. ISA, during that time, ISA did not have the granting authority, the degree granting. All of them they're from the University of Calcutta. And then, of course, later on in the 60s, ISA started giving master's PhD and so on. Next one, please. More than, as we all know, more than 35 honorary degrees globally. And I have some pictures here, maybe I can stop here. We can go all the way at the end. Yeah. I have a lot of pictures, so we can see some of these pictures. If the time is...
Exact number is 39 degrees. 39 university degrees.
Yeah.
39.
39. Maybe by now it is 39. Okay. I think when I prepared the slides, okay, you're right. Yeah, 39 now. And we are working on number 40. There is one university in Bangladesh, but they are putting together some papers, so this might be number 40. Anyway, we can go to the end, please. Almost to the end. Go down, please. Okay. Yeah, there is one nice picture. Yeah, next one, please. Yeah, next one. Yeah, right there. Bush. This happened in inside the White House. President Bush. That was in 2002. National Medal of Science. Okay, next one, please. And among many others, nice picture of Dr. Rao. Happily married couple. Unfortunately, Mrs. Rao passed away a couple of years back. So Dr. Rao, kind of a sad life now. Next one, please. I want to skip it. Next one, please. Yeah. So on September 5, 2020, last fall, there was a global ceremony of global, birth centenary celebration organized by alumni of ISI. I'm sure, maybe some of you or most of you may have attended. I was virtual. It was a virtual celebration. So you can see the screen, the back, many people attended. And, at the end, Dr. Rao, in his feeble voice, he thanked all of us, and he said a few words. So that was on September 5, 2020. And 5 days later, next slide, please. This is my last slide. On September 10, 2020, on the day of his birth centenary, on behalf of the statistics faculty at UMBC, we are 11 of us, myself and my colleague, Dr. Matthew is here. Dr. Matthew, Dr. Nichol, Nagraj is here, Dr. Ryan, etc. On behalf of all of us, we sent this nice card to Dr. So my pranam to Dr. Rao. Dr. is still alive. Bless us, bless all of us, Professor Rao. we wish you a happy, healthy life as best as you can. Thank you. Thank you so much for your attention.
Thank you, Professor, for your nice lecture on Professor C.R. Rao with a lot of photographs. Anybody needs any clarification from Professor Bimal Sinha?
Pardon?
Thank you, Professor, for your nice lecture.
Thank you. Thank you.
Over to Dr. Satish, sir.
Thank you, Professor Sinha, for an excellent narration of Professor Rao and his works, days of the ISI days, everything.
Yes.
In a very beautiful way.
Excellent,
excellent, Professor. I shall try to send it to Professor Rao in the meantime.
Oh, that would be nice.
The record.
Please do. Thank you.
Yeah.
Thank you.
Okay. Thank you so much.
Bye-bye.
Thank you. Yeah.
Bye-bye.
In fact, on behalf of the Department of Stats, University of Kerala, we extend our gratitude to you, Professor, for your nice session of our great giant C.R. Rao in the area.
All time
And
great.
also,
All time
Professor,
great. Yes.
Okay.
yeah, for chairing this session. Yeah.
Okay, thank you, sir.
Okay.
And Professor, okay. Dr. Bindu also.
Okay, Bindu, I thank you.
Yeah.
Govind, thank you. Satish, I thank you.
Thank you.
Okay.
Thank you, sir.
Yeah, Professor. Gopal sir has given a better introduction.
Yeah.
Gopal sir. Yeah.
Thank you, sir. Thank you.
Sir, also new to me. Yeah, it was the audience.
And I'm getting some chat comments. I thank all of you for your nice words.
Yeah.
For your kind words. Stay safe, okay?
In fact, I read this article. The twins has written an article about themselves.
Oh.
Thank you.
Okay. All right.
Thank you.
Bye-bye.
Okay, bye. Thank you all. Thank you so much. Now let us move to the session. In the next session, we have two speakers, Professor Peter Lohamander and Professor Violeta Piparu. To chair this session, we have Professor Srinivasa Rao Gede. And to support him, the Sister Josephine David, Dr. Sister Josephine David to support him. So please, Sister,
Yes.
give a brief introduction about our Professor Gede, and thereafter Professor Gede to take over the other proceedings of this session.
Yes.
Okay, welcome to all.
Thank you, sir. Good evening to all. It's my great pleasure to introduce Chair of this session, Dr. Srinivasa Rao Gede, Professor of Statistics, Department of Statistics, Dodoma University, Tanzania. He received his BSc in 1985 and MSc in 1988, both from Acharya Nagarjuna University. MPhil in 1994 and the PhD in 2002 from the same university, Acharya Nagarjuna. His area of research includes statistical inference, quality control, and reliability estimation. He has published more than 140 articles in different peer-reviewed journals. Dear sir, with a warm welcome, may I now request you to chair this session.
Thank you, madam. Am I audible?
Yes, sir.
Am I?
Yeah.
Am I audible?
Yes, sir. Yes.
Okay.
Audible.
Thank you, madam. Nice words about me. Now let us go to our technical session number 21, a special invitee session. The first invited speaker, Professor Peter. He will He will give a lecture on world life dynamics and management optimization via statistics and mathematics. Shall I invite the professor or before that any?
I am here. Thank you very much. Thank you very much.
Okay.
So,
yeah, you are most welcome, welcome, Professor Peter.
thank you very much. Thank you very much. It's a great honor for me to be here.
Yeah, you're welcome.
Thank you. I have a PowerPoint presentation. I don't know how I show it.
Yeah, Professor.
I have a PowerPoint presentation.
Okay.
I can, okay, present now, it says. Maybe I go there.
Okay, Professor.
Okay, I do like that. Can you see this?
No, sir.
Yeah.
You can see?
Sir? Sister? No.
The
Sister
PowerPoint, sir,
yeah.
PowerPoint is not seeing.
Oh, you cannot. Okay.
Okay, sir.
Sister, whether you
share your entire
try
screen.
to introduce Professor Peter Lemon?
No, sir.
Yeah, okay.
You cannot see. Okay. Let's see.
We will do, Professor. Can we? Already sent it to
okay. Just.
Yes.
One window. Okay, can you see something?
Yes, sir.
Okay. Do you see it the way you want it to be seen, or can you see the whole picture? If I maximize like this, do you see anything else? Okay, anyway, you see this, as far as I understand, right?
Now it is
okay.
appearing. Now it is appearing.
Okay. I will thank you very much. It's a great pleasure for me to be here, and I'm very much honored to be in your conference. I will talk to you about wildlife dynamics and management optimization via statistics and mathematics. And
Professor,
yes.
sorry to disturb you, and put it in a presentation mode, full screen.
Please wait. Make it full screen. Yeah.
Make it to full screen.
Full screen.
Yeah.
Okay. Can you see now?
F5. Just you.
If I even do like this, can you see everything? Can you still see this?
Okay, it's okay.
Okay. So you see this? You see the first picture?
Yeah. Okay.
Okay. So okay, I will talk to you about wildlife dynamics and management optimization via statistics and mathematics. And you see two of the animals that I will talk about rather much, wolf and the moose, and they are very frequent in the north, in Sweden, in Russia, in the northern United States and Canada. Can you see this picture, this presentation? Can you see this text? This presentation is based on?
Yeah, Professor.
Okay, very good. This presentation is based on the following 3 open access articles. More details can be obtained from the links found below. And there are 3 articles there, and you can see them, and you can click on the links at a later point in time. And I'm very honored that this 3rd link is in Asian Journal of Statistical Sciences. You can see it there. I will talk about this in a few minutes. And in the link in the end, you can also see more references about quite different things that I've been studying. 3 alternative. Can you see the moose? Can you see the moose? Hello?
No, sir.
No, Professor.
No, sir.
Can you not see the picture with the moose?
We can't see, sir.
You can see.
Can't
Or
see,
you
sir.
cannot, or you can.
We cannot see.
Cannot see, or you can.
Sir, we cannot see.
Okay.
I think your slides are not moving.
Professor, shall let us move? Let us present from here.
Okay, please do that. I did send this to Professor Kumar maybe half an hour ago.
Yeah, Professor. We can present from here. So that.
Okay, very good, very good. That's very good. Now I can see it. Okay. So this is okay. So I will talk about wildlife dynamics and management optimization via statistics and mathematics. And you see me, and you see wolf and the moose. And the wolf and the moose are very common in the north, in Russia, in the United States, and Canada, and Sweden, for instance. Next, please. And this presentation is based on the following 3 open access articles, and more details can be obtained from the links found below. And in particular, I'm very happy that my 3rd article in this field is published now in Asian Journal of Statistical Sciences, and you can find it in the end. And the link in the bottom, there you can find more references to all other types of published articles. Next, please. This is too small to read, but we can go to next. Next, please. Okay, here you see a moose. And 3 alternative approaches to dynamic optimization of the management of moose populations will be presented. First, we have a Wiener process and stochastic optimal control theory are used to determine an explicit function for the optimal adaptive hunting level according to the methods described in Lomander 1. This is in Iranian Journal of Operations Research. Next, please. We maximize the objective function, which is the expected value, as you see in equation 1, where x is a state variable and u is a closed-loop control variable. Time is represented by t, small t, and capital T is a time horizon. F is the instantaneous profit rate, and S is the salvage value. E denotes expected value, and Z is a standard Wiener process. And there you see that X is the moose and the control is the rifle. Next, please. There you see the moose again, and this moose, I took a picture of this in Russia. Next, please. The same moose in Russia. Next, please. According to the Bellman principle of optimality, we may determine the value function V as the maximum of the sum of the net reward during the first short time interval, f dt, and the value function directly after that time interval, as in equation 3. The Taylor approximation gives you equation 4. Next, please. And the value function is approximately given by 11. You see this equation? And since the time derivative of v is not a function of u, we obtain the famous Hamilton-Jacobi-Bellman equation, as we see in equation 14, with the boundary condition as stated in equation 15. Next, please. The particular stochastic optimization problem is the following. We want to maximize the expected present value of wildlife management. We need the following notation. U is a control variable, the level of hunting at time t. X is the size of the wildlife population. And then we have 3 parameters, K, P, and F. They are objective function parameters. The net revenue of the hunting and meat values is the expression there, Ku minus Pu squared, the quadratic function. Strictly concave function of the hunting level. And then Fx, where f is simply a constant times x. this is proportional to the population level X, and that is the cost of destroyed forest plantations and cost of traffic accidents caused by the wildlife population. Population growth increases with the size of the population and decreases with the hunting level. The magnitude of the stochastic population changes depend on the standard Wiener process Z, the size of the population, and the risk parameter S. With R as a rate of interest in the capital market, we then have the following problem. Next, please. There in equation 16, you have the optimization problem with the particular assumptions just mentioned. And it's important to be aware that S is a parameter of the risk level, you can say. And next, please. The Hamilton-Jacobi-Bellman equation becomes equation 18. And now the problem is to determine the value function and the control function so that the Hamilton-Jacobi-Bellman equation is satisfied. We assume that the value function can be expressed as follows, as a quadratic function. Next, please. We need to optimize the control, U, and this is done here in 26. And then, as you see, I jump to equation 32, where we have using the optimal values of the control via the optimized control function, we get 32. Next, please. Now we have obtained a quadratic function that always has to be 0. If the function is not 0, then the Hamilton-Jacobi-Bellman equation is violated. Since the function must hold for all possible values of x, the size of the population, it's clear that we have 3 equations that can be used to determine the parameters a, b, and c. And these 3 equations are found here. They should all be equal to 0. So we can start by determining C and then B and then A and so on. Next, please. So we get C, B, and A as functions of the parameters. And then in 47, we get the value function as a quadratic function of X. And you can see it in equation 48, where we have the parameters of the problem also. Next, please. Next, we'll determine the optimal control function, and we know that this looks as it does here on this page. So U star, the optimal control, is a linear function of the stock or the population. X. Next, please. Then a numerically specified case with the figures from Sweden looks like this. Here you have the optimal total present value function, V, as a function of the population density, X, and the stochastic parameter, S. And you see that the level of the curve it decreases with S. So if the risk increases, the level of the optimum decreases, and also you see that the level of the population that gives you the maximum of the function also shifts to the left as the risk increases. So with more risk, you want lower population. Next, please. And here we have the optimal control, the hunting level, U star as a function of the population density X and the stochastic parameter S. And you see again that these are linear functions, and you see that if the risk increases in the Wiener process, you should hunt more. So you should have a lower population. Thank you. Next, please. Then the dynamical predator-prey system with wolf and moose populations is defined along the lines presented in Lomander 2. The dynamics is analyzed via simulation and an analytical solution to the linearized system close to the system equilibrium. The system is found to be stable, but it converges very slowly. The deterministic steady-state control optimization approach is applied to this system. And there you have this. Next, please. Next. And there we have again the wolf and the moose. And now we will look at them in the same meeting, in the same presentation. Next, please. So here we have the 2 differential equations in the small differential equation system, namely number 6. The exact background to these functional forms is found in the paper. I don't have time to talk about them. But in order to determine the parameters of 6, we do that by simply looking at the equations 7. And we simply estimate them through regression analysis. Next, please. The simplified estimated differential equation system looks like this. Next, please. And we can look at this system, the qualitative behavior of it through this graph. So we see that the path will be, you will have some orbit here. But you don't know more right now, but it will be working counterclockwise. And you also see that there is one equilibrium where both species are present, and that is, we call this equilibrium 1, where the moose population is 1061 and the wolf population is 29.47. In fact, these particular figures come from an island in the United States. I will give you more information about this later. But on this island, this is the equilibrium. So this is based on real data, so to say. Next, please. If we simulate the system with the deterministic simplified version of the system and start in the purple point, we will move to the yellow point in 200 years. So you can see that it converges very slowly. Next, please. If we start in the purple point, far away from the equilibrium, you see that you will end up in the yellow point after 200 years. So also now it converges very slowly. But anyway, next, please. So in equilibrium, we have 33. M dot and W dot are both 0. And then we can let U and V represent small deviations from the equilibrium. So we have 34 and 35. So the equilibrium values are M1 and W1. Next, please. Differential equation system is now written as 36. And that can be given also as 37. Next, please. So we see that we have different parts in these expressions, 39 and 40, and some of them are quadratic and some are linear. Next, please. As we approach an equilibrium, the second order terms go to 0 much faster than the first order terms. Hence, close to the equilibrium, U square is approximately 0 and UV is also approximately 0. Next, please. We may express a linear differential equation system of the linearized system as 43. And we also remember that the wolf population is in equilibrium, so this gives us 44. Next, please. Hence, the differential equation system is simplified to 45, and the parameter values that we now need are found in 46. With the parameter values in 46, we get expression 47. Next, please. We consider exponential functional forms as in 48, and then the time derivatives can be obtained and included in the equations as in 49. Next, please. Clearly, it's necessary that 50 is satisfied, and we want to be sure that non-trivial solutions can be obtained. This implies a condition found in 51. Hence, a quadratic equation has to be solved. This is found in 52. Next, please. And there we see 52 and 53, and there are in general two solutions. 54 and 55 reveal them. Next, please. Obviously, we have two complex roots. The real part is negative. This means that the solutions will be converging spirals. Since the real part is close to 0, the solution converges very slowly. In fact, it takes approximately 243 years for the spiral to get 50% closer to the equilibrium. this seems reasonable if we compare the spirals in figures 2 and 3, and we saw them before, that they converge very slowly. Next, please. And there we have the expressions of the linearized system. Next, please. Equilibrium 1 is given in 80, where we have M1 and M1 square, but in 81 we have only the parameters. So 81 is more useful. Next, please. In order to determine if the system is stable or unstable, it turns out that it's necessary to investigate the signs of the first part of the element in the first row and first column of the determinant 84. In order to do this, we first investigate the solution to an alternative problem found in equation 85. In 85, you have M star on the right-hand side, and that is the size of the moose population that maximizes the net moose production per year. Next, please. So, general results concerning the nature of equilibrium 1. If M1 is strictly less than M star, then the equilibrium is an unstable diverging spiral. If M1 is equal to M star, then the equilibrium is the center, and if M1 is greater than M star, then the equilibrium is a stable converging spiral. Next, please. So let's look at the linearized system. Here we see how this behaves, and that looks almost the same as the earlier system that we just simulated from the original functions. We start in the purple and end in the yellow after 200 years. Next, please. And here we can compare the linearized system, which is more yellow in behind, and then in the front we have the system generated by the simulation with the original equations, and we see that they behave almost identically. So the linearized system works well close to the equilibrium. Next, please. And this is a linearized system if we look at what happens far from the equilibrium. It starts in the purple point and ends in the yellow one. Next, please. And here we see that the linearized system does not function very well when we compare it to the simulation with the real functions. It seems that, well, they both start in the purple point and they end in the yellow points. And the yellow points seem to be close, but in fact, there are more orbits in the orange path than in the white path. So it doesn't really function very well as an approximation, far away from the equilibrium. Next, please. So let's introduce some optimal control of this system with a rifle. So we can control the moose population with R, and S times W is control of the wolf population. Yes? 1 minute. I don't hear you. I don't hear you.
Make it in 2 minutes.
2 minutes, okay. Yes, I'm sorry, but I was delayed in the beginning, but I will talk faster then. Next, please. Okay, 2 optimal values of the moose population are found here. Next, please. Moose and wolf population, optimal values. Next, please. Wolf population maximum. Next, please. Hunting of moose is a decreasing function of the valuation of the wolf population. Next, please. And the value of the total system. It's a function of the value of the wolf population. Next, please. So, a numerical approach to optimal adaptive integer pulse control of stochastic nonlinear system will now be presented. For most stochastic nonlinear systems, optimal adaptive control rules cannot be derived through analytical methods, and therefore a robust optimization algorithm is created. The complete nonlinear adaptively controlled stochastic system is simulated during 100 years for 100 alternative sequences of stochastic disturbances for every feasible integer combination of adaptive control rules. The optimal adaptive control rules that maximize the expected value of the objective function are selected as the optimal adaptive control rules. And you can read more about this in the article in the end. I will just use 1 minute to show the final graphs, if I can. Please, next. Next, please. Next, please. So here we see the nature of this. We look at both the value of the moose and the wolf. And the wolf enters in the value function of the population and also in the hunting, and the moose enters in the value of the hunting. And we work with the difference equations, and we use with the real stochastic deviations. Next, please. Next, please. So here are the really empirical estimations of also the risk in these processes. Next, please. Next, please. And here we can see how the average optimal moose hunting level is a increasing function of the risk. If there's no risk, or if there is risk. Next, please. And we see also optimal moose control limit is an increasing function of risk. Next, please. And the average optimal moose population level is an increasing function of the risk. Next, please. And the average population level is above the optimal control level for moose. Next, please. And if there is no risk, you see that the optimal wolf control limit and the average population size are almost the same. And then next, please. If there is risk, the control level is much higher than the actual population size. Next, please. And the average optimal wolf hunting level is much higher if you have risk than if you have no risk. And this result, I think, is one of the reasons why it's necessary to actually include risk in this type of analysis. Next, please. And the average optimal wolf population level is much lower if you have risk than if you have no risk. Next, please. And also the value goes down of the whole system in economic terms if you have risk. Next, please. So, two many central observations. The average optimal moose hunting level is a decreasing function of the wolf population value parameter and an increasing function of the level of risk in the predator-prey system. The average optimal wolf population level is an increasing function of the wolf population value parameter and a decreasing function of the level of risk in the predator-prey system. Next, please. Many different methods can be used to study the dynamics and to optimize the management of wildlife populations. This presentation includes 3 alternatives. Please continue the process and try to find the most relevant approach to your particular problems. Next, please. Thank you very much for your time and the most interesting conference.
Yeah, you're welcome, Professor. It's a very nice presentation, Professor.
Thank you.
Yes, indeed. Any questions from audience? Any questions? Professor, I have one doubt.
Sorry?
I have one doubt.
Yes.
Which algorithm procedure you used for optimization technique?
Once more, please. What?
Optimization algorithm.
Yes. In the different papers or different approaches. In the final version, I look at the expected present value of the whole system over 100 stochastic series of disturbances. And I look at every possible combination of these limits. So it's a complete enumeration. Because there are only one limit population for the moose and one limit population for the wolf. And I look at all possible combinations. So it's a foolproof system, so you can say. There is no local optima that I go to.
Do you have any?
Yeah,
do you have
Professor.
any test? Do you have any test procedure to which model is a valid model?
A valid model is, I would say, the optimal model given the system. And you can say if you want to test this with more random numbers or something like that, it's very easy. You just do it with all new random numbers as stochastic disturbances. Now I used 100 different random number sequences for during 100 years for both species. With the distributions where I approximated this, well, I used the you can say, I generated numbers myself.
Oh. Okay,
So
nice.
Srinivas, can I ask a question?
Okay, please.
I'm Ravi from Mysore.
Yeah.
Professor Peter, thank you for a very interesting talk. I would like to know the choice of your animals, moose and wolf. Was there any particular reason for you choosing wolf and moose?
Yes, there is one particular reason, and that is that in the United States, since 1958, in one isle, Ile Royale, one isolated island, they have measured these populations every year. So it's a very, very long time series, and there the wolf and moose have been together, and they have been, yes. So this is a complete description of this system for a long time period, and well, it's also an economically very important system, and it covers very large part of the globe because all of Russian Federation, Canada, United States, and the Nordic countries, we have these animals together.
Okay. Okay, thank you. Thank you, Professor Srinivas. Thank you.
Okay, thank you. Thank you very much, Professor Peter.
Thank you.
Very nice presentation, and I appreciate you. And now let us proceed to the next presenter, Professor Violet. Professor Violeta.
Good afternoon from Patras. How are you doing?
Yeah, nice man. Nice to see you, and please present your topic.
Can you hear me well, please?
Yeah, you are welcome, madam.
Thank you.
Yes, you are audible.
Yeah, you are audible.
Yeah, Professor. Violeta, yeah, it is audible.
Please share your presentation, madam.
Can you see my presentation now, please?
Yeah. Please proceed.
Thank you for the invitation. And I'm going to talk to you this afternoon for the ratio of two probability generating functions and an application in branching processes. So we are going first to show a historical overview of the Galton-Watson branching process, the probability tools that we are going to use in order to study this process, some applications in biological phenomena, and a problem that can be raised to solve in distribution theory, both in the univariate and the biovariate setup. So we may start from the observation of Kendall in his article in Journal of London Mathematical Society about a problem that Sir Francis Galton posed in the Educational Times something like 100 years ago in 1873 about adult males and their surnames and how this population of males evolve, having a percentage of giving no adult males or a percentage of giving only 1 or 2 or 5 adult males. And there is a solution there to this problem and how many people with the same surname we will have after some generations. later, Kental has pointed that from this problem, where we are interested in the human males, we are focusing now instead of the rate of diminution of the stock of family names, but also in customers waiting in queuing systems or in neutrons in a nuclear reactor. So we have a greater variety of problems with respect to branching processes. And of course, there is the old problem of the noblesse and the bourgeois family and the extinction of their names. So according to the Malthus theory and observations for the city of Bern between 150-83 and 170-83, that is 300 years, the proportion of the extinct families is really very high, 75% in 6th generation. So from there, we are going to see what is the Galton branching process and how it evolves in this time according to certain rules. The first rule is that we have initially only one individual. This is generation 0, and that individual is the ancestor. And then at the nth generation, each individual produces a random number of individuals that we call offsprings, and these are the next generation. The offsprings are mutually independent and also independent of the offsprings counts of the individuals from earlier generations, and usually they are identical distributed. So the symbols we are using is ZY for the individuals of the ith generation, and then the offsprings of the jth individual that belongs to the I-1 generation to the I generation. So these are the people that contribute the individual J to the next generation. So Z0 is 1 because we have only one ancestor, and from there on, let's have this first person, the ancestor, and then it gives 5 people here in the first generation, and then the first person of the first generation gives just 1, and then the second gives 2 to the next generation, and then the third gives no 1, and the fourth gives no 1, and the fifth gives 1. In total, we have 4 people in the second generation, and so on. We go to the third generation with no 1 from the first, 2 for the second, 3 for the third, and for this one, no 1. So in total 5, and so on for the fourth generation. I think that by now you have realized this mechanism of Galton-Watson branching process. So the probabilities tools that we are going to use here, since we are talking about discrete random variables on non-negative integers, is going to be the probability generating function. And if this is the probability mass function, that is a random variable taking value x, then the probability generating function, symbolized by the Greek letter p at the argument u, is nothing more but a series, and it is absolutely convergent. And the first derivative of this function is non-negative, so it is an increasing function of the argument u, and at 1, as we all know, this is the expected value of the random variable. And if we take the second derivative, which is also non-negative, that is a convex function, and this is the elements that we're going to use later in a figure. Of course, we all know that the probability generating function at 0 gives us the probability that the random variable takes the value 0, and of course at 1 is also 1. But we also need to know certain properties of these functions, and these have to do with the convolution of random variables. That means when they are independent, then the probability generating function of their sum is the product of the probability generating function. And this goes to more than 2 random variables. And in case that these random variables are not only independent but also identically distributed, then we have this result when the number of the summand is known. But when the number of the summand is a random variable, then things go differently, as then we have a random summation, and here n is also a random variable with its own probability generating function, and using the law of total probability and conditioning on the number of the summands, we get this formula. And so this new random variable, which is a random sum, the probability generating function is a composing function of the probability generating function of the summands, of the number of the summands to the probability generating function of each one of xy. So the commonly used discrete distribution is going to be the Bernoulli. This is the form of the probability generating function. Convolution of identical and independent Bernoulli give us the binomial distribution. Of course, Poisson plays its role, but we're going to see here the geometric, that is the number of failures until the first success in independent and identically distributed Bernoulli trials, and its generalization, that is the Pascal or negative binomial, where k might be a positive integer in the case of Pascal, or even a positive real number in general. How we are going to use these distributions? Let me show you how we are going to use in the case of the branching process. So the offsprings counts of an individual has probability given in general by this form, and we have the probability generating function of the offsprings. Then, according to the branching process as we developed earlier, we are interested in the number of individuals at generation V. So we have all these random variables which are independent, and we impose identical distributed as well, but it's a random summation that depends on how many ancestors they have in the previous generation. So according to what I showed you in the previous slides, there is a recurrence relation from the probability generating function of generation n with respect to the probability generating function of the number of individuals in generation n minus 1. And of course, we have the initial population. This recurrence relation is a forward recurrence relation. There is, in this simple case of univariate offsprings, that means offsprings of one type only, there is also a backward relation. One of the problems that usually is addressed here is the extinction probability, and is denoted by theta of n. That means the probability that the n generation contains no individuals, 0 individuals. So extinction has occurred by nth generation, and this with respect to the value of the random variable is the event that the random variable Zn takes the value 0. And extinction by nth generation means extinction by nth minus 1 generation plus extinction exactly at the nth generation. So this sequence has this relation, and so it's an increasing sequence. And using the backward now identity, we can see, putting at the argument u value 0, that this relation holds. And since this sequence is a non-decreasing and it is bounded, it converges, and so we can find the limit of this sequence, and this limit, theta star, satisfies this relation. So we have to solve this equation where P is the probability generating function of the number of the descendants in each generation. And this limit is the ultimate extinction probability of this process. And there is a well-known theorem that this probability is 1 if M, which is the mean value of the descendants of its individual, is less or equal to 1, or is less than 1 if M is greater than 1. So this mean value plays an important role, and it is called subcritical and critical cases, whether M is less than 1 or equal to 1, and supercritical cases, this case. So this is the probability generating function at 1 x value 1, and the slope of this tangent is the mean value of the random variable. So here is our first subcritical case. Here is M less than 1. It means that the slope of the tangent here is less than 1. And so we have one solution here and one here. So we take this solution. The extinction probability in both cases is 1. But in this case, here we have the probability generating function, but in the supercritical cases, that is, the slope of the tangent is greater than 1. So we have another solution here, and finally, we don't have extinction. You can find a lot of applets in the internet. Here is one from Wolfram project that you can choose. For instance, here, a Poisson distribution and C, 6th generation, a lot of simulations here, but this is just an instance that this process in 3 generation diminishes. Of course, it is a case where the probability of extinction is 1. Here also we have M 1.39, so no extinction. The probability of extinction is less than 1. It can't be a nuclear chain reaction, this process. Or we can choose a Bernoulli type distribution here with smaller or greater pi, and gives extinction or no extinction. An example would be genes and mutation for these processes. Of course, we can have a Euler evolutionary process where we have species and genus, that is, group of species, and so we have a branching process within a branching process. Either we can have a nuclear chain reaction, or we have epidemic models like SARS that we are facing these 2 years, and we can study the links between the affected patients and identify the generation that these patients belong to. And here, the parents are these people that are effective, and the offsprings are these that they carry the new infection. That type of applications appear here. But let me see. Okay, you can say everything. All right. Let me consider now the case where the offspring probability generating function is of this linear form. C is a constant, and it might be less or greater than 1, but positive in any case. Then it can be proved that the number of individuals in generation V, the probability generating function is given by this form, is again a linear fractional form. The proof can be, of course, given by induction, and it can be found in the book of Harris and Kimmel and Acherlof as well. But let me show you how this works here. This is an interesting case, as if we think a little bit more about this form, it is nothing more than a a zero modified geometric distribution. This is the probability generating function of a geometric distribution, and this is a weight here and another weight for 0 case. This is the geometric counting values until the first success, and in the case that C is less than 1, this is the geometric counting trials. So in both cases is a zero modified geometric distribution for the number of offsprings. However, we can also see the number of individuals in the nth generation in this form. And in such a case, this can be written like this, and it has this form considered by Kemp, actually is a paper in Sankhya. And when this relation holds, the product of this probability generating function is also a non-negative integer value distribution. This is a geometric, and this is a pseudo variable, as Kemp calls it. It reminds of the Bernoulli, but it's not, as here there's a minus. So evidently, we can write this probability generating function as the ratio of the probability functions of two geometric distributions. So that's the problem that I'm going to discuss, and this is a problem that refers to the distribution theory. And we have to consider this structure. We have two random variables, x and x2 are independent. We know x2, we know their results, the result of their convolution, of their summation, but we don't know what x is. So we are asking actually whether x1 and x2 are compatible. That is, if there is an x, a positive discrete random variable, so that this equation holds. We know the probability generating function of this random variable, we know the probability generating function of the other one, and so we are looking for the probability generating function of this one, which is going to be the ratio of the probability generating function of the others. So the question is, what are the conditions that allow such a ratio to be the PGF of a non-negative discrete random variable? In